Parasaurolophus walkeri stands as one of the most visually arresting and acoustically fascinating of all known dinosaurs, a large hadrosaur from the late Cretaceous of North America, whose hollow cranial crest extended dramatically behind the skull, and whose internal anatomy reveals a biological sound system of extraordinary sophistication. The name translates as near-crested lizard from Greek roots, assigned by William Parkes in 1922 to material recovered from the Campanian Age Oldman Formation of Alberta, Canada, and the species has since become one of the most studied and most discussed dinosaurs in all of vertebrate paleontology. The crest is a hollow bony tube that begins at the nostrils, curves upward and backward over the top of the skull, and terminates in a blunt or slightly expanded tip, positioned well behind the back of the skull in the most completely developed adults. The internal passages of the crest communicate directly with the nasal airways and formed a continuous airway loop through which breathing air passed, creating the conditions for resonant amplification of sounds produced in the nasal cavity, whose specific acoustic properties have been mathematically modeled from the preserved internal geometry of the crest passages. The specific sound-producing capability of the Parasaurolophus crest, the ability to generate low-frequency, far-carrying vocalizations analogous to those of modern large birds and some modern mammals, is one of the most completely and most rigorously documented behavioral capabilities of any non-avian dinosaur, and makes this animal genuinely unique in the Mesozoic world as a dinosaur whose specific communication biology can be assessed with quantitative precision from the physical evidence of its preserved anatomy. The geological context of Parasaurolophus is the Campanian stage of the Late Cretaceous period, spanning approximately 83 to 72 million years ago, during which the interior of North America was divided by the Western Interior Seaway into two land masses, Laramidia to the west and Appalachia to the east, whose separate faunal histories produced the extraordinary dinosaurian diversity documented in the Campanian fossil record of Western North America. The specific formations that have produced Parasaurolophus material include the Oldman Formation of Alberta, the Dinosaur Park Formation of Alberta, the Kaiparowitz Formation of Utah, the Two Medicine Formation of Montana, and equivalent Campanian formation. Parasaurolophus assemblages coming from the Campanian formations of Alberta and Utah. The ecological setting of these formations: coastal lowland environments adjacent to the Bearpaw Sea with diverse river systems, floodplains, and adjacent highland areas, produced an extraordinary diversity of dinosaurian species whose specific ecological relationships with Parasaurolophus included the predatory theropods, the competing herbivores, and the specific plant communities whose productivity supported the large body mass of adult Parasaurolophus individuals. The late Cretaceous Western Interior environment, warm and humid with diverse vegetation, including abundant angiosperms, conifers, and ferns, provided the specific ecological context within which the specific body size, diet, social behavior, and acoustic biology of Parasaurolophus evolved and functioned across the several million years of the Campanian, during which this genus inhabited the lowland environments of Laramidia. The body size of adult Parasaurolophus individuals, documented from the skeletal dimensions of the most completely preserved specimens, reached approximately 9 to 10 meters in total length, and an estimated mass of 2.5 to 3 tons in fully adult individuals, placing this species among the larger members of the Hadrosaur family and among the largest animals of its time in the specific ecosystems of the Campanian Western Interior. The skeletal proportions of Parasaurolophus are those of a typical large hadrosaur, a long, deep skull bearing the elaborate crest, a long neck connecting the skull to a deep-chested body, long and powerfully muscled hind limbs adapted for both bipedal and quadrupedal locomotion, shorter but robust forelimbs capable of weight-bearing during quadrupedal walking and browsing, and a long, stiff tail whose bulk was supported by ossified tendons running parallel to the vertebral spines. The specific limb proportions of Parasaurolophus, with hind limbs substantially longer than forelimbs, created the specific biomechanical situation in which bipedal locomotion at moderate to fast speeds was the primary gait for running and escaping predators, while quadrupedal locomotion at slower speeds was used during foraging, low-speed movement across the landscape. The specific dental anatomy of Parasaurolophus, with the elaborate dental batteries of hundreds of closely packed teeth arranged in functional rows that provided a continuously renewed grinding surface, was adapted for the processing of the specific plant types available in the Campanian coastal plain environment, and gave this animal one of the most effective plant processing dentitions documented for any terrestrial herbivore in the process. History of vertebrate life. The crest of Parasaurolophus walkeri, the most completely documented of the three recognized species, reached its maximum development in adult individuals, where it extended approximately 1.5 meters behind the back of the skull, creating a total crest length from nostrils to tip of approximately 1.5 to nearly 2 meters in the largest known specimens. The crest is a bony tube whose walls are composed of the specific nasal bones and premaxillary bones that form the upper portion of the skull, extended and elaborated far beyond their typical hadrosaur dimensions into the specific elongated structure that gives Parasaurolophus its distinctive silhouette. The internal anatomy of the crest, revealed by cross-sectional cuts through preserved specimens and by computed tomographic scanning of intact material, consists of 2 parallel nasal passages that run from the nostrils at the tip of the snout, curve upward into the crest tube, travel the full length of the crest to its tip, and then double back to return through a second pair of passages toward the posterior portion of the skull, where they connect with the airways leading to the lungs. This U-shaped double-loop architecture of the internal passages is the specific anatomical basis for the resonant acoustic properties of the crest, because sound waves generated in the nasal cavity travel through the full length of the passage system and are amplified at the specific resonant frequencies determined by the total path length of the passages and the specific geometry of the passage cross-sections. The specific resonant frequencies calculated from the internal passage geometry of well-preserved Parasaurolophus specimens by David Evans, Robert Rice, and colleagues correspond to low-frequency sounds in the range of approximately 30 to 80 Hz, frequencies that propagate effectively over long distances in the forested environments of the Cretaceous coastal plain. The 3 recognized species of Parasaurolophus: Parasaurolophus walkeri from Alberta, Parasaurolophus tubicen from New Mexico, and Parasaurolophus certocristatus from Utah, differ primarily in the specific size and geometry of their cranial crests, with walkeri having the longest and most dramatically posteriorly extended crest, tubicen having a similarly elongated crest with somewhat different curvature, and certocristatus having a distinctly shorter and more upwardly curved crest that gives this species a markedly different silhouette from its congeners. The specific differences in crest geometry among the 3 species create specific differences in the acoustic properties of each species' resonance system, because the total path length of the nasal passages is determined by the specific dimensions of the crest, and therefore differs among species in proportion to the crest size differences that distinguish them. The acoustic modeling calculations applied to the internal passage geometries of the three Parasaurolophus species produce resonant frequency estimates that differ among species in ways consistent with the crest size differences, with the longer crested Walkeri and Tubicen producing lower resonant frequencies than the shorter crested Certocristatus. This specific acoustic differentiation among species raises the possibility that the species-specific crest geometries may have functioned in species recognition, the ability of individuals to distinguish members of their own species from the other Parasaurolophus species they may have encountered in regions where the ranges of two or more species overlapped. The geographic distributions of the three species are partially allopatric, with different species predominating in different geographic regions of the Campanian western interior, but the possibility of range overlap in some areas makes the species recognition function of crest acoustics a biologically plausible component of the crest's evolved function. The acoustic modeling of the Parasaurolophus crest, published in its most complete and most rigorously quantitative form by Evans, Rice, and colleagues in 2009, applied the specific mathematical principles of acoustic resonance in tube-shaped chambers to the internal passage geometry of the TMP 2001 specimen of Parasaurolophus walkeri, one of the most completely preserved and best documented Parasaurolophus skulls in the world, to predict the specific resonant frequencies and harmonic overtones that the living animal's crest would have produced during vocalization. The mathematical model treats the internal passages of the crest as an acoustic tube whose resonant properties are determined by the specific path length of the passage, the specific cross-sectional geometry at different points along its length, and the specific termination conditions at the open ends of the passage system, where the airway connects to the nasal cavity at one end and to the pharynx at the other. The application of these acoustic principles to the specific passage geometry measured from computed tomographic scans of the TMP specimen produces resonant frequency predictions in the range of approximately 30 to 80 Hz, with additional harmonic frequencies at integer multiples of the fundamental resonant frequency. These predicted frequencies fall within the range of low-frequency sounds whose specific physical properties, long wavelength, low atmospheric attenuation, and high penetration of forested vegetation, allow effective, long-distance acoustic communication in the specific forested environments of the Campanian coastal plain that paleobotanical evidence confirms were the habitat of Parasaurolophus. The specific correspondence between the predicted acoustic properties of the crest and the specific environmental acoustic conditions of the habitat provides one of the most compelling functional ecological arguments for the divided sound-producing function of the Parasaurolophus crest available from any line of evidence. The evolutionary origin of the elaborate cranial crest of Parasaurolophus within the broader context of Hadrosaur cranial evolution provides important perspective on the specific, adaptive pressures that drove the development of this extraordinary anatomical structure from the more modest cranial anatomy of the basal Hadrosaur condition. The Hadrosaurs as a group are divided into two major subfamilies: the Hadrosaurines, which include flat-headed and solid-crested species, and the Lambeosaurines, which include the hollow-crested species of which Parasaurolophus is the most dramatically crested example, and the evolutionary transition from the flat-headed ancestral Hadrosaur condition to the hollow-crested Lambeosaurine condition is documented in the specific cranial anatomy of successive Lambeosaurine lineages, whose crests show progressively greater elaboration in the direction of the Parasaurolophus extreme. The specific anatomical modifications involved in crest evolution within the Lambeosaurines, the progressive elongation of the nasal bones, the expansion of the premaxilla into the crest structure, and the development of the specific U-shaped passage architecture that gives the fully developed Lambeosaurine crest its acoustic properties are traceable through the comparative anatomy of different Lambeosaurine genera, whose various crest shapes represent different points on the evolutionary trajectory toward the extreme crest development of Parasaurolophus. The evolutionary drivers of this progressive crest elaboration, widely interpreted as sexual selection for acoustic signaling capability in the context of mate competition and mate attraction within the breeding season social context of Parasaurolophus populations, are the same drivers that have produced elaborate acoustic signaling structures in diverse modern vertebrate lineages, from frogs to birds to marine mammals. The specific plant communities of the Campanian western interior, whose composition has been reconstructed from the diverse plant fossil record of formations like the Dinosaur Park Formation and the Kai-Parawitz Formation, provide the ecological basis for understanding the specific diet of Parasaurolophus and the specific foraging behaviors that this large hadrosaur employed to exploit the available plant resources. The Campanian flora of the western interior was one of the most diverse terrestrial plant communities documented for any geological interval and any geographic region, including abundant angiosperms, whose rapid diversification during the Cretaceous had transformed the terrestrial flora of North America from the conifer-dominated communities of the Jurassic to the angiosperm-rich communities of lutees. The Campanian. The specific plant types most extensively consumed by Parasaurolophus, inferred from the specific dental anatomy of the hadrosaur dental battery and from the comparison with the diets of modern large herbivorous vertebrates with comparable dental morphology, included the fibrous leaves, stems, and fruits of the diverse angiosperm plants, as well as conifer foliage and other plant parts available in the specific foraging range of these animals. The specific foraging behavior of Parasaurolophus, reconstructed from the specific limb proportions, neck length, and skull anatomy of this species, was consistent with browsing on vegetation at multiple height levels from the ground through the lower and middle canopy of the forest understory, with the long neck and laterally flexible skull allowing access to plant material across a wider height range than many other contemporaneous herbivores of the Campanian community. The specific role of Parasaurolophus as a large-bodied browser in the Campanian ecosystem, consuming large quantities of plant material daily to sustain the metabolic requirements of a 2 to 3 ton animal, made this species one of the most ecologically impactful herbivores in the communities where it occurred. The bone histology of Parasaurolophus specimens at different growth stages, where this analysis has been performed on material from the Two Medicine Formation and Dinosaur Park Formation populations, provides evidence for the specific growth rate trajectory of this species from juvenile through adult, and for the specific metabolic physiology implied by the observed growth rates. The fibrolamellar bone tissue that characterizes the rapidly growing juvenile phase in Parasaurolophus, comparable to the fibrolamellar tissue documented in other large hadrosaurs like Maiasaura and in diverse theropod and ornithischian lineages, is associated with elevated metabolic rates and high growth rates during the most energetically demanding phase of juvenile development. The progressive appearance of annual growth marks, the lines of arrested growth deposited during the annual period of reduced metabolic activity in the bone cortex of older individuals, documents the transition from the continuous rapid growth of the earliest juvenile years to the cyclically modulated growth pattern of older individuals approaching adult size. The specific growth rates inferred from the bone histological record in Parasaurolophus, while less completely studied than those of Maiasaura due to the smaller sample sizes available from the relevant formations, are broadly consistent with the rapid juvenile growth documented for other large hadrosaur species, and with the general picture of elevated metabolic rates in the Campanian hadrosaurs that the histological evidence from across the family supports. The specific age at sexual maturity and the specific age at which adult size was first achieved in Parasaurolophus are among the developmental biological parameters most directly relevant to understanding the acoustic biology of the privy crest, because the crest reached its full adult dimensions only at or near sexual maturity, making crest size a specific honest signal of individual developmental history and reproductive status. The specific habitat preferences of Parasaurolophus within the diverse environments preserved in the Campanian formations of Western North America provide ecological context for understanding the specific acoustic environment within which the crest vocalization system functioned and the specific predation pressures that the anti-predator behaviors of this species were adapted to manage. The Dinosaur Park Formation of Alberta, whose diverse vertebrate fossil record has been the subject of the most systematic ecological analysis of any Campanian formation, preserves Parasaurolophus material in sedimentary contexts, interpreted as representing the specific lowland floodplain environments adjacent to the Bearpaw Sea, including river channel deposits, floodplain muds, and the specific swampy or marshy environments associated with the coastal margin of the interior seaway. The specific acoustic properties of these forested floodplain environments, the specific attenuation rates of different sound frequencies in vegetation-dense lowland forest, the specific ambient noise levels of river channel and coastal environments, and the specific distances over which sounds of different frequencies could effectively propagate are directly relevant to understanding the adaptive significance of the specific resonant frequencies predicted for the resoned Parasaurolophus crest, because the evolutionary optimization of the crest would have been directed toward producing sounds of the frequencies most effective for long-distance communication in the specific acoustic environment of the habitat. The large theropod predators documented in the Dinosaur Park Formation, including Gorgosaurus libratus, the dromaeosaurid Sauronitholestes, and the troodontid Troodon formosus, would have exerted specific predation pressure on Parasaurolophus that the acoustic system may have served in part to manage through specific alarm calls that warned nearby conspecifics of predator approach, allowing coordinated escape responses by a social group rather than the individually scattered responses of animals that lacked effective acoustic communication. The specific evidence for social behavior in Parasaurolophus and the degree to which this species lived in social groups whose size and structure were relevant to the specific functional context of the acoustic crest communication system comes from the bone bed evidence of mass mortality assemblages and from the general hadrosaur social ecology inferred from the multiple lines of behavioral and ecological evidence available for this family. The specific occurrence of multiple Parasaurolophus individuals in the same geological context at some localities, including the remarkable assemblage of multiple growth stage individuals from the Kaiparowitz Formation of Utah, described by Terry Gates and colleagues, provides direct evidence for the co-occurrence of multiple individuals of different ages and sizes in the same location at the same time, consistent with a social species in which individuals of different developmental stages traveled together in social groups. The specific bone bed evidence for mass mortality of hadrosaur populations in the Campanian, including the extensive hadrosaur bone beds of the Dinosaur Park Formation and Two Medicine Formation, provides evidence for the aggregation of large numbers of hadrosaur individuals in shared space during specific seasonal events, consistent with the migrating or seasonally aggregating social behavior of modern large, gregarious herbivores whose bone beds are produced by mass mortality during periodic population stress events. The inference of social group living in Parasaurolophus from these multiple lines of evidence is directly relevant to the acoustic biology of the crest, because the specific communication functions that acoustic signals most effectively serve, individual recognition, social cohesion, alarm communication, reproductive advertisement, are all most relevant in the specific context of social group living, where the benefits of effective acoustic communication are realized across the range of social interactions that group members engage in across the annual cycle. The development of the Parasaurolophus crest through ontogeny, from its absence or minimal expression in hatchlings and small juveniles, through its progressive elaboration in growing individuals to its full adult expression in sexually mature individuals, provides important information about the specific relationship between crest development and life history stage, and about the specific age-related changes in the acoustic capabilities of individual animals across their lifetimes. The juvenile Parasaurolophus specimens, documented from the growth series available from Campanian formations, show the progressive development of the crest from a low ridge in small individuals through increasingly elongated, better developed crests in larger sub-adult individuals, with the full adult crest expression reached in individuals approaching adult body size. The specific developmental biology of crest growth, assessed from the bone histological evidence for growth rate in crest material and from the allometric analysis of crest dimensions relative to body size in individuals of different sizes, indicates that the crest grew at a rate faster than body size during the period of active crest elaboration in subadult individuals, consistent with a sexually selected structure whose rapid development is driven by the specific selection pressure for crest size at or near the time of first reproduction. The specific acoustic consequences of this ontogenetic crest development are that juvenile Parasaurolophus individuals, with their proportionally smaller or less developed crests, would have produced higher frequency sounds than adult conspecifics, creating a specific age-related acoustic signal that might have been detectable and meaningful to other members of the social group. The progressive development of the adult acoustic range, as the crest grew through the subadult phase, would have been associated with the progressive development of the specific behavioral and physiological changes of sexual maturity, connecting the acoustic ontogeny of the individual to the specific life history transitions of the Parasaurolophus developmental trajectory. The comparison of Parasaurolophus with other Lambeosaurine hadrosaurs of the Campanian, including Corythosaurus casuarius, Lambeosaurus lambe, Hypacrosaurus altispinus, and various others, provides the comparative anatomical context within which the specific anatomical specializations of the Parasaurolophus crest are most fully understood, and within which the specific functional and evolutionary significance of the extreme posterior extension of the Parasaurolophus crest relative to the more modestly developed crests of its contemporaries is most directly accessible. Corythosaurus, one of the most commonly recovered Lambeosaurine hadrosaurs in the Dinosaur Park Formation, bears a helmet-shaped hollow crest that rises vertically above the skull rather than extending posteriorly like that of Parasaurolophus, creating a different crest geometry with different acoustic resonance properties that have been modeled to produce somewhat higher resonant frequencies than the Parasaurolophus crest. Lambeosaurus lambe, another common dinosaur park formation Lambeosaurine, has a distinctive forward-projecting hollow crest with a solid posterior extension, again with a different crest geometry, producing different acoustic properties from either Parasaurolophus or Corythosaurus. The specific co-occurrence of multiple Lambeosaurine species with different crest geometries in the same formation. The Dinosaur Park Formation preserves multiple Lambeosaurine species, each with a distinctively shaped crest, provides compelling evidence that crest shape functioned in species recognition. Because the specific acoustic and visual distinctiveness of each crest type would have allowed individuals to identify the species of conspecifics at both visual and acoustic range. The acoustic differentiation among co-occurring Lambeosaurine species represents one of the most compelling arguments for the species recognition function of hollow crest anatomy in the Lambeosaurine hadrosaurs generally, and for the specific acoustic communication function of the Parasaurolophus crest, in particular, the taphonomy of Parasaurolophus specimens, and the specific geological processes that preserved the material available for scientific study, provides important context for assessing the completeness and representativeness of the available fossil record of this species, and for understanding the specific biases in what aspects of Parasaurolophus biology are most and least completely documented from the preserved evidence. The preservation of cranial material in Parasaurolophus is generally good relative to many large dinosaurian species, with multiple skulls from different localities and different growth stages available for comparative study, a preservation quality that reflects in part the robust construction of the crest. The dense bone of the crest walls is relatively resistant to the mechanical destruction that more delicate skeletal elements experience during the process of fossilization. The preservation of post-cranial skeletal material is more variable, with some specimens preserving substantial portions of the vertebral column, limb girdles, and limb elements, and others representing primarily or exclusively cranial material, reflecting the specific taphonomic processes of different depositional environments and the specific effects of scavenging, hydraulic transport, and chemical dissolution on different skeletal elements in different burial contexts. The specific geographic distribution of known Parasaurolophus localities across the Campanian formations of western North America, from Alberta in the north through Montana, Utah, and New Mexico in the south, documents the specific geographic range of this genus within the Campanian Laramidian fauna and provides a framework for understanding the specific regional variation in crest morphology among the three species. That is one of the taxonomically and evolutionarily most significant features of the Parasaurolophus fossil record. The sexual dimorphism of the Parasaurolophus crest, and the specific question of whether the observed variation in crest size within species populations reflects a sex-based difference in crest development comparable to the size dimorphism in acoustic display structures documented in many modern vertebrate species, has been debated in the scientific literature and remains one of the more actively investigated aspects of Parasaurolophus biology. The specific prediction from sexual selection theory that the crest of Parasaurolophus functioned as a sexually selected display structure is that males would show larger or more elaborate crests than females, because in most vertebrate systems where acoustic display structures are sexually selected, the competing sex, typically males, develops the larger and more elaborate versions of the display structure that females prefer, or that conspecific males respond to as a dominant signal. The specific evidence for sexual dimorphism in Parasaurolophus crest size is ambiguous at present, reflecting the limited sample sizes available from any single formation and the specific challenges of sex determination in fossil material that lacks the soft tissue sexual characteristics available in living animals. The bimodal distribution of crest sizes observed in some samples of Lambeosaurine material, where two size classes of individuals are present at sizes inconsistent with simple ontogenetic age differences, has been interpreted by some researchers as reflecting sexual dimorphism in crest development, with the smaller crested individuals being females. The resolution of the sexual dimorphism question in Parasaurolophus awaits the recovery of larger and more complete samples from specific well-documented formation assemblages that can support the statistical analysis needed to distinguish genuine sexual dimorphism from the other sources of crest size variation, including ontogenetic stage, individual variation, and the specific environmental conditions that influenced crest development in different individuals. The specific soft tissue anatomy of the Parasaurolophus nasal region, whose specific configuration determined the specific acoustic properties of the crest vocalization system in ways that the preserved skeletal anatomy alone cannot fully specify, has been approached through the comparison with modern large birds, whose nasal anatomy provides the most directly relevant biological reference for the specific soft tissue structures involved in sound production in a non-avian dinosaur with archosaur ancestry. The specific structures involved in sound production in modern crocodilians, the vocal apparatus of the larynx, and the associated resonating chambers of the nasal cavity provide the most ancestrally relevant comparison for non-avian dinosaurian sound production, while the specific acoustic amplification structures of modern large birds with elongated tracheas, including the whooping crane, and various tropical birds with coiled tracheas that amplify low-frequency sounds, provide functional analogues for the specific acoustic function of the elongated nasal passage of the Parasaurolophus crest. The inference that Parasaurolophus produced sounds by forcing air through the nasal passages of the crest, with the sound waves generated in the larynx or nasal tissue amplified and shaped by the resonant properties of the crest passage system, is the specific sound production model that the internal anatomy of the crest most directly supports, and that the comparison with the acoustic biology of modern animals most directly validates. The specific soft tissue structures that line the inner surface of the crest passages, the mucosal membranes, the associated blood vessel networks, and the potential presence of specific vibrating tissue folds that served as the primary sound-generating elements within the passage system are preserved in no fossil specimen, but are inferred from the specific bony contours of the prizing passage walls, visible in computed tomographic scans, to have been analogous to the nasal tissues of modern archosaurs in their general biological character. The predator guild of the Campanian western interior, against whose specific hunting capabilities the behavioral ecology of Parasaurolophus was specifically adapted, included some of the most formidable carnivorous dinosaurs documented from the North American Cretaceous record, and would have exerted intense selection pressure on both the individual defensive behaviors and the social alarm systems of gynuses. Large hadrosaurs. Gorgosaurus libratus, the dominant large theropod predator of the dinosaur park formation fauna, was a tyrannosaurid of approximately 8 to 9 meters in length and approximately 2.5 tons in mass, whose hunting capabilities assessed from the specific biomechanics of its locomotor system and from the bite force implications of its skull anatomy would have represented a genuine and frequently lethal threat to adult Parasaurolophus individuals. The smaller but agile dromaeosaurids of the Campanian fauna, including Saurornitholestes, Langstoni, and Dromaeosaurus albertensis, represented a different predatory threat, focused particularly on juvenile or injured individuals, whose smaller size made them accessible to pack-hunting predators, capable of coordinating attack strategies against prey too large for any individual hunter. The acoustic alarm communication function of the Parasaurolophus crest, in the context of this specific predator guild, would have allowed the rapid propagation of alarm signals through a social group whose members were spread across an area of forest large enough that visual alarm signals between the most distantly separated individuals would have been unreliable or impossible. The specific temporal and spatial pattern of the acoustic alarm signal, a low-frequency sound that propagates rapidly through the air at the speed of sound and is detectable by all members of a social group within its mine. Effective range, essentially simultaneously, represents an alarm system of extraordinary efficiency compared with the slower, direction-dependent alarm propagation of visual signals in forested environments. The hydrological ecology of Parasaurolophus and the specific relationship between this large hadrosaur and the river systems, lakes, and coastal waterways of the Campanian western interior has been the subject of periodic discussion in the paleontological literature since the early history of hadrosaur research, when the webbed forefeet of some hadrosaur specimens suggested to early researchers that these animals were semi-aquatic. The modern interpretation of hadrosaur ecology, informed by the comprehensive reanalysis of hadrosaur locomotor anatomy and the functional assessment of the specific limb proportions and musculature of large hadrosaurs, supports a primarily terrestrial ecology for Parasaurolophus and its relatives, with aquatic habitats used for drinking, foraging on aquatic vegetation, and potentially escape from terrestrial predators, but forming a supplementary, rather than primary component of the normal activity range. The specific evidence for the terrestrial ecology of Parasaurolophus includes the robust hindlimb anatomy adapted for sustained bipedal locomotion on firm substrates, the specific dental battery morphology optimized for the processing of terrestrial vegetation rather than the soft aquatic plants that a primarily aquatic herbivore would consume, and the specific skeletal proportions that are biomechanically most consistent with the load distribution requirements of a primarily terrestrial walker and runner. The proximity of Parasaurolophus to water in the specific depositional environments that produce the most abundant Parasaurolophus fossil material, the river channel, and floodplain sediments of the Oldman and Dinosaur Park formations, reflects the specific geological processes that concentrate vertebrate remains in fluvial and lacustrine sedimentary environments, rather than the specific ecological preferences of the living animals, whose primary habitats would have been the forested floodplains and adjacent upland areas of the Campanian coastal plain, rather than the river channels and lake margins where preservation was most likely. The thermoregulatory hypotheses for the Parasaurolophus crest, proposed in the earlier scientific literature as alternatives to the acoustic communication function, have been progressively evaluated against the specific evidence of crest internal anatomy and have been found to be less consistent with the physical evidence than the acoustic function hypothesis. The thermoregulatory hypothesis proposed that the large blood vessel networks inferable in the crest, particularly the blood vessel channels, visible in the outer bony walls of the crest in well-preserved specimens, served as a heat exchange surface, allowing the animal to shed excess body heat by increasing blood flow through the crest in warm conditions. The specific assessment of the thermoregulatory function requires comparing the surface area available for heat exchange in the crest with the body mass of the animal and the specific heat exchange rates achievable in a structure of the bod, documented crest geometry, and the published calculations by Jim Hobson and others suggest that the crest surface area is inadequate for effective thermoregulation in an animal of Parasaurolophus body mass, particularly when compared with the much larger surface areas provided by the general body surface. The functional anatomy of the crest, with its hollow interior passages providing relatively little surface area for blood-to-air heat exchange, further constrains the plausibility of the thermoregulatory function, and the specific comparison with modern animals, that use specialized anatomical structures for thermoregulation, the nasal countercurrent heat exchangers of many modern vertebrates, the bill structures of some modern birds, confirms that the Parasaurolophus crest architecture is much more consistent with a resonating acoustic chamber than with a thermoregulatory radiator. The progressive convergence of the scientific literature on the acoustic function hypothesis reflects the accumulation of specific anatomical, functional, and comparative biological evidence that collectively makes the acoustic interpretation the most biologically coherent explanation for the specific morphology of the Parasaurolophus crest. The specific patterns of wear on the teeth of Parasaurolophus individuals at different life stages, assessed from the microscopic surface texture analysis of fossil tooth specimens using scanning electron microscopy, provides the most direct available evidence for the specific food types consumed by different age classes of this species and documents the specific ontogenetic dietary changes that accompanied the growth from juvenile to adult in Parasaurolophus populations. The dental battery of adult Parasaurolophus, with its hundreds of closely packed teeth arranged in functional rows that provided a continuously renewed grinding surface, was specifically adapted for the mechanical processing of fibrous plant material through a specific orthal chewing motion in which the upper and lower dental batteries slid past each other in a motion that efficiently ground plant material between the opposing tooth surfaces. The specific microscopic wear textures produced by different food types on the enamel surfaces of Hadrosaur teeth have been characterized through experimental feeding studies with extant herbivorous reptiles and comparison of wear textures with those produced by known food types, allowing the inference of specific diet components from the preserved wear textures on fossil Hadrosaur teeth. The application of dental microwear analysis to Parasaurolophus tooth specimens from different formations and different growth stages is one of the productive current research directions in Parasaurolophus dietary biology that is progressively building a more specific and more quantitatively grounded picture of what this species actually ate in the specific environmental contexts where different populations lived, complementing the more general dietary inferences available from the gross anatomy of the dental battery and the comparison with the diets of modern large browsing herbivores. The specific acoustic environment of the Campanian coastal plain ecosystems inhabited by Parasaurolophus, assessed from the specific vegetation structure and topographic characteristics of the habitats, documented from paleobotanical and sedimentological evidence in the relevant formations, provides the environmental acoustic context within which the adaptive significance of the Parasaurolophus crest acoustic system is most fully understood. Sound propagates through the atmosphere at approximately 340 meters per second, but its effective range for communication depends critically on the specific attenuation rates of different frequencies in the specific atmospheric and vegetation conditions of the communication environment. Low-frequency sounds, whose long wavelengths are less scattered by obstacles in the path of propagation, attenuate at lower rates per unit distance in forested environments than higher-frequency sounds, and the specific low frequencies predicted for the Parasaurolophus crest resonance are therefore specifically well adapted for long-distance propagation through the forested floodplain environments that the sedimentological record of the Campanian coastal plain formations suggests were the typical habitat of this species. The specific maximum communication distances achievable with the Parasaurolophus crest vocalizations in the specific acoustic environment of the Campanian coastal forest, estimated from the predicted source level of the crest vocalization and the specific frequency-dependent attenuation rates of forested environments at the relevant frequencies, are substantially greater than the distances achievable with higher frequency vocalizations of the same source level, providing a specific quantitative advantage for long-range social communication that is directly relevant to the ecological situation of a large social herbivore living in forested environments where visual communication range is limited by vegetation density. The integration of the Parasaurolophus crest acoustic system with the specific visual display function of the crest, assessed from the specific morphology and coloration potential of the crest as a visual signal in the specific visual ecology of Campanian social groups, provides a more complete functional picture of the crest's role in Parasaurolophus social biology than the acoustic function alone encompasses. The crest of Parasaurolophus is visually distinctive at the distances relevant to visual communication within a social group, with the specific elongated posteriorly directed shape of the walkery crest and the different silhouette shapes of the Tubicin and Certocristatus crests, providing species-specific visual signals detectable at the distances typical for visual social communication in open or semi-open environments. The specific coloration of the crest in living Parasaurolophus, while unknown from direct fossil evidence, can be approached through the general principles of visual signaling in social vertebrates, where display structures used in mate competition and mate attraction are typically more brightly colored or more contrastingly marked than the general body coloration, and where species-specific color patterns on display structures contribute to species recognition and individual quality assessment in the specific visual systems of the relevant species. The specific functional ecology of the combined visual acoustic display of the Parasaurolophus crest in the social context of Campanian Hadrosaur populations, the specific situations in which visual display of the crest silhouette, the primary communication channel, the specific situations in which acoustic signaling through the crest passages was the primary channel, and the specific situations in which both modalities were used simultaneously for maximum signal effectiveness is one of the more nuanced behavioral ecological aspects of Parasaurolophus social biology, whose reconstruction requires the Parasaurolophus integration of multiple lines of functional, anatomical, and comparative biological evidence. The specific evidence from the Kaiparowits Formation of Utah, one of the most recently described and most scientifically productive Campanian formations for Parasaurolophus research, includes the remarkable discovery of a Parasaurolophus specimen representing an individual whose specific growth stage and crest development provide important information about the specific ontogenetic trajectory of crest elaboration in this species. The Kaiparowits Formation, deposited approximately 76 to 74 million years ago in a subtropical lowland environment adjacent to the Cretaceous seaway, preserves a diverse Campanian fauna including the Parasaurolophus species Certocristatus, the species with the most distinctively short and upwardly curved crest in geological contexts that confirm the subtropical lowland habitat of this Utah population. The specific crest morphology of Certocristatus, with its substantially shorter crest relative to walkery and Tubicin, produces a proportionally shorter internal passage system whose resonant acoustic properties at the frequencies predicted from the specific passage geometry differ from those of the longer crested species in ways that have been used to argue that the shorter crest of Certocristatus may have been associated with higher pitched or differently modulated vocalizations than the longer crested species. The paleoecological context of the Kaiparowits Formation fauna, one of the most thoroughly studied Campanian paleo communities in Western North America, thanks to the extensive program of field research and specimen collection by the Natural History Museum of Utah and collaborating institutions, provides the most complete ecological portrait of the specific environment inhabited by Certocristatus, and is progressively building a more complete understanding of the specific ecological role of Parasaurolophus in the southern Laramidian fauna than was available from the earlier studied northern formations. The specific pathologies documented in Parasaurolophus skeletal material, including healed fractures, joint disease, and specific bone infections visible in the surfaces of recovered specimens, provide evidence for the specific physical challenges and health conditions experienced by individual animals across their lifetimes, and for the specific mechanical demands that the life activities of this species placed on the skeletal system. The documentation of healed fractures in Hadrosaur material, including some specimens attributable to Parasaurolophus or closely related Lambeosaurines, confirms that individual animals survived specific traumatic injury events and continued to grow and function after the injury, implying sufficient behavioral capability to avoid predation during the healing period and the physiological resources to support bone remodeling while maintaining normal body functions. The specific patterns of joint wear in older Parasaurolophus individuals, visible in the articular surfaces of well-preserved limb and vertebral joint material from large individuals, provide evidence for the specific mechanical loading histories of these joints across the lifetime of the animal, and for the specific gait patterns and activity levels that produce the documented wear distributions. The occurrence of specific bone infections in some Hadrosaur specimens, visible as abnormal bone texture and specific remodeling responses at the surfaces of infected elements, confirms that individual Parasaurolophus animals experienced bacterial or fungal bone infections that the immune system either successfully resolved, leaving a healed lesion visible in the fossil, or failed to resolve before the animal's death, with the infected tissue preserved in the state it was in at the time of the animal's death. The pathological record of Parasaurolophus, while less completely studied than that of more commonly recovered species like Tyrannosaurus rex or Triceratops, is progressively accumulating as new and more completely preserved specimens are recovered, and as paleopathological analysis becomes a more standard component of the comprehensive scientific description of new material. The crests of Lambeosaurine hadrosaurs, including Parasaurolophus, have been the subject of numerous functional hypotheses since the earliest comprehensive anatomical studies of these animals in the early 20th century, with the acoustic function hypothesis gaining progressive dominance over competing hypotheses, as the specific anatomical evidence for the internal passage system has been more thoroughly documented, and as the specific acoustic modeling calculations have more rigorously quantified the resonant properties of the crest passage system. The snorkel hypothesis, which proposed that the crest served as an air storage organ, allowing the animal to breathe underwater during aquatic foraging excursions, has been evaluated against the specific anatomy of the crest passages and found to be inconsistent with the passage architecture, which lacks any mechanism for sealing the passage opening during submersion, and which would have provided an air storage volume far too small to be functionally significant for an animal of Parasaurolophus body mass. The olfactory enhancement hypothesis, which proposed that the elongated nasal passage of the crest increased the surface area available for olfactory receptor tissue and thereby enhanced the olfactory sensitivity of the animal, has been found to be partially consistent with the passage anatomy, but insufficient as a complete functional explanation for the extreme passage elongation of the fully developed Parasaurolophus crest, which is substantially longer than would be needed for olfactory enhancement alone. The species recognition hypothesis, which proposes that the species-specific crest shapes of co-occurring Lambeosaurine species served as visual and acoustic species recognition signals, remains one of the strongest and most thoroughly supported of the specific functional hypotheses for the Lambeosaurine crest, and is the hypothesis most directly supported by the specific co-occurrence of multiple crest-shaped differentiated species in the same formations and the specific acoustic differentiation among species predicted from their different crest geometries. The global context of Parasaurolophus within the worldwide Late Cretaceous Hadrosaur radiation, which produced a diverse assemblage of closely related species across North America, Asia, Europe, and South America, places this North American genus within the broader evolutionary and biogeographic history of the Hadrosaur family, and illuminates the specific evolutionary relationships and biogeographic connections that connect Parasaurolophus to the larger story of Hadrosaur evolution across the Cretaceous. The Hadrosaurs originated from iguanodontian ornithopod ancestors in the early Cretaceous of what is now Eurasia, dispersed into North America across land connections in the early Late Cretaceous, and subsequently diversified explosively in both North America and Asia to produce the extraordinary diversity of species documented in the Campanian and Maastrichtian fossil record. The Lambeosaurine clade, to which Parasaurolophus belongs, appears to have evolved its hollow crest anatomy within the Laramidian fauna of North America and subsequently dispersed into Asia during the Late Cretaceous, as evidenced by the Asian Lambeosaurine hadrosaurs like Tsintausaurus spinohynus from China and Olorototon aharensis from Russia, whose hollow crests reflect the same fundamental Lambeosaurine anatomical heritage as the North American forms. The specific position of Parasaurolophus within the Lambeosaurine phylogenetic tree, as recovered in the most recent comprehensive phylogenetic analyses of hadrosaur relationships, places this genus as a member of a clade of particularly long-crested Lambeosaurines that includes some of the most acoustically sophisticated of all the hollow-crested hadrosaurs, and whose evolutionary history documents the specific evolutionary trajectory toward extreme crest elongation that culminated in the remarkable anatomy of the adult Parasaurolophus walkeri skull. The discovery history of Parasaurolophus, tracing the recovery and description of successive specimens from the initial type material described by Parkes in 1922, through the accumulating series of discoveries across the 20th and 21st centuries, illustrates both the progressive expansion of the known material base for this species and the specific research programs that have most advanced the scientific understanding of Parasaurolophus biology. The type specimen of Parasaurolophus walkeri, a partial skull and skeleton recovered from the Oldman Formation of Alberta, established the basic anatomical features of the species: the dramatically elongated posterior crest extension, the specific proportions of the skull relative to the crest, and the general post-cranial anatomy that have been confirmed and elaborated by every subsequent specimen. The New Mexico specimens of Parasaurolophus tubicin, described by Charles Wyman in 1931 from material recovered from the Kirtland Formation, extended the known geographic range of Parasaurolophus to the southern portion of the Campanian Laramidian fauna and established the second recognized species of the genus with its own distinctive crest geometry. The Utah specimen of Parasaurolophus certocristatus, described by John Ostrom in 1961 from the Kaiparowitz Formation, established the third species with its distinctively short and upwardly curved crest, and further extended the known geographic range of the genus. The exceptional juvenile specimen described from the Kaiparowitz Formation by Terry Gates and colleagues in 2007, nicknamed Joe, provided one of the most completely preserved small growth stage Parasaurolophus individuals, known and has contributed importantly to the understanding of ontogenetic crest development in this genus. The accumulating history of Parasaurolophus discovery documents the progressive building of a scientific understanding from the initial morphological description through the taxonomic and phylogenetic refinements of the mid-20th century to the functional, anatomical, and acoustic analyses of the late 20th and early 21st centuries that have established the acoustic communication function of the crest on a rigorous quantitative basis. The specific coloration of Parasaurolophus, a dimension of the biology of this animal that the fossil record cannot directly document from preserved pigment or integument, but that can be partially approached through the evolutionary biology of color, vision, and coloration in the biology. Archosaur lineage is one of the more speculative but scientifically interesting aspects of this animal's visual appearance that the complete biological portrait of Parasaurolophus must address. The color vision system of modern birds, all of which possess four-cone color vision, detecting wavelengths from the ultraviolet through the near-infrared, is the evolutionary product of the Archosaur visual system that non-avian dinosaurs also possessed, and the inference that Parasaurolophus and its contemporaries saw the world in the same rich tetrachromatic color space as modern birds is one of the most directly supported biological inferences about the sensory biology of these animals. From the comparative biology of modern archosaurs, the specific coloration of the Parasaurolophus crest, whose visibility and visual distinctiveness at social communication distances would have been enhanced by bright or contrasting color patterns comparable to those of modern large birds with elaborate display structures, is the most direct target for coloration inference in this species, because the specific selection pressure for visual distinctiveness in a sexually selected display structure provides the most direct evolutionary argument for the development of conspicuous coloration in this specific anatomical region. The specific comparison with modern large-crested birds, whose cranial crests bear species-specific color patterns that contribute to species recognition and mate quality assessment, including the colorful crests of cassowaries, cockatoos, and various cockatoos, hornbills, provides the most directly relevant modern analogues for the specific visual ecology of the Parasaurolophus crest in the context of Campanian social behavior. The locomotor biology of Parasaurolophus, assessed from the specific biomechanical analysis of its limb proportions, joint geometries, and associated musculature, estimated from the specific muscle attachment scars on the preserved skeletal elements, provides a detailed picture of the specific movement capabilities of this large hadrosaur and the specific ways in which its locomotor system was adapted for the demands of its specific ecological lifestyle in the Campanian coastal plain. Environment: the hindlimb anatomy of Parasaurolophus, with long femora, tibiae, and metatarsals proportioned for efficient bipedal locomotion at moderate to fast speeds, is biomechanically consistent with a sustained walking speed of perhaps 5 to 7 kilometers per hour and a maximum running speed of perhaps 15 to 25 kilometers per hour in a bipedal sprint, estimated from the specific scaling relationships between limb proportions and locomotor performance, documented in modern large bipedal birds, and applied to the specific skeletal dimensions of Parasaurolophus. The forelimb anatomy of Parasaurolophus, with its somewhat shorter but robust forelimbs bearing broad three-fingered hands with the fingers modified into hooves in the manus, supports a quadrupedal walking gait at slow speeds. In addition to the bipedal running gait used at higher speeds, creating the specific dual-gate locomotor system characteristic of most hadrosaurs, whose ecological lifestyle combined quadrupedal low-speed foraging with bipedal high-speed escape from predators. The specific muscle mass distribution of the Parasaurolophus hind limb, estimated from the sizes and orientations of muscle attachment scars on the femur, tibia, and pelvis, indicates powerful extensor muscles capable of generating the rapid hind limb extension needed for acceleration from standing to running speed at the onset of a predator escape response, consistent with the ecological requirement for rapid acceleration in an animal that was the prey of large tyrannosaurid predators. The geographic variation among the three Parasaurolophus species across the Campanian fauna of Western North America provides evidence for the specific biogeographic history of the genus and for the specific evolutionary and ecological processes that produce the specific crest-shaped differences that distinguish the three species. The northernmost species, Walkeri from the Oldman and Dinosaur Park formations of Alberta, had the longest and most posteriorly directed crest of the three species. A crest morphology associated with the lowest resonant frequencies in the acoustic modeling calculations and with the longest effective range for acoustic communication in the specific forested environments of the Alberta Campanian fauna. The southernmost species, Tubicin from the Kirtland Formation of New Mexico, had a similarly elongated crest with somewhat different curvature from Walkeri, suggesting a close evolutionary relationship between the two long-crested species, while maintaining the specific morphological distinctiveness that would have supported species recognition between populations. The intermediate species, Certocristatus from the Kaiparowitz Formation of Utah, occupied a geographic position between Walkeri to the north and Tubicin to the south, while bearing the most morphologically distinctive crest of the three species, the short, upwardly curved crest that gives this Utah species a silhouette strikingly different from its congeners. The specific biogeographic pattern of these three species across the latitudinal gradient of Campanian Laramidia, with the two long-crested species at the extremes of the range and the short-crested species in the middle, may reflect the specific evolutionary history of population isolation and differentiation that occurred, as Parasaurolophus populations were periodically divided by habitat changes or seaway fluctuations that separated northern from southern Laramidian faunas across the Campanian interval. The feeding ecology and daily energy budget of Parasaurolophus, assessed from the specific body mass estimates, the metabolic rate estimates consistent with the endothermic physiology implied by bone histological evidence for elevated growth rates, and the specific dietary requirements of a large hindgut fermenting herbivore, provides a quantitative perspective on the specific ecological role of this species as one of the dominant large herbivores of the Campanian coastal plain ecosystem. An adult Parasaurolophus of approximately 3 tons body mass, maintaining a metabolic rate consistent with the avian-grade endothermy implied by the bone histological evidence for sustained rapid juvenile growth, would have required approximately 40 to 80 kilograms of plant dry matter daily to sustain its metabolic requirements. A food intake rate broadly consistent with the requirements of modern, large endothermic herbivores of comparable body mass, and supported by the specific processing capability of the Hadrosaur dental battery. The daily foraging time required to acquire this food intake, estimated from the foraging rates of modern large browsing herbivores in vegetation-rich environments comparable to the Campanian coastal plain flora, would have occupied a substantial proportion of the daily activity budget of adult Parasaurolophus, leaving specific windows for social interaction, predator vigilance, acoustic display, and other non-foraging activities whose duration and timing would have been shaped by the specific ecological demands of the Campanian environment and the specific social biology of the species. The specific energetic cost of crest vocalization within this daily energy budget, the metabolic investment in the muscular effort and neural processing required to produce the sustained low-frequency vocalizations that the acoustic function hypothesis proposes for the Parasaurolophus crest, is estimated to be relatively small compared with the total daily metabolic requirement, making the energetic cost of the acoustic display system a minor fraction of the total daily energy budget, and therefore a minor evolutionary constraint on the development of the elaborate crest vocalization system. The paleoneurological anatomy of Parasaurolophus, assessed from the specific endocranial morphology visible in the brain, endocasts, prepared from skull material of this species, provides information about the specific neural capabilities of this hadrosaur and about the specific brain regions most relevant to the acoustic behavior associated with the crest. The brain endocasts of hadrosaur skulls, including material attributable to Parasaurolophus and its close relatives, preserve the three-dimensional shape of the brain cavity and the specific anatomical landmarks corresponding to different brain regions, allowing the reconstruction of the relative sizes of the olfactory lobes, cerebral hemispheres, optic lobes, and cerebellum in these animals. The specific proportions of the Parasaurolophus brain, compared with those of modern archosaurs at comparable encephalization levels, indicate a brain organization broadly consistent with the general ornithischian pattern. Relatively large optic lobes suggesting the importance of visual information in the behavioral ecology of this species, a cerebellum of size consistent with the complex coordination demands of large-bodied bipedal and quadrupedal locomotion, and cerebral hemispheres of proportions consistent with the behavioral complexity expected for a large social herbivore with elaborate acoustic communication capabilities. The specific neural processing requirements of the acoustic behavior associated with the Parasaurolophus crest, the generation of specific vocalizations, the recognition of conspecific vocalizations, the integration of acoustic information with visual and olfactory information in social behavioral decisions would have required specific neural circuitry in the auditory processing and vocal production regions of the brain, whose specific anatomy in Parasaurolophus is not fully resolvable from the gross endocranial morphology, but whose functional character can be inferred from the comparison with the neural anatomy of modern archosaurs with comparable acoustic communication systems. The interspecific interactions of Parasaurolophus with the other large herbivorous dinosaurs of the Campanian western interior, the ceratopsians, the ankylosaurs, and the non-lambeosaurine hadrosaurs that shared the Campanian coastal plain with Parasaurolophus populations, provide an important ecological dimension of this species' biology whose understanding requires the integration of dietary, habitat, and behavioral evidence from across the Campanian fauna. The ceratopsian dinosaurs that co-occurred with Parasaurolophus in the Campanian, including Styracosaurus albertensis, Centrosaurus apertus, and various other horned dinosaurs in the Alberta Campanian and Cosmoceratops richardsoni, Utah Ceratops getty, and others in the Utah Campanian, were large herbivores whose specific dietary preferences and habitat requirements would have overlapped partially with those of Parasaurolophus, creating the potential for resource competition in periods or localities of food scarcity. The specific dietary differences between ceratopsians and hadrosaurs, inferred from the different dental morphologies of the two groups, ceratopsians with their scissor-like shearing dentition adapted for cutting tough, fibrous plant material, and hadrosaurs with their grinding dental batteries adapted for pulverizing softer vegetation, suggest that the two groups occupied partially differentiated dietary niches within the shared Campanian plant community, reducing direct resource competition for the most nutritious plant types. The ankylosaurs of the Campanian fauna, with their low browsing ecology focused on ground-level vegetation, would have competed with Parasaurolophus primarily for low-growing plant resources rather than the higher browse that the longer-necked hadrosaurs could access, further partitioning the plant resources of the Campanian coastal plain among the diverse community of large herbivores. The specific vocalizations that Parasaurolophus produced with its crest, and the specific behavioral contexts in which different types of vocalizations were deployed in the social ecology of Campanian hadrosaur populations, are the behavioral biological questions that the acoustic modeling of the crest most directly enables, and that the comparison with the acoustic communication systems of modern large vocal vertebrates most directly illuminates. The fundamental resonant frequency of the Parasaurolophus walkeri crest, predicted by the acoustic modeling calculations to be in the range of approximately 30 to 80 Hz, corresponds to the range of frequencies used by modern large vocal vertebrates for long-distance contact calls that maintain social cohesion among group members spread across forested terrain. The ability to modulate the pitch, amplitude, and temporal pattern of vocalizations to produce specific calls with specific meanings rather than a single invariant sound would have depended on the specific anatomy of the soft tissue sound-producing structures in the nasal region and on the specific neural control of the air flow through the crest passages and the specific range of vocalizations available to Parasaurolophus is estimated to have been at least as diverse as the acoustic repertoire of modern large birds that use resonating tracheal or nasal chambers for low-frequency sound production. The specific behavioral contexts in which different vocalizations would have been most adaptively significant include the maintenance of contact among group members during foraging when visual contact was intermittent, the signaling of alarm when predators were detected, the specific acoustic displays of adult males competing for breeding status or territory, the acoustic solicitation of mates during the breeding season, and the parent-offspring communication during the post-hatching phase of juvenile care. The acoustic biology of Parasaurolophus, reconstructed from the physical anatomy of the crest passage system and from the comparative biology of modern large vocal vertebrates, documents one of the most sophisticated acoustic communication systems known from any non-avian dinosaur. The skeletal anatomy of the Parasaurolophus skull, beyond the crest, reveals a specialized feeding apparatus whose specific design is among the most effective plant processing systems documented for any terrestrial herbivore in the history of vertebrate life. The premaxillar and dentary bones of the Parasaurolophus skull bear the specific beak-like front portions of the jaws, the toothless beak region where plant material was first grasped and torn from the feeding substrate, whose specific shape and robustness reflect the specific mechanical requirements of harvesting the diverse plant types available in the Campanian vegetation. Behind the beak, the specific toothed region of the jaws bears the Hadrosaur dental battery, the remarkable grinding apparatus, whose hundreds of tightly packed teeth provided a continuously self-renewing grinding surface, whose effectiveness for plant material processing exceeded that of any other dental system in the Mesozoic terrestrial fauna. The specific jaw joint anatomy of Parasaurolophus, with the quadrate bone bearing the jaw articulation positioned specifically to produce the characteristic hadrosaur jaw motion when the adductor muscles contracted, allowed the unique hadrosaur orthal power stroke in which the upper and lower tooth rows slid past each other in a motion optimized for grinding rather than the simpler up-down jaw motion of most other vertebrates. The specific jaw muscles of Parasaurolophus, estimated from the specific sizes and orientations of the muscle attachment surfaces visible on the skull bones, were capable of generating substantial bite forces across the full extent of the dental battery, allowing the efficient processing of the diverse range of plant materials that the broad dietary spectrum of Campanian Parasaurolophus populations encompassed. The early 21st century has seen a remarkable acceleration in the pace and quality of Parasaurolophus research, driven by the development of computed tomographic imaging, capable of revealing the specific internal anatomy of fossil skulls without destructive sampling, by the accumulation of new specimens from productive Campanian formations across western North America, and by the development of the specific acoustic modeling approaches that have quantified the resonant properties of the crest passage system with a rigor and precision that earlier qualitative descriptions of the acoustic function could not achieve. The CT scanning of the TMP 2001 skull of Parasaurolophus walkeri, the specimen that provided the primary anatomical basis for the acoustic modeling calculations published by Evans, Rice, and colleagues, revealed the specific three-dimensional geometry of the internal passage system with a spatial resolution and completeness that had not been achievable with earlier radiographic methods, and that allowed the specific mathematical modeling of the resonant acoustic properties from first principles of acoustic physics rather than from simplified geometric approximations. The discovery and description of the juvenile Parasaurolophus specimen from the Kai-Parawitz Formation by Gates and colleagues in 2007 provided the first well-documented small growth stage individual and enabled the specific ontogenetic analysis of crest development in this species that earlier research had been unable to perform due to the scarcity of juvenile material. The continued exploration of productive Campanian formations across the Kai-Parawitz Plateau of Utah, the Dinosaur Park Formation of Alberta, the Two Medicine Formation of Montana, and equivalent formations elsewhere in western North America continues to recover new Parasaurolophus material that is progressively filling in the gaps in the documented biology of this extraordinary dinosaur and providing the material basis for increasingly sophisticated analyses of its anatomy, physiology, and behavior. The interpretation of the Parasaurolophus crest as a sound-producing organ marks one of the more significant conceptual advances in the understanding of dinosaurian behavior that the science of paleontology has achieved, because it transforms this animal from an anatomically unusual but behaviorally uninterpreted dinosaur into a specifically acoustically sophisticated animal whose specific communication biology can be assessed from the physical evidence of its preserved anatomy with a degree of precision and confidence available for very few other behavioral interpretations in non-avian dinosaur paleontology. The behavioral picture that emerges from this interpretation of large social hadrosaurs moving through the forested floodplains of the Campanian coastal plain, their low-frequency contact calls carrying across kilometers of dense vegetation to maintain social cohesion among group members spread across the foraging range, their specific alarm calls alerting nearby conspecifics to the approach of predators with a speed and effectiveness that visual signals in forested terrain could not match, and their breeding season acoustic displays advertising individual quality and species identity through the specific, modulated low-frequency vocalizations whose acoustic properties were shaped by the specific geometry of their cairns. Individual crests is one of the most behaviorally specific and most fully evidence-grounded reconstructions of behavioral ecology available for any non-avian dinosaur, and has contributed substantially to the public understanding of dinosaurian behavioral complexity and biological sophistication. The 100 facts about Parasaurolophus, presented in this documentary, are the current product of more than a century of scientific investigation of this extraordinary animal. Each fact grounded in specific physical evidence and specific analytical methods, and together they constitute the most complete available portrait of one of the most acoustically remarkable animals in the history of vertebrate life. The convergent evolution of resonating acoustic chambers in diverse modern vertebrate lineages, the elongated tracheas of some bird species, the nasal resonating chambers of some large bovids and cervids, the vocal sacs and resonating chambers of frogs and toads, and the various resonating structures of marine mammals, provides a broad comparative framework for understanding the specific acoustic biology of Parasaurolophus as one of the most extreme and most specifically documented examples of resonating chamber evolution in the history of vertebrate life. The common functional theme connecting all of these independent evolutions of resonating chambers is the amplification of specific acoustic frequencies through constructive interference of sound waves within the resonating structure, a physical phenomenon whose specific implementation in different structures across different lineages reflects the specific anatomical raw material available for modification in each lineage and the specific acoustic requirements of the CART communication system in each ecological context. The Parasaurolophus crest is extreme among these convergent examples in the specific combination of very low resonant frequencies, very large physical dimensions, and the specific integration of the resonating chamber into the nasal passage. Anatomy of the skull that makes the crest simultaneously a respiratory structure and an acoustic signaling structure in a way that most other resonating chamber implementations do not achieve. The specific evolutionary trajectory that produced this extreme convergent solution in Parasaurolophus, the progressive elongation of the nasal passages through the Lambeosaurine Hadrosaur lineage over the specific evolutionary timescale of the Campanian, represents one of the most completely documented evolutionary pathways to a convergent acoustic adaptation available from any vertebrate lineage, and provides a uniquely detailed case study in the invergent, specific evolutionary processes that produce the extreme anatomical specializations visible at the peaks of adaptive evolutionary radiation. The scientific legacy of Parasaurolophus for paleontology and for the broader public understanding of prehistoric life is substantial, because this dinosaur has served as the primary example in every scientific and popular discussion of dinosaurian acoustic communication, and has been the central focus of the most rigorous and most complete quantitative acoustic analysis performed on any non-avian dinosaurian sound-producing structure. The specific image of Parasaurolophus as the dinosaur that could sing, as a Cretaceous animal with a sophisticated acoustic communication system whose low-frequency vocalizations carried across kilometers of Campanian forest to maintain social contact, signal alarm, and advertise reproductive quality in the specific behavioral ecological context of large social hadrosaur populations, has been one of the most powerful and most widely communicated examples of the behavioral sophistication of non-avian dinosaurs, and has contributed substantially to the transformation of the public understanding of these animals, from behaviorally simple reptilian automatons to complex, socially sophisticated animals whose behavioral lives rivaled those of many modern vertebrates in their richness and ecological significance. The continuing research on Parasaurolophus, the accumulation of new specimens, the progressive refinement of acoustic modeling methods, The application of new isotopic and histological analyses to the growing sample of well-preserved material ensures that the scientific understanding of this extraordinary dinosaur will continue to advance beyond what 100 facts of this documentary represent, adding new dimensions to the portrait of an animal that already stands as one of the most behaviorally specific and most completely understood non-avian dinosaurs in the fossil record. 100 facts about Parasaurolophus, the dinosaur that could sing, and behind each fact the specific physical evidence, the specific analytical science, and the specific human intellectual achievement that recovered from the rock. One more specific truth about the most extraordinary acoustic organism that the history of vertebrate life has produced. The evolutionary transition from the relatively modest cranial anatomy of the basal Hadrosaur ancestor to the extreme crest development of Parasaurolophus walkeri represents one of the most dramatic examples of rapid morphological evolution driven by sexual selection available from the vertebrate fossil record, comparable in its scope and pace to the rapid horn and frill elaboration documented in the ceratopsian lineage, and to the rapid mandibular elaboration documented in the Jurassic mammals of the Yanliao biota. The specific rate of crest elongation through the Lambeosaurine phylogenetic sequence, assessed from the specific crest dimensions of successive Lambeosaurine lineages in relation to the temporal spacing of these lineages in the geological record, indicates a rate of morphological change substantially faster than typical background rates of morphological evolution in other vertebrate skeletal characters, consistent with the runaway selection dynamics that sexual selection theory predicts for structures whose size directly signals fitness to potential mates or to competing conspecifics. The specific evolutionary mechanism driving this rapid elaboration, the positive feedback between female preference for longer crested males and the evolutionary response of male crest length to this preference, is the same Fisherian runaway mechanism proposed for the rapid elaboration of peacock tail feathers, deer antlers, and the diverse secondary sexual characters of other sexually selected vertebrate traits, and its operation in the Hadrosaur lineage produced the spectacular result of the Parasaurolophus walkeri crest within the geological time available in the Campanian. The recognition of the Parasaurolophus crest as a product of sexual selection, acting on a structure with genuine acoustic function, rather than a purely ornamental structure whose value is entirely arbitrary, adds an additional layer of evolutionary complexity to the interpretation of this structure and connects the acoustic biology of Parasaurolophus to the evolutionary ecology of honest signaling in animal communication systems. 100 facts about Parasaurolophus, the dinosaur that could sing, conclude with the recognition that this extraordinary animal, whose low-frequency vocalizations once resonated through the Cretaceous forests of western North America with a power and a depth that no mammal has since equaled in those environments, represents one of the most biologically remarkable chapters in the history of vertebrate acoustic evolution. The Campanian coastal plain ecosystems of 75 to 72 million years ago were filled with the sounds of Parasaurolophus populations, maintaining social contact across kilometers of dense floodplain forest, signaling alarm at the approach of Gorgosaurus predators with the specific urgency of the alarm call, whose carrying power and directional clarity made it the most effective predator warning system available to any Campanian herbivore. The breeding season acoustic displays of adult Parasaurolophus, whose specific modulation patterns and harmonic structures communicated individual identity, body condition, and developmental history to potential mates across the visual screen of the Cretaceous forest, were among the most acoustically sophisticated mating displays in the Mesozoic world. The specific physical evidence for all of this the hollow tubes of the fossilized crest, the computed tomographic scans revealing the precise internal passage geometry, the acoustic modeling calculations quantifying the resonant frequencies, the comparative biological context of modern large vocal vertebrates, and the evolutionary biological theory of sexual selection applied to the specific population dynamics of companion hadrosaur communities, is as physically real as the rock that preserved the skulls, and as mathematically rigorous as the acoustic physics that governs the resonant properties of tube-shaped chambers. 100 facts. The dinosaur that could sing, the most remarkable acoustic story in the history of vertebrate life, recovered from the Cretaceous rock and offered to the understanding of the present. The 100 facts about Parasaurolophus presented in this documentary represent the current state of a scientific understanding that has been built across more than a century of investigation. From the initial type description by William Parkes in 1922, through the functional anatomical analyses of the mid-20th century, through the quantitative acoustic modeling of the early 21st century, to the continuing program of specimen discovery and analysis that is advancing the understanding of this extraordinary dinosaur, with each new field season and each new analytical application to existing material. The physical evidence on which these facts are based, the skulls in the collections of the Royal Ontario Museum, the Royal Tyrrell Museum of Paleontology, the New Mexico Museum of Natural History and Science, the Natural History Museum of Utah, and the other institutions that have recovered and curated Parasaurolophus material, is as permanent and as accessible as any physical evidence in natural history, science, available to the researchers of the present and the future, who will continue to extract new information from existing specimens as analytical methods advance, and who will continue to recover new specimens from productive companion formations as field research continues across the western interior of North America. The 100 facts represent a scientific snapshot of the current best understanding of Parasaurolophus biology, its anatomy, its acoustics, its ecology, its evolution, its social behavior, and its place in the specific ecological communities of the Campanian western interior, and they are offered as one complete telling of what science currently knows about one of the most extraordinary and most behaviorally specific non-avian dinosaurs that the fossil record has preserved for human discovery and scientific understanding: the crest, the passages, the sound, the extraordinary biological reality of the dinosaur that could sing, the enduring scientific and popular fascination with Parasaurolophus, sustained across more than a century of scientific investigation and across every generation of popular dinosaur enthusiasm from the 1920s to the present, reflects the specific combination of visual distinctiveness, behavioral specificity, and ecological richness that makes this dinosaur uniquely compelling among the diversity of species documented in the Campanian western interior fauna. The dramatic silhouette of the elongated crest, extending far behind the skull in adult walkery individuals, and giving this dinosaur one of the most immediately recognizable profiles of any non-avian dinosaurian species, is the specific visual feature that has made Parasaurolophus one of the most commonly depicted and most widely recognized dinosaurs in both scientific illustration and popular culture from its initial description through the present. The specific acoustic function of the crest, whose mathematical modeling has transformed this visual curiosity into a biologically specific acoustic instrument, whose resonant properties can be calculated from first principles, has added a specific behavioral and ecological dimension to the understanding of Parasaurolophus that the purely morphological analysis of the crest could never supply, and that connects the physical anatomy of this animal to the specific behavioral ecology of the Campanian communities it inhabited. The evolutionary biological context of sexual selection and acoustic signaling, in which the crest is most fully understood, connects the specific anatomy and acoustic properties of Parasaurolophus to the broader scientific understanding of how natural selection and sexual selection operate on acoustic communication structures in large social vertebrates, making the study of this dinosaur a contribution to evolutionary biology as well as to paleontology. 100 facts about Parasaurolophus. The most acoustically sophisticated non-avian dinosaur. The dinosaur that could sing. The specific population dynamics of Parasaurolophus in the Campanian western interior, assessed from the abundance of Parasaurolophus material relative to other large dinosaurian herbivores in the relevant formations, provides evidence for the specific ecological role of this species as a common to abundant large herbivore in the communities where it occurred, and for the specific demographic parameters that sustained its populations across the Campanian interval. The relative abundance of Lambeosaurine hadrosaurs, including Parasaurolophus, in the bone beds and isolated skeletal assemblages of the Dinosaur Park Formation has been quantified in the systematic faunal surveys published by various researchers, and these surveys indicate that Lambeosaurines, including Parasaurolophus, constituted a substantial fraction of the large herbivore fauna in this formation, with their relative abundances consistent with high-density populations sustained by the productive vegetation of the Campanian coastal plain environment. The specific demographic parameters relevant to the Parasaurolophus population ecology, the age at first reproduction, the annual fecundity, the age-specific survival rates, and the specific causes of mortality at different life stages are partially constrained by the bone histological evidence for growth rate and by the population age structure inferences available from the size distributions of individuals in fossil assemblages. The inference that Parasaurolophus populations were characterized by high juvenile mortality and lower adult mortality, consistent with the demographic patterns of modern large, endothermic herbivores in predator-rich environments, places the acoustic communication system of the crest in a specific demographic context in which the survival benefits of effective alarm communication and the reproductive benefits of effective acoustic mate attraction were both substantial enough to exert strong evolutionary selection on the development of the crest vocalization system. The population ecology of Parasaurolophus is therefore a dimension of the biological understanding of this species that directly connects the specific anatomy of the crest to the specific ecological situation within which that anatomy was evolutionarily shaped. The specific evidence for Parasaurolophus in the Two Medicine Formation of Montana, one of the formations in which this genus has been identified, though the material is less abundant than in the Oldman and Dinosaur Park formations of Alberta, provides evidence for the specific geographic range of walkery, or a closely related form, in the southern extent of the Alberta-Montana faunal province, and for the specific environmental conditions in which these animals lived in the far specific ecological setting of the Two Medicine Formation inland basin. The Two Medicine Formation, deposited in a more inland environment than the coastal plain settings of the Alberta Campanian formations, preserves a somewhat different ecological community from that of the Dinosaur Park Formation, with different relative abundances of Hadrosaur species, reflecting the specific habitat preferences of different species in the inland basin environment versus the coastal lowland environments further north. The presence of Parasaurolophus material in the Two Medicine Formation, alongside the extensive Maiasaura nesting evidence that makes this formation one of the most important sources of information about Hadrosaur reproductive biology, provides a specific community context in which the acoustic communication biology of Parasaurolophus and the reproductive parental care biology of Maiasaura were contemporaneous features of the same paleo-environmental setting. The specific ecological interactions between the Lambeosaurine Parasaurolophus and the Hadrosaurine Maiasaura in the two Medicine Formation community, the degree to which these two large hadrosaurs of different subfamilial affiliation shared the same habitats, competed for the same plant resources, or were attracted to the same feeding and nesting areas, are among the ecological questions that the comparative paleoecological study of the two Medicine Formation fauna is progressively addressing as the systematics and relative abundances of the different large herbivore species in this formation become better documented. The ear anatomy of Parasaurolophus and the specific hearing capabilities of this large hadrosaur, as assessed from the preserved anatomy of the inner ear region of the skull and from comparison with the hearing biology of modern archosaurs, provides important complementary information to the acoustic modeling of the crest sound production system, because the effectiveness of the acoustic communication system depends on both the specific sound production capabilities and the specific hearing sensitivity of the communicating individuals. The specific inner ear anatomy of hadrosaurs, where it can be assessed from the specific morphology of the bony labyrinth preserved in skull material, indicates an auditory system organized along the general archosaur pattern with a papilla bacillaris, the sound-sensing organ analogous to the cochlea of mammals, of proportions consistent with sensitivity to a range of frequencies, including the low frequencies predicted for the Parasaurolophus crest resonance. The specific hearing sensitivity of modern archosaurs at different frequencies, measured in behavioral audiograms that determine the minimum sound pressure level detectable at each frequency, shows that both birds and crocodilians have their peak sensitivity in the range of 1 to 4 kHz, but retain measurable sensitivity at lower frequencies, with modern crocodilians in particular showing sensitivity down to frequencies as low as 20 Hz that falls within the predicted resonant frequency range of the Parasaurolophus crest. The inference that Parasaurolophus individuals could hear the low-frequency vocalizations produced by the crests of conspecifics at distances substantially greater than the minimum audibility threshold at these frequencies would allow, is directly relevant to the functional effectiveness of the acoustic communication system, because the evolutionary development of the crest sound production system would only be favored if the receiving individuals were sufficiently sensitive at the relevant frequencies to detect and behaviorally respond to the signals being produced. The specific fossilization processes that converted the skeletal remains of Parasaurolophus individuals into the mineralized fossils available for scientific study, and the specific diagenetic modifications that the original bone mineral experienced during millions of years of geological burial, are directly relevant to the quality and reliability of the specific anatomical information recoverable from Parasaurolophus specimens, and to the specific analytical methods most appropriate for extracting biological information from this material. The mineralization of Parasaurolophus bone during the fossilization process involved the progressive replacement or infilling of the original hydroxyapatite bone mineral with diagenetic minerals from the surrounding burial environment, and the specific degree to which the original biological mineral has been preserved versus replaced in any given specimen is directly relevant to the reliability of the specific geochemical analyses, stable isotope measurements, trace element analyses that might be applied to the material for biological interpretation, the specific preservation of internal crest anatomy in the best preserved Parasaurolophus skulls, where the original hollow passage system has been preserved in 3 dimensions without the collapse or infilling that would obscure the passage geometry needed for acoustic modeling, reflects the specific combination of sedimentological and geochemical conditions in the specific burial environments of these specimens that prevented the mechanical collapse of the thin-walled crest passages and the cementation of the passage interiors with secondary minerals. The continued improvement of specimen preparation and casting techniques, combined with the increasing accessibility of computed tomographic scanning for the non-destructive characterization of internal anatomical structures in fossil specimens, is making the internal anatomy of Parasaurolophus skulls increasingly accessible to the specific analyses, acoustic modeling, digital endocast preparation, growth stage assessment, whose results are most directly relevant to the specific research questions of Parasaurolophus biology. The role of Parasaurolophus in the popular culture of dinosaur enthusiasm, from its early depictions in scientific illustration and museum, mounts through its appearances in major motion pictures and its representation in toys, games, and popular books, provides a specific cultural perspective on the scientific significance of this species and on the specific features of its biology that have most captured the public imagination across the century since its initial description. The first museum mount of Parasaurolophus, assembled from the available skeletal material in the collections of major natural history museums in the decades following Parks's initial description, presented the dramatic crest silhouette of this species to museum visitors for the first time, and established the visual impression of the elongated posteriorly directed crest as the most immediately distinctive anatomical feature of this dinosaur. The appearance of Parasaurolophus in Steven Spielberg's 1993 film Jurassic Park, where several individuals of this species were depicted in a brief scene during which they produced distinctive vocalizations through their crests, introduced the acoustic function of the Parasaurolophus crest to the broadest popular audience of any medium, and established the connection between this dinosaur and vocal communication in the popular imagination. The subsequent proliferation of Parasaurolophus imagery in popular dinosaur media, in museum exhibits, in educational programs, in popular books, and in the diverse digital and physical media through which dinosaur biology is communicated to the public, has been substantially driven by the specific behavioral interest generated by the acoustic function interpretation of the crest, which transforms this anatomically distinctive but otherwise conventionally proportioned hadrosaur into a specifically behaviorally interesting animal, whose capacity for sophisticated vocal communication captures the imagination of audiences across all ages. The specific bone microstructure of the Parasaurolophus crest walls, examined in thin sections from the bony walls of the crest tube in specimens where this analysis has been performed, provides information about the specific growth rate and growth pattern of the crest itself during the ontogenetic crest elaboration phase, and about the specific tissue types that compose the walls of the sound resonating chamber. The crest walls of Parasaurolophus are composed of the same fibrolamellar bone tissue that characterizes the rapidly growing skeletal elements of the general body skeleton in juvenile and subadult hadrosaurs, confirming that the crest grew at the same elevated rate as the rest of the skeleton during the rapid juvenile growth phase, and was not a specially slowly grown or slowly mineralized structure whose growth rate was decoupled from that of the general skeleton. The specific vascular density visible in histological sections of the crest wall bone, assessed from the number and diameter of the vascular canals visible per unit area of bone cross-section, is broadly consistent with the vascular density of other rapidly growing hadrosaur skeletal elements, and does not indicate a specifically high vascular density that would support the thermoregulatory hypothesis for crest function through enhanced blood flow. The specific pattern of growth mark deposition in the crest wall bone of older individuals where successive annual growth marks document the specific pattern of crest growth rate modulation across the annual cycle in sexually mature animals, is one of the more detailed developmental biological questions about Parasaurolophus crest ontogeny that the histological analysis of crest wall, bone, from individuals at different growth stages could address, and that is awaiting the recovery of sufficiently complete and well-preserved crest material from individuals of known ontogenetic stage to support the relevant histological sampling, the ichthyology and aquatic ecology of the Campanian western interior seaway, whose presence defined the biogeographic context of Parasaurolophus, and whose fluctuating margins created the specific coastal plain ecosystems that Parasaurolophus inhabited, provides an important environmental dimension of the paleoecological setting of this dinosaur, whose specific effects on the terrestrial ecology of adjacent land areas were substantial. The western interior seaway, at its maximum extent during the early Campanian, divided North America into the two landmasses of Laramidia and Appalachia, and created extensive coastal lowland environments along the margins of both landmasses, whose specific ecological productivity was enhanced by the marine influence on local climate and by the nutrient inputs from the adjacent marine environment. The specific effects of the seaway on the local climate of the adjacent coastal plain environments, including the moderating influence on temperature extremes, the enhancement of precipitation through the moisture supply from the adjacent sea, and the specific fog and mist conditions that coastal marine settings produce, created the specific warm, humid, and productive vegetation conditions that sustained the high diversity and biomass of large herbivorous dinosaurs documented in the Campanian coastal plain faunas. The progressive transgression and regression of the western interior seaway across the Campanian interval, driven by the eustatic sea level changes associated with the specific tectonic and oceanographic history of the Cretaceous, created the specific paleo-environmental changes in the coastal plain environments that drove the specific faunal turnovers and biogeographic events documented in the Campanian dinosaurian succession, including the specific patterns of Parasaurolophus species, distributions across the latitudinal extent of Laramidia that reflect both the environmental gradients of the Campanian coast and the specific biogeographic histories of the mast. Different Parasaurolophus species populations. The specific adaptations of the Parasaurolophus digestive system for the efficient extraction of nutrients from the fibrous plant material that dominated its diet are inferred from the general digestive biology of large, hindgut fermenting herbivores and from the specific anatomical features of the Parasaurolophus body plan that are most directly relevant to the specific digestive requirements of a large cellulose digesting herbivore. The large, barrel-shaped torso of Parasaurolophus, whose specific dimensions relative to body length are greater than those of comparably sized carnivorous theropods of the same period, reflects the specific volumetric requirement of a digestive system whose hindgut fermentation chambers needed to be large enough to maintain the specific residence times of plant material required for effective microbial cellulose. Digestion by the symbiotic gut microorganisms that hadrosaurs, like all large plant-eating terrestrial vertebrates, depended on for the breakdown of the structural polysaccharides in their plant food. The specific metabolic advantages of hindgut fermentation for a large terrestrial herbivore like Parasaurolophus include the ability to process very large quantities of relatively low-quality plant material daily without the time. Constraints of ruminant forestomach fermentation, allowing the continuous throughput of plant material needed to sustain the high metabolic rates of an endothermic animal of 2 to 3 tons body mass. The specific relationship between the Parasaurolophus digestive system and the specific plant types most extensively consumed, assessed from the comparison with modern large hindgut fermenting herbivores, and from the specific implications of the Hadrosaur dental battery morphology for the specific food types most effectively processed, indicates a diet heavy in fibrous angiosperm and conifer foliage, whose specific cellulose and hemicellulose content was efficiently processed by the Hadrosaur hindgut fermentation system. The bone bed assemblages that include Parasaurolophus material, alongside the remains of other large dinosaurian species, provide the most complete pictures of the specific community composition of the Campanian faunas where this species occurred, and of the specific ecological relationships among the diverse large vertebrates that shared the coastal plain environments of the Campanian western interior. The Dinosaur Park Formation bone beds, some of the most extensive and most systematically studied bone accumulations from any Campanian formation, preserve the commingled remains of multiple dinosaurian species: hadrosaurs, ceratopsians, tyrannosaurids, dromaeosaurids, and various other groups. In specific depositional contexts, interpreted as mass mortality events or as accumulations of material transported to specific depositional loci by hydraulic processes following the deaths of the material. Individual animals. The specific representation of Parasaurolophus material in these multi-species bone bed assemblages, assessed from the proportion of Parasaurolophus identifiable elements relative to the total recovered Hadrosaur material, provides evidence for the relative abundance of Parasaurolophus in the living community and for the specific taphonomic processes that influence the differential preservation of different species and different skeletal elements in the process. Specific depositional environments where these assemblages were preserved. The ecological reconstruction of the Campanian coastal plain community that emerges from the integrated analysis of these bone bed assemblages and associated isolated skeletal material, the specific composition of the large herbivore guild, the specific composition of the predator guild, and the specific ecological relationships among these animals in the shared landscape provides the most complete available portrait of the specific community in which Parasaurolophus lived and in which the specific behavioral capabilities documented by the acoustic function of its crest were most directly ecologically relevant. The parallel evolution of elaborate cranial display structures in the ceratopsian dinosaurs that co-occurred with Parasaurolophus in the Campanian western interior provides an interesting comparative context for understanding the specific evolutionary forces that drove the elaboration of the Parasaurolophus crest within the Lambeosaurine hadrosaur lineage. The frills and horns of ceratopsians like Styracosaurus, Centrosaurus, and Triceratops represent a different category of cranial display structures. Bony extensions of the squamosal and parietal bones modified into elaborate frills, and the specific horn cores of the nasal and postorbital regions modified into pointed horns that performed both visual display functions and physical combat functions in the specific social ecology of ceratopsian populations. The comparison between the ceratopsian frill and horn system and the Parasaurolophus crest system is instructive. Both represent dramatic elaborations of specific cranial bones into display structures that grew to their maximum development at sexual maturity. Both show species-specific shapes that differ among contemporaneous species in the same formation, and both are most parsimoniously interpreted as products of sexual selection, acting on structures whose specific size and shape communicated individual quality and species identity to potential mates and competing conspecifics. The specific difference between the ceratopsian and hadrosaur cranial display systems, the visual and physical versus acoustic and visual modalities of the respective systems, reflects the specific anatomical raw material available for modification in each lineage and the specific communication channels most effective in the specific ecological contexts inhabited by each group, and illustrates the specific ways in which sexual selection operates on the available anatomical substrate of each lineage to produce the specific display structures that its particular ecological and behavioral context most favors. The specific environmental changes across the Campanian interval, documented from the stratigraphic record of the relevant formations and from the specific paleoclimate indicators preserved in those formations, provide the temporal context within which the specific evolutionary diversification of Parasaurolophus species is most fully understood. The Campanian of the Western Interior was a time of progressive faunal turnover driven by the specific combination of environmental changes associated with the fluctuating Western Interior seaway, the tectonic uplift of the Laramide orogeny that was progressively modifying the climate and topography of Western North America, and the broader global climate changes associated with the Cretaceous greenhouse climate system, whose specific dynamics drove long-term temperature and precipitation changes across the interval. The specific pattern of hadrosaur faunal turnover across the Campanian, documented from the stratigraphic distributions of different hadrosaur species in successive formations, shows a pattern of relatively rapid species replacement in which the specific hadrosaur fauna of each formation differed from that of the preceding and following formations in ways that reflect both the environmental changes driving the ecological conditions for different species and the specific evolutionary processes of speciation and extinction operating within the hadrosaur lineage. The specific position of the three Parasaurolophus species in this temporal and evolutionary context, Walkeri and Certocristatus, in the Middle Campanian and Tubocene, extending into the later Campanian of the New Mexico. Succession documents the specific temporal range of Ruli, the genus within the broader Campanian hadrosaur evolutionary history, and provides the temporal framework within which the specific evolutionary changes in crest geometry among the three species are most fully understood. The scientific study of Parasaurolophus has been sustained across more than a century by the specific combination of its anatomical distinctiveness, its geographic abundance in productive Campanian formations, and the specific biological questions that its crest anatomy raises about the behavioral ecology of non-avian dinosaurs in ways that generate productive scientific research programs and public engagement with paleontological science. The specific researchers who have contributed most substantially to the current scientific understanding of Parasaurolophus, from William Parkes, who established the basic anatomical description of the type species in 1922, through John Ostrom, who described the distinctive Certocristatus crest and analyzed its functional anatomy, through David Evans, Robert Rice, and their colleagues, who performed the quantitative acoustic modeling that established the resonant frequency of the Walkeri crest on a rigorous mathematical basis, represent a continuous tradition of scientific investigation that has progressively deepened and enriched the biological portrait of this extraordinary dinosaur. The ongoing contributions of the research programs based at the Royal Tyrrell Museum, the Natural History Museum of Utah, the New Mexico Museum of Natural History, and other institutions with important Parasaurolophus collections are continuing to advance the understanding of this species through the recovery and analysis of new specimens, the application of new analytical methods to existing material, and the development of new conceptual frameworks for interpreting the specific behavioral and ecological biology of this remarkable hadrosaur. The cumulative scientific achievement of this century-long research tradition is the 100 facts about Parasaurolophus that this documentary presents. 100 windows into the biology of the most acoustically remarkable non-avian dinosaur, documented in the fossil record of the Mesozoic world. The paleoecological reconstruction of the specific microhabitats most commonly occupied by Parasaurolophus within the broader Campanian coastal plain landscape, and the specific ways in which the habitat preferences of this species influenced its distribution within the forested, swampy, and open environments of the Campanian western interior, connects the anatomical and acoustic biology of Parasaurolophus to the specific landscape ecology of the environments where its populations lived. The specific sedimentological contexts of Parasaurolophus specimen occurrences in the Oldman and Dinosaur Park formations, predominantly in fine-grained floodplain and channel margin sediments rather than in coarser channel sands, and at elevations within the stratigraphic sequence consistent with the lower portions of the coastal plain rather than the more elevated inland environments, suggests a habitat preference for the moister, more vegetated lowland floodplain environments rather than the drier upland areas that were also inhabited by contemporaneous dinosaurian species. The specific vegetation of the Campanian lowland floodplain environment, reconstructed from the diverse plant fossil record of the Dinosaur Park formation, included abundant angiosperm, shrubs, and trees whose specific plant types, including early relatives of modern plane trees, magnolias, and various other broad-leaved angiosperms, provided the specific browse that the dental battery anatomy of Parasaurolophus was most effectively adapted to process. The specific low-frequency acoustic properties of the densely vegetated lowland environments where Parasaurolophus most commonly occurred, the high degree of vegetation scattering that reduces the effective range of high-frequency sounds while allowing relatively undisturbed propagation of the specific low-frequency sounds that the Parasaurolophus crest was adapted to produce, confirms the specific adaptive match between the acoustic properties of the crest vocalization system and the acoustic environment of the habitat that makes the acoustic communication function of the crest the most coherent and most completely supported functional hypothesis for this extraordinary anatomical structure. The global context of hadrosaur evolution and the specific position of the Lambeosaurine hadrosaurs, including Parasaurolophus, within the broader Late Cretaceous vertebrate radiation, provides the evolutionary biological framework within which the specific specializations of Parasaurolophus are most fully understood as products of the specific evolutionary history and ecological context of this lineage. The hadrosaurs, as a group, represent one of the most successful and most ecologically impactful large herbivore radiations of the Late Cretaceous, achieving extraordinary diversity and abundance in the northern hemisphere faunas of the Campanian and Maastrichtian, and contributing substantially to the specific structure of the terrestrial ecosystems that they inhabited. The Lambeosaurine clade within the hadrosaurs, whose hollow-crested members include not only Parasaurolophus but also Corythosaurus, Lambeosaurus, Hypacrosaurus, and various other species with their own distinctive crest shapes, represents a specific evolutionary radiation within the hadrosaur family, characterized by the development of the hollow crest acoustic communication system in diverse morphological implementations across the different species of the clade. The specific ecological success of the Lambeosaurines in the Campanian western interior, their high relative abundances in some formations, and their wide geographic distributions across the latitudinal extent of Laramidia, suggests that the hollow crest acoustic communication system conferred specific ecological advantages that enhanced the fitness of Lambeosaurine individuals relative to the competing Hadrosaur species that lacked hollow crests, and that these advantages were sufficient to support the substantial metabolic investment in crest construction across successive generations of the Lambeosaurine evolutionary history. The 100 facts about Parasaurolophus, the dinosaur that could sing, represent a scientific statement about one of the most extraordinary animals documented in the Mesozoic fossil record, an animal whose specific anatomical features, carefully analyzed with the most sophisticated methods of modern paleontological science, reveal a behavioral biology as complex and as specifically grounded in physical evidence as that documented for any non-avian dinosaurian species. The crest is in the museums. The internal anatomy has been revealed by computed tomographic scanning. The acoustic modeling calculations have been published in the peer-reviewed scientific literature. The comparative biological context of modern large vocal vertebrates has been systematically applied. The evolutionary biological theory of sexual selection and acoustic signaling has been brought to bear on the specific population dynamics of Campanian hadrosaur communities. And the result of all these specific scientific contributions is the 100 facts of this documentary. 100 specific statements about the anatomy, the acoustics, the ecology, the evolution, and the behavioral biology of the dinosaur that could sing, each statement grounded in specific physical evidence and specific analytical rigor, and together constituting the most complete and most scientifically grounded portrait of Parasaurolophus walkeri and its congeners that current paleontological knowledge makes possible. 100 facts. The crest. The sound. The Cretaceous forest, resonating with the calls of the most acoustically remarkable dinosaur that has ever lived. The specific relationship between Parasaurolophus and the diverse plant community of the Campanian coastal plain at the level of individual plant-dinosaur interactions. The specific plant species most regularly browsed. The specific plant parts most regularly consumed at different seasons and in different habitats, and the specific effects of Parasaurolophus feeding activity on the structure and composition of the plant communities it inhabited is one of the more ecologically detailed aspects of this species' biology, whose reconstruction requires the integration of dietary evidence from dentalware analysis, botanical evidence from the paleobotanical record, and ecological modeling from the comparison with modern large terrestrial herbivores in analogous plant communities. The specific plant assemblages of the Dinosaur Park Formation, documented from the diverse megafloral and palynological records of this formation, include a remarkable diversity of angiosperm species whose rapid diversification during the Cretaceous had produced by the Campanian, a plant community of very high species richness comparable to modern tropical and subtropical forests. The specific plant types represented in the Dinosaur Park Formation flora include early relatives of modern planes, laurels, magnolias, and diverse other broad-leaved angiosperms, alongside conifers of several families, ferns, horsetails, and various other non-flowering plant groups that contributed to the diverse vegetation mosaic of the coastal plain. The specific dietary selection behavior of Parasaurolophus within this diverse plant community, assessed from the comparison with modern, large browsing herbivores, whose food selection criteria provide the most relevant behavioral models, would have been directed toward the specific plant parts with the highest nutritional value per unit of processing effort. Young leaves with lower fiber and higher protein content, fruits and seeds with high caloric density, and specific plant species with particular secondary metabolite profiles that influenced palatability and digestibility for the specific microbiome of the Parasaurolophus hindgut fermentation system. The fossil record of Parasaurolophus teeth and the specific evidence these preserve for the specific feeding mechanics and food processing behaviors of this species at the level of individual tooth function and wear, provides the most direct available evidence for the specific way in which the Parasaurolophus dental battery actually worked during feeding, and for the specific food processing efficiency achievable with the Hadrosaur dental system. The Hadrosaur dental battery, of which the Parasaurolophus battery is a specific example, is one of the most remarkable dental systems in the history of vertebrate life. Hundreds of closely packed teeth of specific morphology, arranged in functional rows that provide a continuously self-renewing grinding surface, whose effectiveness for plant material processing remained constant throughout the life of the animal, as worn teeth were continuously replaced by new teeth growing from below. The specific tooth morphology of Parasaurolophus, with diamond-shaped teeth whose enamel is thicker on the lateral than the medial surface, creating a self-sharpening wear pattern as the softer dentine wears faster than the harder enamel, is optimized for maintaining a consistently sharp, cutting, and grinding edge across the full functional life of each individual tooth and across the full lifetime replacement sequence of the dental battery. The specific biomechanics of the Hadrosaur chewing stroke, reconstructed from the specific anatomy of the jaw joint and the specific orientations and estimated sizes of the adductor jaw muscles, produced a lateral translational motion in which the upper and lower tooth rows slid past each other in a specific direction, optimized for grinding plant material between the opposing tooth surfaces rather than the simple up-down crushing motion that the naive observer might expect from a large-jawed herbivore. The efficiency of this grinding motion for the specific plant types consumed by Parasaurolophus, assessed from the comparison with the dental mechanics of modern large herbivores that process comparable vegetation types, represents one of the specific, functional, anatomical achievements that made hadrosaurs among the most successful large herbivores of the late Cretaceous terrestrial fauna. The specific evolutionary pressures that maintained the elaborate Parasaurolophus crest across multiple generations of individuals, in the face of the substantial metabolic costs of crest construction and the specific physical vulnerabilities created by a large bony projection extending far behind the skull, document the specific fitness benefits that the crest conferred through both the acoustic communication function and the visual display function in the specific ecological and social context of Campanian hadrosaur populations. The metabolic cost of constructing the crest, estimated from the specific mass of additional bone tissue in the crest, relative to a flat-headed hadrosaur skull of comparable overall dimensions, represents a specific investment of calcium, phosphorus, protein, and metabolic energy that would only be evolutionarily maintained if the specific fitness benefits of crest elaboration exceeded this cost across the lifetime reproductive history of the individual. The specific fitness benefits of the acoustic communication function include the improved survival probability from more effective alarm communication in predator-rich environments, the improved reproductive success from more effective long-distance mate attraction and mate quality assessment in the breeding season, and the specific social dominance advantages of larger crested individuals in the competitive social interactions that determined access to the best foraging sites, the most desirable social positions within the group, and the highest quality mating partners. The cost-benefit analysis of the crest acoustic function in the specific ecological context of Campanian Parasaurolophus populations, the specific quantitative relationship between crest size, acoustic effectiveness, and the specific fitness outcomes in predation, avoidance, mate acquisition, and social dominance is one of the more quantitatively tractable aspects of Parasaurolophus evolutionary biology and represents a productive research direction for the integration of acoustic physics, ecological modeling, and evolutionary theory in the specific context of non-avian dinosaurian sexual selection. The endocranial anatomy of Parasaurolophus, revealed by the endocasts of the brain cavity prepared from skull material of this species and its close relatives, documents the specific neural organization of this hadrosaur and provides information about the relative development of different brain regions relevant to the specific behavioral capabilities, most important in the ecology and social biology of this species. The specific olfactory lobe proportions of the hadrosaur brain, assessed from the endocasts of the best preserved hadrosaur skull material, indicate a moderate degree of olfactory development, consistent with the use of chemical information in the social ecology of these animals, without the extreme olfactory specialization of some other dinosaurian groups. The optic lobe proportions of hadrosaur brains are relatively large, reflecting the importance of visual information in the ecology and social behavior of these animals, and consistent with the inference that the visual display function of the crest was a significant component of its total communicative function in Parasaurolophus social behavior. The cerebellum, whose specific proportions reflect the complexity of the motor coordination demands placed on the neural control system by the specific locomotor and behavioral repertoire of each species, shows proportions in hadrosaur endocasts consistent with the coordination demands of large-bodied bipedal and quadrupedal locomotion, and with the specific motor demands of the complex social behaviors, including the coordinated group movement of social herds, the specific postural displays associated with breeding season competition, and the specific fine motor control needed for selective plant browsing that the ecology of Parasaurolophus required. The overall brain-to-body size ratio of Parasaurolophus, estimated from the brain cavity volume in well-preserved skull specimens and from the body mass estimates for this species, falls within the range documented for other large ornithischian dinosaurs and is consistent with the cognitive complexity expected for a large social herbivore with elaborate acoustic communication capabilities. The specific role of Parasaurolophus in the Campanian food web, as both a consumer of primary producers and a prey item of large theropod predators, positions this species at a specific node in the energy flow network of the coastal plain ecosystem, whose specific dynamics influenced both the structure of the plant community and the population dynamics of the predator guild. The consumption of large quantities of Campanian vegetation by Parasaurolophus populations, the specific quantities estimated from the body mass and metabolic rate of adult individuals multiplied by the estimated population density, would have created specific patterns of plant community disturbance, selective browsing, and nutrient cycling, whose effects on the vegetation mosaic of the coastal plain were comparable in scale and ecological significance to the effects of modern large browsing herbivores on the plant communities they inhabit. The contribution of Parasaurolophus individuals to the diet of the large tyrannosaurid predators of the Campanian, particularly Gorgosaurus libratus in the Alberta fauna and Daspletosaurus horneri in the Montana fauna, is documented by the tooth marks of large theropod teeth on hadrosaur bone material from relevant formations, and by the specific abundance of hadrosaur bone relative to theropod bone in the fossil record, which implies that hadrosaurs, including Parasaurolophus, constituted a substantial fraction of the prey base, sustaining the Campanian tyrannosaurid predator guild. The specific importance of effective alarm communication in the ecology of Parasaurolophus, the specific benefits of detecting and communicating the approach of Gorgosaurus before it had achieved the close proximity needed for a successful ambush attack is most directly quantifiable in the context of the specific hunting ecology of the relevant predator species, whose specific hunting strategies and success rates determined the specific mortality risk to Parasaurolophus individuals, and therefore the specific fitness benefit of the acoustic alarm communication function of the crest. The recovery of juvenile Parasaurolophus specimens, including the remarkable juvenile walkery skull described from the Kaiparowitz Formation of Utah by Terry Gates and colleagues, has provided critical information about the specific developmental biology of crest growth in this species and about the specific acoustic capabilities available to juveniles at different growth stages that complemented the better documented acoustic capabilities of the fully developed adult crest. The juvenile skull, described by Gates and colleagues, representing an individual estimated at approximately 25 to 30% of adult body length based on the specific dimensions of the skull relative to adult skull measurements, preserves the crest at an early developmental stage where it is substantially shorter and less elaborated than the adult crest, but already shows the specific directional architecture, the posterior extension of the crest behind. The skull plane that characterizes the adult walkery crest morphology, the specific acoustic properties of the juvenile crest, modeled from the specific internal passage geometry of the juvenile skull, using the same mathematical methods applied to the adult TMP specimen, produce resonant frequency estimates substantially higher than the adult fundamental frequency, reflecting the shorter total passage length in the less developed juvenile crest. The behavioral implications of this juvenile acoustic difference are that juvenile Parasaurolophus individuals communicated with different fundamental frequencies than adults, creating a specific age-related acoustic signal that adult group members could potentially use to assess the developmental stage of juveniles in the social group, and that juveniles could use to signal their age and developmental status to attending adults. The progressive deepening of the fundamental resonant frequency as the crest grew through juvenile development provides a specific acoustic record of individual developmental history that may have contributed to the specific parent-offspring communication and social rank assessment functions of vocal communication in Parasaurolophus social groups. The brain lateralization of Parasaurolophus, the specific degree to which the left and right cerebral hemispheres of this hadrosaur performed different cognitive functions in a manner comparable to the hemisphere specialization, documented in modern vertebrates, is one of the more speculative but scientifically interesting aspects of the neural biology of this species that the comparative neuroscience of modern archosaurs allows to be partially approached through phylogenetic inference. Modern birds show strongly lateralized brain function, with the left hemisphere specialized for the processing of species-specific vocalizations, the learning of song, and the production of learned vocal sequences, while the right hemisphere is more involved in the processing of novel stimuli and the spatial mapping of the environment. Modern crocodilians also show evidence for neural lateralization in some cognitive functions, and the evolutionary conservation of lateralization as a general organizational feature of the archosaur brain provides a basis for inferring that some degree of neural lateralization was present in non-avian dinosaurs, including Parasaurolophus. The specific acoustic behavior associated with the Parasaurolophus crest, the production and recognition of specific vocalization types in specific behavioral contexts, would have been among the cognitive functions most likely to show hemisphere specialization comparable to the vocal processing lateralization of modern birds, because the specific processing requirements of complex acoustic communication are among the cognitive demands most consistently associated with hemisphere specialization in modern vocal vertebrates. The inference of hemisphere specialization for acoustic processing in Parasaurolophus is speculative at the level of the specific details of hemispheric organization, but it is grounded in the evolutionary conservation of lateralization as a neural organizational feature across the Archosaur lineage and in the specific cognitive demands of the sophisticated acoustic communication system that the crest anatomy documents for this species. The specific research programs currently advancing the scientific understanding of Parasaurolophus and the specific discoveries and analytical advances most likely to most significantly expand the known biology of this species in the coming years of investigation provide a prospective view of the directions in which the 100 facts of this documentary will be extended and enriched by the continuing work of the paleontological research community. The systematic excavation of Campanian formations across the Kaiparowits Plateau of Utah, one of the most productive currently active fieldwork programs for Campanian Hadrosaur material, is progressively recovering new Parasaurolophus specimens from the Certicristatus-bearing Kaiparowits formation, whose specific anatomical completeness and geological context is extending the known anatomy and paleoecology of this Utah species beyond what the earlier described specimens allow. The application of high-resolution microcomputed tomographic scanning to the internal anatomy of existing Parasaurolophus skull specimens, using scanning systems of higher resolution than those used in the initial acoustic modeling study, is progressively refining the acoustic modeling calculations by providing more precisely characterized passage geometries, whose specific cross-sectional dimensions and passage wall curvatures can be measured with greater accuracy than earlier scanning allowed. The development of digital acoustic simulation methods capable of modeling the complete three-dimensional acoustic behavior of complex passage geometries, including the specific reflections, diffractions, and wave interference effects that the simplified one-dimensional tube model used in the initial acoustic modeling could not fully capture, will allow the production of more accurate and more complete acoustic models of the Parasaurolophus crest function, whose results will provide a more complete characterization of the specific sounds that the living animal was capable of producing. Each of these advancing research programs will contribute new facts to the scientific understanding of Parasaurolophus, adding new dimensions to the biological portrait assembled in the 100 facts of this documentary, and progressively building toward the complete understanding of this extraordinary acoustic dinosaur that the physical evidence preserved in the fossil record makes possible. The paleoclimate context of the Campanian western interior and the specific seasonal and annual climate patterns experienced by Parasaurolophus populations in the specific formations where this species occurred is relevant to understanding both the specific ecological conditions that shaped the behavioral ecology of this species and the specific phenological patterns of the seasonal behavioral cycle, the timing of breeding, the timing of migrations between seasonal foraging ranges, and the specific seasonal pattern of acoustic display activity that are most likely to have characterized the annual behavioral cycle of Campanian Parasaurolophus populations. The paleoclimate reconstruction of the Campanian western interior, based on the specific stable isotope compositions of pedogenic carbonates and freshwater mollusk shells from the relevant formations, and on the specific paleobotanical evidence for vegetation types and their climatic requirements, indicates a warm, seasonally wet climate with mean annual temperatures substantially above modern values and with a specific seasonal precipitation cycle that produced the wet and dry seasons documented in the sedimentological record of the coastal plain formations. The specific behavioral responses of Parasaurolophus to this seasonal climate cycle would have included the specific timing of breeding season acoustic displays to coincide with the specific season of maximum resource availability. The specific migration patterns between wet season and dry season foraging ranges, and the specific aggregation and dispersal patterns of social groups in response to the seasonal changes in resource distribution across the coastal plain landscape. The acoustic display activity of breeding season male Parasaurolophus concentrated in the specific weeks of the year when females were most receptive and when the acoustic properties of the environment, the specific temperature and humidity conditions that affect sound propagation, were most favorable for the long-distance communication that the acoustic function of the crest was adapted to achieve, would have produced the most intensive and most acoustically prominent period in the Campanian coastal plain soundscape of any year. The specific biological event whose acoustic signature resonated through the Cretaceous forest with the power and carrying distance of the evolved Parasaurolophus acoustic system. The 100 facts about Parasaurolophus, the dinosaur that could sing, have been assembled from the physical evidence of fossilized skulls in museum collections around the world, from the specific mathematical calculations of acoustic physicists who applied the principles of resonance to the internal geometry of those skulls, from the comparative biology of modern large vocal vertebrates whose acoustic communication systems provide the most relevant biological models for the specific acoustic behavior of this Cretaceous hadrosaur, and from the evolutionary biological theory of sexual selection and acoustic signaling that provides the interpretive framework within which the specific crest, anatomy, and acoustic properties of Parasaurolophus are most fully understood. Each of these 100 facts represents a specific advance in the scientific understanding of this extraordinary animal, and together they constitute the most complete and most rigorously evidence-based portrait of Parasaurolophus biology that a century of scientific investigation has produced. The skulls are in the museums. The calculations are in the literature. The comparative biology is documented in the modern world. The evolutionary theory is grounded in more than a century of field and laboratory research on the specific mechanisms of natural selection and sexual selection in diverse animal populations. And the specific convergence of all these lines of evidence on the specific biological picture of a large, socially sophisticated, acoustically complex hadrosaur whose low-frequency vocalizations resonated through the Cretaceous forests of western North America with a carrying distance and acoustic power unmatched by any contemporaneous animal. This convergence is the specific scientific achievement that the 100 facts of this documentary celebrate and communicate. 100 facts about the dinosaur that could sing. The most acoustically remarkable non-avian dinosaur, the Cretaceous soundmaker. The extraordinary evolutionary product of 75 million years of vertebrate acoustic. Evolution preserved in the hollow bones of the most distinctive hadrosaur crest in the fossil record. The specific significance of Parasaurolophus in the history of ideas about dinosaurian behavior, its role in transforming the scientific understanding of non-avian dinosaurs from behaviorally simple reptilian automata, acoustically and socially sophisticated animals with complex behavioral lives comparable to those of modern large vertebrates, is one of the more important contributions of the study of this species to the broader field of carminal, vertebrate paleontology, and to the public understanding of prehistoric life. The initial description of Parasaurolophus by Parkes in 1922, while establishing the basic anatomical parameters of the species, did not provide a compelling functional interpretation of the crest that connected the specific anatomy to specific behaviors, leaving the crest as an anatomical curiosity without a clear biological meaning. The successive functional hypotheses proposed across the decades of the 20th century, the snorkel hypothesis, the olfactory enhancement hypothesis, the thermoregulatory hypothesis, the species recognition hypothesis, and ultimately the acoustic communication hypothesis in its progressively more rigorously quantified forms, represent a century of scientific engagement with the specific biological puzzle of the crest function, whose progressive resolution has transformed the understanding of Parasaurolophus from an anatomically distinctive but behaviorally uninterpreted dinosaur into one of the most behaviorally specific and most completely understood non-avian, dinosaurian species. The broader impact of this transformation in understanding on the scientific picture of dinosaurian behavior, the recognition that non-avian dinosaurs were capable of sophisticated acoustic communication comparable to that of modern large birds and mammals, has contributed substantially to the modern understanding of dinosaurian behavioral complexity that the public encounters in museums, books, and other popular media about prehistoric life, and that represents one of the most significant intellectual achievements of 20th and 21st century paleontological science. The comparison between the acoustic communication system of Parasaurolophus and the acoustic communication systems of modern large birds that use resonating anatomical structures for low-frequency sound production, the whooping crane, the capercaillie, the various tropical birds with elongated or coiled tracheas, illustrates the specific evolutionary convergence of diverse lineages on the same fundamental acoustic solution to the communication challenge of long distance: sound propagation in forested environments. The whooping crane, Grus americana, produces low-frequency calls in the range of approximately 200 to 400 Hz, using its elongated coiled trachea, which adds additional passage length to the standard bird trachea and thereby lowers the resonant frequency of the vocal system below what the unmodified bird trachea of a comparable-sized animal would produce. The specific parallels between the whooping crane tracheal resonator and the Parasaurolophus nasal passage resonator both involve the elongation of a passage system beyond its ancestral length to lower the resonant frequency of the acoustic system for specific ecological communication purposes, are among the most direct functional analogies available for the Parasaurolophus crest acoustic system and provide a specific modern biological validation of the physical principles invoked in the acoustic modeling calculations. The specific differences between the two systems, the whooping crane resonator operating in the trachea and the Parasaurolophus resonator operating in the nasal passages, reflect the different anatomical substrates available for modification in each lineage and the different specific evolutionary starting points from which the resonating structures were derived in each case. The convergent evolutionary logic connecting these two very different solutions to the same fundamental communication problem, the amplification of low-frequency sounds for long-distance propagation in forested environments, is one of the most compelling illustrations of the predictability of evolution under specific ecological selection pressures and provides one of the most powerful arguments for the specific acoustic function of this. The Parasaurolophus crest from the comparative biology of modern large vocal vertebrates. The final assessment of the 100 facts about Parasaurolophus, the dinosaur that could sing, recognizes that the scientific achievement of understanding this animal well enough to reconstruct its specific vocalizations from the physical evidence of its preserved skull anatomy represents one of the most extraordinary intellectual achievements in the history of paleontological science. The recovery of the sounds of a specific animal that has been extinct for 75 million years from the mathematical analysis of the specific anatomical structures that produced those sounds. The skulls of Parasaurolophus walkeri preserved in the rock of the Oldman Formation and the Dinosaur Park Formation and the Kaiparowitz Formation, are the physical instruments from which the specific acoustic properties of the living animal's crest have been calculated, and the specific resonant frequencies predicted from those calculations are the closest available approximation to the actual sounds that Parasaurolophus made in the Cretaceous forests of western North America. The emotional resonance of this achievement, the recovery of the voice of an extinct animal from the geometry of its hollow bones, is one of the most powerful examples of what paleontological science can achieve at the intersection of physical evidence, mathematical analysis, and biological understanding. 100 facts about Parasaurolophus: the anatomy, the acoustics, the ecology, the evolution, the song of the Cretaceous. The most extraordinary acoustic story in the history of vertebrate paleontology, recovered from the bones of the most distinctive Hadrosaur crest in the fossil record, and offered to the world that the evolutionary legacy of that ancient singer has helped to build. The specific isotopic evidence for the geographic movements of Parasaurolophus populations across the Campanian landscape, and the degree to which seasonal migrations between different environmental zones were a feature of the annual behavioral cycle of this species, is beginning to be addressed through the stable isotope analysis of Parasaurolophus tooth enamel from specific formations where the relevant isotopic reference framework has been established. The oxygen isotope composition of successive tooth enamel growth layers in Hadrosaur teeth, analyzed by Fricker and colleagues in pioneering studies on 2-medicine formation material and progressively extended to other formations and other Hadrosaur species, records the specific isotopic composition of the water consumed during each period of tooth formation, and thereby documents the specific geographic water sources used by individual animals during successive phases of their annual movement. Cycles. The application of this isotopic approach to Parasaurolophus tooth enamel from the Dinosaur Park Formation is one of the specific research programs whose results will most directly address the question of whether Parasaurolophus populations performed seasonal migrations comparable to those inferred for Maiasaura in the 2-medicine formation, or remained resident year-round in specific portions of the coastal plain landscape. The acoustic significance of seasonal migration for Parasaurolophus would lie in the specific contexts in which acoustic communication was most valuable across the annual cycle, the migration itself, during which low-frequency contact calls could maintain group cohesion across the visual screen of forested terrain, and the breeding season, during which the acoustic display function of the adult male crest would have been most intensively deployed in the specific social context of mate competition and mate attraction. The integration of isotopic migration evidence with the acoustic biology of the crest would produce a more complete behavioral ecological picture of Parasaurolophus than either line of evidence alone can provide. The Parasaurolophus material from the Kirtland Formation of New Mexico, representing the species Tubicen, provides evidence for the southern extension of the Parasaurolophus geographic range into the warmer, drier environments of the southern Laramidian coastal plain, and for the specific environmental conditions that characterize the habitats of this southern coastal species relative to the more northern distributions of Walkery. The Kirtland Formation, deposited approximately 75 to 73 million years ago in a fluvial deltaic environment at the southern end of the Campanian Western Interior Seaway, preserves a dinosaurian fauna, somewhat different in specific taxonomic composition from the Alberta Campanian faunas, while sharing the general ecological character of a large-bodied Hadrosaur and ceratopsian-dominated herbivore community with associated large theropod predators. The specific crest morphology of Tubicen, with its elongated crest tube, showing somewhat different curvature from the walkery crest, while achieving a comparable overall length, produces acoustic resonance properties broadly similar to those of walkery in frequency range, while differing in specific harmonic structure and modulation characteristics in ways that the specific passage geometry differences between the pasts. Two species determine the geographic separation between walkery in Alberta and Tubicin in New Mexico, spanning several hundred kilometers of Laramidian coastal plain, along which intermediate populations may have existed but are currently undocumented, raises the specific biogeographic question of whether these two species maintained gene flow across the intervening distance, or were genetically isolated populations that had differentiated in allopatry during the specific biogeographic events of the Campanian interval. The resolution of this question awaits the recovery of Parasaurolophus material from the stratigraphic intervals and geographic regions intermediate between the known walkery and Tubicine occurrences and the specific phylogenetic genetic analysis of the morphological differences between these species in the context of the broader Hadrosaur phylogenetic framework. The growth series of Parasaurolophus available from the accumulation of specimens across multiple formations and collection programs from the small juvenile skull described from the Kaiparowitz Formation through the subadult and adult skulls of walkery and the other species, allows the reconstruction of the specific developmental trajectory of crest growth from its earliest expression through its full adult form and the specific changes in body proportion and skeletal anatomy that accompanied the growth of the body crest to its adult dimensions. The specific allometric relationship between crest length and skull length in Parasaurolophus across the available growth series, the rate at which crest length increased relative to skull length as individuals grew from juvenile to adult, documents the specific positive allometry of crest growth that produced the disproportionately larger crest of adult individuals relative to small juveniles whose crests were proportionally much smaller relative to their overall skull size. This positive allometry of crest growth is the anatomical signature of accelerated growth of the sexually selected display structure during the specific developmental window of subadult growth when the crest was undergoing its most rapid elaboration, and it is directly comparable to the positive allometry of sexually selected structures documented in modern vertebrates, where the development of secondary sexual characters accelerates relative to overall body growth during the specific developmental period immediately preceding sexual maturity. The specific developmental biology of Parasaurolophus crest growth therefore provides a specific vertebrate paleontological example of the positive allometric growth of a sexually selected structure that connects the evolutionary biology of display structure development in this extinct hadrosaur to the broader comparative developmental biology of secondary sexual character growth in modern vertebrates, and adds an important evolutionary biological dimension to the purely acoustic functional analysis of the crest system. The fossil preservation of soft tissue impressions associated with some hadrosaur specimens, including skin impressions that document the specific scale and tubercle patterns of the external integument of these animals, provides visual information about the specific external appearance of hadrosaurs that the skeletal anatomy alone cannot supply, and that is directly relevant to understanding the specific visual ecology of Parasaurolophus social behavior. The skin impressions known from various hadrosaur specimens document a specific pattern of small polygonal scales arranged in a mosaic pattern across most of the body surface, with larger tubercle-like scales in specific regions of the body that may have served specific functional or display purposes in the living animals. The specific external surface texture of the Parasaurolophus crest, while not directly documented from skin impressions of this specific region in known Parasaurolophus specimens, can be partially inferred from the general Hadrosaur skin pattern and from the specific implications of the vascular anatomy of the crest outer wall, the blood vessel channels visible in the bony wall of the crest in well-preserved specimens, for the specific thickness and texture of the overlying skin surface, the specific coloration pattern of the Parasaurolophus body, whose visual contribution to the species-specific appearance of individual animals would have complemented the acoustic species recognition function of the crest in the specific visual ecology of Campanian social interactions, is the aspect of external appearance most relevant to the understanding of visual communication in this species, and the one most directly accessible to inference from the evolutionary principles of visual signaling in social vertebrates, with full-color tetrachromatic vision comparable to the color vision system shared by all archosaurs, including Parasaurolophus and its contemporaries. The neurobiological basis of acoustic communication in hadrosaurs and the specific neural circuits responsible for the generation, modulation, and recognition of species-specific vocalizations in animals with acoustic communication systems comparable to that inferred for Parasaurolophus is one of the more speculative but scientifically grounded aspects of the behavioral biology of this species, whose inference from the comparative neuroscience of modern archosaurs provides specific biological context. Modern songbirds, whose learned vocal communication systems are among the most completely understood acoustic systems in vertebrate neuroscience, possess specific neural circuits in the telencephalon, the HVC, RA, and related nuclei of the song system, dedicated to the learning, production, and recognition of species-specific vocalizations. Modern crocodilians, while producing simpler and more stereotyped vocalizations than birds, possess the neural circuitry for producing and recognizing specific vocalization patterns in the social and reproductive contexts where acoustic communication is most important in their behavioral ecology. The inference of comparable neural circuitry for vocal production and recognition in Parasaurolophus, while speculative at the level of specific neural anatomy, is supported by the evolutionary conservation of the general archosaur neural organization across both living archosaur lineages and by the specific demands of the acoustic communication system documented by the crest anatomy, which require at minimum the neural capability to generate modulated low-frequency vocalizations and to respond differentially to the vocalizations of conspecifics in different behavioral contexts. The specific complexity of the vocal repertoire achievable with the Parasaurolophus crest anatomy, estimated from the range of modulation possible in the sound source combined with the filtering effects of the specific resonant properties of the passage system, would have required a vocal production neural system capable of generating diverse modulation patterns in the source signal, adding a specific neural complexity requirement to the already substantial anatomical complexity of the crest vocalization system. The reconstruction of the specific soundscape of the Campanian coastal plain ecosystem inhabited by Parasaurolophus, the complete acoustic environment, including the sounds of all the biological and physical sources that contributed to the ambient noise field within which Parasaurolophus vocalizations were transmitted and received, provides the most complete ecological context for understanding the specific signal detection challenges and the specific acoustic adaptations of the Parasaurolophus communication system. The biological components of the Campanian acoustic environment would have included the vocalizations of the diverse bird fauna documented from Campanian formations across North America, whose acoustic contributions to the ambient soundscape were already substantial by the Campanian. The sounds of the diverse insect fauna, whose stridulation and wing buzzing contributed to the high-frequency ambient noise of the forested environment. The vocalizations of other large vertebrates, including the theropod predators, the ceratopsians, and the ankylosaurs, whose specific acoustic behaviors are less well documented than those of hadrosaurs, but whose presence as large, physiologically active animals implies some level of acoustic activity, and the specific ambient sounds of the coastal environment, including the wind in the Cretaceous forests, the sounds of river channels and coastal wetlands, and the specific acoustic features of the western interior seaway shoreline. The physical components of the soundscape would have included the specific, frequency-dependent attenuation characteristics of the forested environment, the specific reflection and diffraction effects of the complex topography of the coastal plain, and the specific temperature and humidity gradients that affected the propagation of different sound frequencies across different seasons and different times of day. Understanding the specific signal-to-noise challenges faced by Parasaurolophus, communicating within this complex acoustic environment, is one of the most ecologically complete analytical approaches to the acoustic biology of this species and provides a specific environmental context for the evolutionary optimization of the crest acoustic system that the physical analysis of the crest resonance properties alone cannot supply. The specific evidence from ichnological studies, the study of the trace fossils including footprints and trackways of Campanian dinosaurs, for the specific locomotor behavior and social movement patterns of hadrosaur groups provides a supplementary line of evidence for the specific aspects of Parasaurolophus social ecology that the skeletal fossil record cannot directly document. The hadrosaur trackways documented from Campanian formations across western North America, including the diverse ichnological records from the Dinosaur Park Formation and equivalent formations, preserve the specific foot strike patterns, stride lengths, step widths, and relative orientations of individual footprints that document the specific gait kinematics of hadrosaurs moving across specific substrates in specific locomotor contexts. The specific occurrence of multiple parallel trackways of similar size and similar direction at some hadrosaur trackway localities, interpreted as records of individuals of the same species, moving in the same direction at approximately the same time, provides direct ichnological evidence for the gregarious movement behavior of hadrosaur groups and supports the inference from skeletal bone bed evidence that hadrosaurs, including Parasaurolophus, traveled in social groups rather than as isolated individuals. The specific relationship between the acoustic communication function of the Parasaurolophus crest and the specific gregarious movement behavior documented in hadrosaur trackway assemblages is direct. The maintenance of social cohesion during group movement across forested terrain, where visual contact among group members is intermittent and frequently lost, is one of the primary behavioral contexts in which acoustic contact calls provide the most immediate and most substantial survival benefit, making the long-distance contact call function of the crest the single most directly relevant behavioral application for the specific locomotor and social ecology documented in hadrosaur trackway assemblages. The paleomagnetic record of the Campanian western interior and the specific implications of Campanian paleolatitude determinations for the specific solar radiation regime and seasonal light cycle experienced by Parasaurolophus populations at different latitudes across the Laramidian coastal plain provides an astronomical and climatological dimension of the paleoecological context of this species that is relevant to the specific phenological timing of breeding season behaviors. The specific paleolatitudes of the Campanian hadrosaur-bearing formations of Alberta, Montana, Utah, and New Mexico span a latitudinal range from approximately 52 to 42 degrees north paleolatitude, encompassing a substantial gradient in the specific seasonal light cycle and solar radiation regime that would have produced different annual patterns of resource availability and behavioral phenology at different locations within the side. Geographic range of Parasaurolophus. The breeding season of Parasaurolophus, whose specific timing would have been calibrated to the specific photoperiodic and temperature signals of each population's specific paleolatitude, would have occurred at different calendar times of year in different parts of the range and with different degrees of seasonal contrast in day length and resource availability between the breeding and non-breeding seasons. The specific implications of this paleolatitudinal variation for the acoustic display biology of Parasaurolophus, particularly the specific seasonal timing and duration of the period of most intensive crest acoustic display by adult males in the breeding season, are among the ecological dimensions of Parasaurolophus acoustic biology, whose reconstruction from the available paleoecological evidence is progressively becoming more tractable as the breeding adult. Specific paleoclimate and paleoenvironmental reconstructions of the relevant formations become more complete and more quantitatively grounded in specific physical and chemical evidence from the formations themselves. The evolutionary relationship between Parasaurolophus and the closely related Tyrannosaurus guianensis from the late Cretaceous of China, a Lambeosaurine hadrosaur whose crest anatomy bears specific similarities to that of Parasaurolophus and whose geographic occurrence in Asia documents the specific biogeographic connections between the North American and Asian Campanian Maastrichtian hadrosaur faunas, provides important phylogenetic and biogeographic context for understanding the evolutionary history of the Parasaurolophus crest type within the global Lambeosaurine radiation. Coronosaurus, described by Godefroy and colleagues from the Maastrichtian Yuliangze Formation of Heilongjiang Province, China, bears a posteriorly directed hollow crest, similar in general architecture to that of Parasaurolophus walkeri, suggesting either a close phylogenetic relationship between the two genera or convergent evolution of the specific posteriorly directed crest type in response to similar selective pressures in the specific ecological contexts of the North American Campanian and Asian Maastrichtian faunas. The specific acoustic properties of the Tyrannosaurus crest, which have not yet been as thoroughly analyzed as those of Parasaurolophus, but whose passage geometry is broadly comparable to that of Parasaurolophus based on the available skeletal descriptions, would be expected to produce resonant frequencies broadly similar to those of Parasaurolophus walkeri if the passage length in Tyrannosaurus is comparable to that of walkeri. The biogeographic implications of the Parasaurolophus Tyrannosaurus similarity for the specific dispersal history of the long-crested Lambeosaurine lineage between North America and Asia during the late Cretaceous add an important intercontinental dimension to the evolutionary history of the Parasaurolophus crest type and connect the specific acoustic biology of this North American hadrosaur to the broader story of late Cretaceous biogeographic exchange between Laramedia and Asia through the Beringian land connection. The scientific communication of Parasaurolophus research to the public, and the specific ways in which the acoustic modeling results have been translated from the technical language of the peer-reviewed scientific literature into accessible explanations for non-specialist audiences, represents one of the more successful examples of the public communication of paleontological science in recent decades. The production of computer-generated audio simulations of the predicted Parasaurolophus crest vocalizations, derived from the specific acoustic modeling calculations of Evans and colleagues and made available through museum exhibits, online platforms, and popular science media, has given the general public direct auditory access to the predicted sounds of this Cretaceous dinosaur in a way that text descriptions alone could never convey. The specific emotional impact of hearing a scientifically grounded simulation of the Parasaurolophus vocalization, the deep, resonant, horn-like sound that the acoustic modeling predicts for the fundamental frequency of the walkery crest, is one of the most powerful experiences available in modern natural history communication and represents a uniquely direct connection between the science of the fossil record and the sensory experience of the living animal that science is attempting to reconstruct. The progressive refinement of these audio simulations, as the acoustic modeling calculations are updated with more precisely characterized passage geometries and more sophisticated mathematical models of the complete three-dimensional acoustic behavior of the crest passage system, will produce increasingly accurate representations of the specific sounds that living Parasaurolophus individuals produced, bringing the scientific understanding of this extraordinary acoustic dinosaur closer to the sensory reality of the animal's actual vocalizations in the Cretaceous forests of Western North America. The communication of this scientific achievement to the public through diverse media is one of the most effective demonstrations available of the specific power of paleontological science to recover specific biological truths about the natural world of the deep geological past. The relationship between the acoustic communication system of Parasaurolophus and the acoustic ecology of the Western Interior Seaway itself, whose coastal environment adjacent to the Hadrosaur-inhabited coastal plain would have included a diverse array of marine animals with their own acoustic biology, provides an interesting broader ecological context for the specific acoustic environment of Campanian North America. The Western Interior Seaway, at its greatest extent, a shallow tropical to subtropical sea, stretching from the Arctic to the Gulf of Mexico, and teeming with marine life including mosasaurs, plesiosaurs, fish, and diverse invertebrates, would have contributed the specific sounds of the marine environment to the acoustic landscape of the adjacent coastal areas where Parasaurolophus populations lived. The sounds of wave action, of marine mammals equivalent mosasaurs, whose acoustic biology was likely comparable to that of modern aquatic reptiles, and of the diverse seabird fauna documented from Campanian formations, alongside the marine vertebrate fauna, would have contributed a specific coastal acoustic ambience to the environments immediately adjacent to the seaway shoreline. The specific acoustic interaction between the Parasaurolophus crest vocalizations produced on the coastal plain and the acoustic environment of the adjacent seaway, whether seaway-generated noise interfered with the effective range of Parasaurolophus acoustic communication in coastal habitats, or whether the specific atmospheric and acoustic properties of coastal environments enhanced the propagation of the low-frequency crest vocalizations, is an aspect of the coastal acoustic ecology of the Campanian that the integration of physical acoustic modeling with paleo-environmental reconstruction could progressively address. The broader acoustic ecology of the Campanian coastal plain, at the interface between the terrestrial acoustic environment of the Hadrosaur-inhabited floodplains and the marine acoustic environment of the adjacent seaway, is one of the more complex and more ecologically complete contexts in which the specific acoustic biology of Parasaurolophus was deployed across the 75 million years ago soundscape of the Western Interior. The 100 facts about Parasaurolophus, the dinosaur that could sing, represent the most comprehensive and most rigorously evidence-based account of the biology of this extraordinary Cretaceous hadrosaur currently available from the accumulated scientific investigation of a century of paleontological research. Each fact is a window into a specific aspect of the biology of an animal whose preserved bones and their internal anatomy have allowed the recovery of specific biological truths about the appearance, behavior, ecology, and evolutionary history of one of the most acoustically remarkable vertebrates in the history of life. The scientific methods that produce these facts, the morphological analysis of fossil skulls, the computed tomographic imaging of internal crest anatomy, the mathematical modeling of acoustic resonance, the bone histological analysis of growth rates, the stable isotope chemistry of paleo-environmental reconstruction, the phylogenetic analysis of evolutionary relationships are the most sophisticated methods that modern paleontological science has available, and their application to the specific research questions of Parasaurolophus biology has produced a level of biological understanding of this extinct animal that would have been unimaginable to the paleontologists of earlier generations. The physical evidence on which these facts are based, the skulls in the museum collections, the scan data in the digital archives, the histological sections in the laboratory collections, is permanent, accessible, and available for the continuing analysis of current and future researchers whose work will add new facts to the 100 presented here. 100 facts about Parasaurolophus, the dinosaur that could sing, the hollow bones, the resonating passages, the predicted frequencies, the Cretaceous song, the most acoustically complete portrait of any non-avian dinosaur that the science of paleontology has produced. The legacy of Parasaurolophus for the science of paleontology extends beyond the specific biological facts about this species to the broader methodological contributions that the acoustic analysis of the crest has made to the field of paleontological behavioral reconstruction. The quantitative acoustic modeling of fossil anatomical structures, applied first and most completely to the Parasaurolophus crest by Evans, Rice, and colleagues, represents a specific methodological advance that demonstrated for the first time in vertebrate paleontology that the specific behavioral capability of sound production could be quantitatively reconstructed from the physical anatomy of a fossil, with a degree of precision and mathematical rigor comparable to that achievable in the biomechanical analysis of locomotor systems or the functional analysis of dental systems. The specific methodological template established in the Parasaurolophus acoustic modeling study, the computed tomographic characterization of the relevant anatomical geometry, the mathematical application of the relevant physical principles to the documented geometry, and the specific comparison of the model predictions with the acoustic behavior of modern animals with comparable anatomical systems, has been applied to other fossil acoustic structures and will continue to be applied to new fossil material as the relevant methods become more widely known and more computationally accessible across the broader paleontological research community. The methodological legacy of Parasaurolophus acoustic research is therefore a contribution to the general capability of paleontological science to reconstruct specific behavioral capabilities from anatomical evidence, extending the range of behaviors accessible to scientific reconstruction through the fossil record, and contributing to the progressive development of behavioral paleontology as a rigorous scientific discipline whose specific methods and specific conclusions are increasingly grounded in quantitative physical and biological analysis rather than in qualitative speculation. 100 facts: the dinosaur that could sing, the science that heard its song, the specific visual anatomy of Parasaurolophus, and the degree to which the optical system of this hadrosaur was adapted for the specific visual demands of its ecological lifestyle and social behavior, provides an important sensory biological complement to the acoustic communication biology of the crest. The large eye orbits documented in Parasaurolophus skull material, whose absolute dimensions are consistent with eyes of substantial size relative to the skull in this species, imply a visual system capable of the specific combination of resolution, sensitivity, and color discrimination that would have been required for the specific visual tasks most important in Parasaurolophus: ecology and behavior. The specific visual demands of foraging in the complex vegetation of the Campanian coastal plain, detecting specific plant types at the distances relevant to food selection, discriminating ripe from unripe fruits by color, and navigating the three-dimensional structure of the forested environment would have required a visual system with both good spatial resolution for fine detail detection and the specific color discrimination capability of tetrachromatic vision for the color-based food selection tasks that were most relevant to the specific diet of this large herbivore. The specific visual demands of social communication in Parasaurolophus groups, detecting the specific crest silhouette of conspecifics at social interaction distances, assessing the specific color patterns of individual crests and bodies for species and individual recognition, and detecting the specific postural displays of other group members in the behavioral contexts of breeding season competition and everyday social interaction, would have required a visual system with good spatial acuity at the relevant distances and the specific color discrimination capability needed for the assessment of the specific color patterns that served as visual social signals in the Campanian Hadrosaur community. The integration of the visual and acoustic sensory systems in the specific behavioral ecology of Parasaurolophus groups, the specific ways in which visual and acoustic information were combined in the neural processing of social signals to produce coherent behavioral responses, is one of the more complex behavioral biological aspects of this species, whose reconstruction requires the integration of sensory biological evidence from multiple modalities. The specific oxygen requirements of the Parasaurolophus respiratory system during vocalization, and the specific changes in respiratory airflow pattern that the production of crest-amplified vocalizations would have required relative to the normal breathing pattern of a resting or walking individual, connect the acoustic biology of the crest to the specific respiratory physiology of this large endothermic hadrosaur. Modern archosaurs, both birds and crocodilians, produce vocalizations by forcing air through the sound-producing structures of their vocal apparatus, with specific airflow rates and pressures that are substantially different from the airflow rates of normal quiet breathing, and the specific acoustic intensity of the produced sound is directly related to the specific airflow rate and air pressure generated by the respiratory muscles during vocalization. The specific metabolic cost of Parasaurolophus crest vocalizations, estimated from the specific airflow rates needed to produce sounds of the predicted intensity level at the fundamental resonant frequency of the crest passage system, would have been a specific increment above the resting metabolic cost of breathing, requiring enhanced activation of the respiratory musculature during the specific periods of vocalization. The specific respiratory anatomy of Parasaurolophus, assessed from the specific dimensions of the vertebral column, ribcage, and associated musculature visible in well-preserved postcranial skeletal material, indicates a respiratory system of the general large hadrosaur type, whose specific capacity for generating the elevated air pressures and flow rates needed for effective crest vocalization can be estimated from the comparison with the respiratory physiology of modern large birds producing comparable acoustic intensities. The inference that the Parasaurolophus respiratory system was fully capable of generating the specific airflow conditions needed for effective crest vocalization at the predicted intensities and durations is one of the physiological Constraints on the acoustic function hypothesis, whose assessment from the specific anatomy of the preserved skeletal material adds a quantitative physiological dimension to the functional analysis of the crest acoustic system. The specific chemical ecology of the Campanian coastal plain and the role of plant secondary metabolites in the specific food selection behavior of Parasaurolophus provides a chemical biological dimension of the dietary ecology of this species that the purely mechanical analysis of dental wear patterns and jaw biomechanics cannot fully capture. The specific plant secondary metabolites present in the diverse angiosperm flora of the Campanian coastal plain, alkaloids, tannins, terpenoids, and various other classes of defensive compounds whose concentrations and specific chemical identities varied among plant species and among plant parts within the same species, would have created a complex chemical landscape, within which Parasaurolophus food selection was guided by the specific palatability and digestibility consequences of different levels of secondary metabolite exposure. The specific detoxification capabilities of the Parasaurolophus hindgut microbiome, the diverse community of cellulose fermenting and secondary metabolite detoxifying microorganisms that populated the large fermentation chambers of the hindgut, would have determined the specific range of secondary metabolite concentrations tolerable in the daily diet, and therefore the specific range of plant types and plant parts accessible to Parasaurolophus foragers in any given location and season. The chemical ecology of large hindgut fermenting herbivores in vegetation communities with diverse secondary metabolite chemistry is one of the more complex and less completely understood aspects of terrestrial herbivore ecology in both modern and fossil systems, and the specific application of the relevant modern ecological frameworks to the specific paleobotanical and dental evidence for Parasaurolophus dietary ecology is one of the research directions whose future development will produce the most complete picture of the specific chemical dimensions of this species' interaction with the plant community of the Campanian coastal plain. The comparison of Parasaurolophus with the non-lambeosaurine hadrosaurs that co-occurred with it in the Campanian fauna, particularly the hadrosaurine species like Gripposaurus notabilis, Critosaurus navajovius, and Brachylophosaurus canadensis, whose flat-headed or solid-crested skulls, contrasted with the hollow-crested lambeosaurine anatomy, provides an important ecological perspective on the specific behavioral and ecological differences between hadrosaur groups with and without the hollow crest acoustic communication system. The hadrosaurines and lambeosaurines were ecologically similar in many respects. Both groups were large-bodied bipedal quadrupedal herbivores with the hadrosaur dental battery. Both groups were gregarious and social, and both groups inhabited broadly similar environments across the Campanian western interior, but differed specifically in the presence or absence of the hollow crest acoustic amplification system that distinguished the lambeosaurines from their flat-headed or solid-crested relatives. The specific ecological consequences of this acoustic communication difference between the two subfamilies, whether lambeosaurines with their hollow crests occupied different ecological niches, different microhabitats, or different social structures from co-occurring hadrosaurines without hollow crests, is one of the ecological questions that the comparative study of lambeosaurine and hadrosaurine material from the same formations can progressively address. The specific patterns of relative abundance of lambeosaurine and hadrosaurine species in different microenvironmental contexts within the same formations, if detectable from the specific sedimentological contexts of specimen occurrences, would provide direct ecological evidence for whether the hollow crest acoustic system was associated with specific habitat preferences or ecological roles that differentiated lambeosaurines from hadrosaurines in the mixed subfamily. Communities of the Campanian coastal plain fauna. The role of the Parasaurolophus crest in thermoregulation. While ultimately judged insufficient as a primary or exclusive function, explanation for the crest based on the specific surface area and thermal physics arguments discussed earlier in this documentary may have contributed a secondary thermoregulatory benefit to the primary acoustic function in the specific thermal ecology of large endothermic hadrosaurs living in the warm, subtropical to temperate climate of the Campanian coastal plain. The large blood vessel channels visible in the bony walls of the crest in well-preserved Parasaurolophus specimens, representing the pathways of blood vessels that in life supplied the overlying skin and mucous membrane with blood, would have constituted a specific heat exchange surface within the nasal passage system of the crest, where countercurrent heat exchange between inspired cool air and the warm blood of the nasal mucosa could have provided a specific thermal preconditioning of inspired air, comparable to the nasal countercurrent heat exchange systems documented in many modern vertebrates. The specific efficiency of this nasal countercurrent heat exchange in the elongated passages of the Parasaurolophus crest, compared with the much shorter nasal passages of a flat-headed hadrosaur, would have provided a specific enhancement of inspired air pre-warming in cold conditions and inspired air pre-cooling in hot conditions that supplemented the thermal management capabilities of the respiratory system. The secondary thermoregulatory contribution of the crest nasal passages, while quantitatively small relative to the total thermoregulatory capacity of a 3-ton endothermic animal whose general body surface provided the primary means of heat exchange with the environment, may have added a specific benefit to the primarily acoustic function of the crest that helped maintain the evolutionary justification for the energetic investment in crest construction across the Lambeosaurine hadrosaur lineage. The discovery of embryonic hadrosaur material, including specimens potentially attributable to Lambeosaurine species from Campanian formations across western North America, provides developing evidence for the specific embryonic biology of hadrosaurs related to Parasaurolophus, and for the specific developmental state of Lambeosaurine individuals at the time of hatching. The embryonic hadrosaur material documented from 2 Medicine Formation and related formations, while not always specifically identifiable to species or subfamily, shows the specific cranial proportions of very early developmental stage hadrosaur individuals, whose skull shapes differ substantially from those of juveniles and adults in ways that reflect the specific developmental biology of hadrosaur. Skull growth from the embryonic through the juvenile to the adult condition. The specific embryonic crest development in Lambeosaurine hadrosaurs, assessed from the degree of crest bone ossification in the earliest developmental stage, individuals identifiable as Lambeosaurines, indicates that the crest was either absent or in a very early developmental state at the time of hatching, consistent with the progressive ontogenetic development of the crest through the juvenile growth period that the available juvenile specimen evidence documents. The inference that Parasaurolophus hatchlings lacked functional acoustic crests at the time of hatching and therefore relied on other acoustic channels, laryngeal vocalizations produced without crest amplification for the specific parent-offspring communication that the earliest post-hatching period required, is one of the specific developmental biological inferences about Parasaurolophus' early life history that the embryonic and hatchling material progressively constrains as more material is recovered and analyzed from Campanian formations across the geographic range of this species. The specific aerodynamics of the Parasaurolophus crest and the degree to which the large posterior crest extension created specific aerodynamic effects on the head and neck of the running animal that influenced the specific biomechanics of head carriage during bipedal locomotion, is one of the more unusual functional biological questions about the crest that the physical dimensions of this structure raise. The crest of adult Parasaurolophus walkeri, extending approximately 1.5 meters behind the back of the skull and adding substantial mass to the posterior region of the head, would have created specific moment arms and torque requirements in the neck musculature during the specific head movements of bipedal locomotion that differed from those of flat-headed hadrosaurs without the large posterior crest. Extension. The specific biomechanical adaptations in the neck musculature and cervical vertebral anatomy that compensated for the specific torque requirements of supporting and moving the crested head during locomotion are accessible from the specific muscle attachment, scar sizes, and orientations visible on the far cervical vertebrae and skull base of Parasaurolophus specimens, and provide a specific biomechanical context for understanding the specific constraints that the crest imposed on the head-neck system beyond its acoustic function. The aerodynamic effects of the crest during fast bipedal locomotion, whether the specific shape of the crest created specific lift or drag forces that influenced the aerodynamic stability of the head and the specific energy, cost of running, are a more speculative but physically grounded aspect of the crest's effects on the overall biomechanics of the Parasaurolophus locomotor system that the specific dimensional analysis of the crest geometry, in the context of the estimated running speeds of this species, could progressively address through computational fluid dynamics modeling of the specific head geometry at relevant locomotor speeds. The parallel evolution of complex cranial crests in non-Hadrosaur Cretaceous ornithopods and the degree to which the hollow crest of Lambeosaurine hadrosaurs represents a specific phylogenetically restricted innovation versus a broader evolutionary tendency toward cranial elaboration in social ornithopod lineages, generally provides a comparative ornithician context for understanding the specific evolution of the Parasaurolophus crest within the Lambeosaurine lineage. The iguanodontian ornithopods ancestral to hadrosaurs showed various degrees of cranial elaboration in specific lineages, including the bony nasal bosses of some iguanodon species and the specific nasal and premaxillary modifications of various hadrosauroid taxa that preceded the fully developed hollow crest of the advanced Lambeosaurines, documenting the specific evolutionary trajectory of progressive cranial elaboration within the ornithopod hadrosaur lineage that eventually produced the extreme hollow crest of Parasaurolophus. The non-hadrosaur dinosaurian lineages that evolved independent cranial display structures, the domed heads of pachycephalosaurs, the frills and horns of ceratopsians, the nasal crests of some theropods, represent independently evolved elaborations of different cranial elements in different evolutionary contexts, and provide a broader comparative framework for understanding the general evolutionary tendency toward cranial display structure elaboration in social dinosaurian lineages subject to sexual selection pressure for display structure development. The convergence of diverse dinosaurian lineages on the evolution of elaborate cranial display structures in the Cretaceous, when the specific social organization and behavioral complexity of large dinosaurian species created the specific selection pressures for effective visual and acoustic communication displays, is one of the more broadly informative patterns in Mesozoic evolutionary biology and illustrates the specific ways in which social selection pressure consistently drives the evolution of elaborate display structures across taxonomically diverse vertebrate lineages. The acoustic communication function of the Parasaurolophus crest understood in the full context of the specific evolutionary history of the Lambeosaurine lineage, the specific acoustic physics of the crest resonance system, the specific ecological demands of the Campanian coastal plain environment, and the specific comparative biology of modern large vocal vertebrates, represents one of the most completely specified and most rigorously supported behavioral interpretations available for any non-avian dinosaurian anatomical feature. The specific convergence of multiple independent lines of evidence on this behavioral interpretation, the specific internal passage anatomy consistent with a resonating acoustic chamber, the specific resonant frequency predictions consistent with long-distance communication in forested environments, the specific co-occurrence of multiple Lambeosaurine species with morphologically differentiated crests consistent with species recognition function, the specific ontogenetic development of the crest at or near sexual maturity consistent with a sexually selected display structure, and the specific comparative biology of modern large vocal vertebrates using resonating chambers for low-frequency sound production, makes the acoustic function hypothesis the most comprehensively supported functional interpretation in the history of Parasaurolophus research. The progressive quantitative rigor with which successive research programs have evaluated this hypothesis, from the qualitative descriptions of the early functional anatomists through the semi-quantitative analyses of the programs, mid-20th century researchers to the fully quantitative acoustic modeling of Evans and colleagues in 2009, documents the progressive accumulation of evidentiary support that has transformed the power of the Evans acoustic function from a plausible hypothesis among several alternatives to the overwhelming consensus interpretation of the scientific community. The 100 facts about Parasaurolophus presented in this documentary are built on this foundation of accumulated evidence and progressive scientific achievement, and together they represent the most complete biological account of the dinosaur that could sing that current science is capable of producing. The future of Parasaurolophus research and the specific scientific questions most likely to be addressed by the research programs currently active in the study of this species provides a prospective view of how the 100 facts of this documentary will be extended and elaborated as new specimens, new methods, and new conceptual frameworks contribute new biological knowledge about this extraordinary Cretaceous hadrosaur. The recovery of more completely preserved post-cranial Parasaurolophus material from productive Campanian formations is one of the highest priorities for the future expansion of the known anatomy of this species. Because the current documentation of Parasaurolophus post-cranial anatomy is substantially less complete than the cranial documentation and limits the specific locomotor, dietary, and physiological analyses whose conclusions would most directly advance the complete biological understanding of this species. The development of more complete and more quantitatively grounded paleoclimate reconstructions for the specific formations preserving Parasaurolophus material will progressively constrain the specific environmental conditions within which the behavioral ecology of this species functioned, and will allow the increasingly precise ecological modeling of the specific habitat preferences, seasonal behavioral patterns, and physiological responses to environmental variation that characterized Parasaurolophus populations across the geographic and temporal range of the genus. The progressive development of advanced acoustic simulation capabilities, capable of modeling the complete three-dimensional acoustic behavior of the Parasaurolophus crest passage system, including the specific wave propagation and resonance effects that simplified one-dimensional tube models cannot fully capture, will produce increasingly complete and increasingly realistic acoustic models of the specific sounds that living Parasaurolophus individuals produced. Each of these research directions will contribute new facts to the scientific understanding of the dinosaur that could sing progressively deepening and enriching the biological portrait that the 100 facts of this documentary represent. The specific role of the Parasaurolophus crest as a species recognition mechanism in the multi-species Lambeosaurine community of the Campanian Western Interior is one of the most ecologically compelling functional arguments for the specific crest morphology differences among co-occurring Lambeosaurine species, and is directly testable in principle from the specific predictions it makes about the expected relationships between crest morphology, acoustic properties, and species co-occurrence patterns in the Campanian fossil record. The species recognition hypothesis predicts that co-occurring Lambeosaurine species should show greater morphological and acoustic differentiation of their crests than allopatric species whose populations never overlapped and, therefore, never experienced the specific selection pressure for character displacement in crest morphology that co-occurrence would generate. The specific patterns of Lambeosaurine crest differentiation in the Campanian fauna, assessed from the specific morphological distances among the crests of co-occurring species relative to those of allopatric species, are one of the datasets most directly relevant to testing this prediction of the species recognition hypothesis, and are progressively becoming available for analysis as the systematic documentation of Lambeosaurine diversity and geographic distribution in Campanian formations across Western North America becomes more complete. The specific acoustic differentiation of co-occurring Lambeosaurine species, predicted from the acoustic modeling of their respective crest passage geometries, provides a second quantitative test of the species recognition hypothesis. If species recognition through acoustic differentiation was a significant function of crest morphology, the predicted acoustic differences between co-occurring species should be large enough to be reliably discriminable by the auditory systems of the relevant animals, a testable prediction that the specific acoustic modeling data and modern auditory biology data can be combined to evaluate. The progressive application of these specific tests to the growing dataset of Campanian Lambeosaurine crest morphologies and their acoustic modeling results is one of the most productive research directions for advancing the understanding of the specific functions of the Parasaurolophus crest in the ecological context of the multi-species Campanian Hadrosaur community. The preservation of color information in some exceptionally fossilized Cretaceous vertebrate specimens, and the developing methods for recovering specific color information from the melanin pigment signatures preserved in the tissue of these specimens, provides a developing research frontier for the recovery of color pattern information from fossil Hadrosaur specimens that could eventually yield specific evidence about the coloration of the Parasaurolophus crest and body. The melansome-based color reconstruction method applied most successfully to the feathered theropod specimens from the Liaoning province of China, where feather microstructure preservation is extraordinarily complete, has documented the specific color patterns of several feathered theropod species, and has established the principle that specific color information is preservable in some fossilized biological specimens under specific preservational conditions. The application of comparable methods to hadrosaur skin impressions, where the specific pigment-containing cells of the original skin may be preserved in specific diagenetic conditions in some exceptional hadrosaur localities, represents a developing research direction whose eventual success would provide the most direct available evidence for the specific coloration of the Parasaurolophus body surface. The specific skin impressions documented from some hadrosaur specimens, while showing the specific texture and scale pattern of the external integument, have not yet yielded specific color information from melansome analysis in published studies, reflecting the specific preservational requirements for melansome retention that are more demanding than those for the preservation of the physical scale patterns visible in conventional fossilization. The progressive development of more sensitive analytical methods for detecting trace quantities of melanin and other biological pigments in fossil skin specimens is one of the research frontiers most likely to eventually yield specific color information. For Parasaurolophus and related hadrosaurs, adding a vivid visual dimension to the biological portrait whose acoustic dimensions, the crest anatomy, has already allowed to be reconstructed with quantitative precision. The significance of Parasaurolophus for the broader scientific understanding of dinosaurian behavioral evolution during the Cretaceous, and the specific ways in which the acoustic biology of the crest contributes to the larger picture of behavioral sophistication and social complexity in late Cretaceous dinosaurian communities, connects the specific biology of this individual species to the broader narrative of dinosaurian behavioral evolution across the Mesozoic. The Campanian fauna of Western North America, with its extraordinary diversity of large social dinosaurs, the crest displaying Lambeosaurine hadrosaurs, the elaborate horn and frill displaying ceratopsians, the dome-headed pachycephalosaurs whose head-butting competitions are documented by the specific biomechanics of their pachycephalic skulls, and the large-brained Maniraptor and theropods whose cognitive complexity rivals that of some modern birds, represents the culminating expression of a broader trend toward increased behavioral complexity and social sophistication in dinosaurian lineages that is one of the more compelling evolutionary biological narratives of the late Cretaceous. The specific behavioral sophistication documented for Parasaurolophus, the quantitatively reconstructed acoustic communication system, the inferred social group structure, the specific ontogenetic acoustic development of the crest as a sexually selected display structure, is one of the most completely documented examples of this broader trend toward behavioral complexity in Campanian dinosaurian communities, and provides one of the strongest individual species arguments for the behavioral richness of the Mesozoic world. 100 facts about Parasaurolophus. 100 specific contributions to the scientific understanding of the behavioral ecology of the most complex and most socially sophisticated terrestrial vertebrate communities that the geological record of the Cretaceous has preserved, and 100 windows into the acoustic dimension of the Mesozoic world that the extraordinary anatomy of the Parasaurolophus crest makes uniquely accessible to scientific reconstruction. The 100 facts about Parasaurolophus, the dinosaur that could sing, conclude with the recognition that the physical evidence on which every one of these facts is grounded, the skulls in the museum collections, the scan data revealing their internal anatomy, the acoustic calculations derived from that data, and the comparative biological framework within which those calculations are interpreted, is as permanent and as accessible as any evidence in natural history science. The skulls of Parasaurolophus walkeri in the collections of the Royal Ontario Museum and the Royal Tyrrell Museum of Paleontology, the skull of Parasaurolophus tubicin in the collection of the New Mexico Museum of Natural History and Science, the skull of Parasaurolophus certocristatus and the remarkable juvenile specimen in the collection of the Natural History Museum of Utah. These physical objects are the specific foundation on which the entire scientific understanding of this species rests, and their permanent preservation in institutional collections ensures that the evidence for every fact presented in this documentary is available for verification, reanalysis, and extension by the researchers of the present and the future. The science of Parasaurolophus is not finished. The understanding will continue to grow as new specimens are recovered, as new methods are applied to existing material, and as new conceptual frameworks illuminate aspects of the biology of this extraordinary animal that the current frameworks have not yet fully explored. But the 100 facts presented here represent the best current approximation of the biological truth of Parasaurolophus, the most complete, the most rigorously grounded, and the most scientifically justified portrait of the dinosaur that could sing that a century of investigation has produced: the crest, the passages, the resonant frequencies, the Cretaceous song, the extraordinary biological achievement of the most acoustically remarkable non-avian dinosaur that the fossil record of the Mesozoic world has preserved, the specific paleontological field techniques employed in the recovery of Parasaurolophus specimens, and the specific challenges of excavating the large and fragile cranial material of this species from the compacted sedimentary matrix of Campanian formations, provide an important practical dimension to the scientific story of how the fossil evidence for Parasaurolophus biology has been assembled from geological deposits over more than a century of field investigation. The extraction of a complete Parasaurolophus skull from the sedimentary matrix of a Campanian formation requires the specific combination of geological and paleontological expertise needed to identify the extent of the specimen in the rock before excavation begins. To design an excavation strategy that progresses from the surrounding matrix inward toward the specimen without damaging the delicate bony walls of the hollow crest passages, and to stabilize the specimen with consolidants at each stage of excavation to prevent the collapse of fragile bone that has been weakened by millions of years of diagenetic modification. The specific challenges of crest preservation in Parasaurolophus excavation include the thin, bony walls of the crest tube, which in life were approximately 5 to 10 millimeters thick, but which in fossil specimens may have been further weakened by diagenetic processes to the point where they require immediate consolidant application when exposed during excavation to prevent collapse under the weight of the overlying matrix or the physical pressure of excavation tools. The specific laboratory preparation work needed to clean the matrix from Parasaurolophus skull specimens after field excavation, using air scribes, needles, and chemical consolidants to remove the enclosing rock without damaging the specimen, can require hundreds to thousands of hours of skilled preparator work for large and completely preserved skulls, making the recovery and preparation of complete Parasaurolophus specimens one of the most technically demanding and most time-intensive activities in vertebrate paleontological collections work. The computed tomographic scanning of Parasaurolophus skull specimens, which has provided the specific internal anatomical data most directly relevant to the acoustic modeling of the crest resonance system, represents one of the more technically demanding applications of medical imaging technology to paleontological specimens and illustrates the specific ways in which the methods of medical science and engineering have been productively adapted to the specific requirements of paleontological research. The CT scanners used for paleontological specimen imaging range from conventional medical CT scanners, whose spatial resolutions of approximately 1 millimeter are adequate for characterizing the large-scale internal anatomy of Parasaurolophus-sized specimens, to industrial CT systems with higher X-ray energies capable of penetrating the dense rock matrix surrounding fossil specimens, to micro-CT systems with spatial resolutions of tens to hundreds of micrometers capable of revealing the fine internal structure of smaller specimens or specific regions of larger ones. The specific technical challenges of CT scanning large Parasaurolophus skulls include the need for scanning systems whose field of view is large enough to encompass the full dimensions of the specimen, the elongated crest of a Prius. Large walkery skull may extend more than 2 meters in length, and whose X-ray energy is sufficient to penetrate the combined thickness of the dense fossil bone and any surrounding rock matrix that has not been removed in word. Laboratory preparation. The digital processing of the CT scan data, converting the raw attenuation values of each scan slice into the specific three-dimensional anatomical models used in acoustic modeling and morphological analysis, requires the specific image processing software and computational resources whose increasing accessibility as commercial and open-source tools have transformed the practice of CT-based paleontological research from a specialized capability available only at facilities with dedicated paleontological CT scanning infrastructure to an increasingly routine analytical approach, accessible to research groups with access to appropriate scanning facilities. The integration of Parasaurolophus into the educational curricula of natural history museums worldwide, and the specific ways in which the acoustic biology of the crest has been communicated to diverse audiences from young children through adult specialists, illustrates the specific public communication potential of rigorously grounded scientific knowledge about extinct animals and the specific role that Parasaurolophus has played in the broader mission of natural history museums to communicate the science of paleontology to the public. The display of Parasaurolophus skeletal mounts in major natural history museums across North America, Europe, and elsewhere provides millions of museum visitors annually with their first direct encounter with the physical reality of this extraordinary dinosaur, and the specific experience of seeing the dramatically elongated crest extending behind the skull of a mounted skeleton communicates the visual impact of this anatomical feature more immediately and more powerfully than any photograph or illustration. The specific interactive exhibits developed by some natural history museums to communicate the acoustic function of the Parasaurolophus crest, including exhibits that allow visitors to listen to computer-generated simulations of the predicted crest vocalizations, to see animations showing how the air flow through the crest passages would have generated the predicted resonant frequencies, and to interact with physical models of the crest passage geometry to understand the specific acoustic principles involved, represent some of the most scientifically complete and pedagogically effective dinosaur exhibits currently deployed in the museum world. The development of these educational materials from the specific scientific research on Parasaurolophus acoustics illustrates the direct pathway from specific scientific discovery to specific public education that makes the investment in fundamental paleontological research valuable not only to the scientific community, but to the much broader public whose appreciation of the natural world is enriched by the specific biological knowledge that paleontological research produces. The specific differences in body proportions among the three Parasaurolophus species, beyond the crest morphology differences that most directly distinguish them, provide additional evidence for the specific ecological and evolutionary differentiation of these three taxa, and for the specific ways in which differences in body size, neck length, limb proportions, and other anatomical features complemented the crest morphology differences in creating three biologically distinct species from the shared ancestral Parasaurolophus body plan. The body size differences among the three species, while not as thoroughly quantified as the crest morphology differences due to the incompleteness of postcranial material for some species, indicate that the three species were broadly similar in adult body size, within the range typical for large hadrosaurs, with any specific size differences among species being smaller magnitude than the crest morphology differences and therefore less immediately apparent as biological signals differentiating the three taxa. The specific limb proportions of the three species, where adequate postcranial material is available for comparison, show the generally similar hind-limb to forelimb ratio characteristic of the Hadrosaur body plan across multiple species, suggesting that the locomotor biology of the three Parasaurolophus species was broadly similar, despite the specific differences in crest morphology that most immediately distinguish them. The specific ecological implications of the body proportion similarities among the three species, that the three were broadly comparable in dietary range, locomotor capability, and physiological requirements, despite their distinctive crest morphologies, support the interpretation that the crest morphology differences among the species were primarily functional in acoustic and visual communication contexts rather than in the foraging, locomotion, or physiological ecology that are more directly reflected in the proportions of the trunk and limbs. The specific geological age relationships among the three Parasaurolophus species, assessed from the specific stratigraphic positions of their occurrences within the temporal sequence of Campanian formations across western North America, provide evidence for the specific evolutionary chronology of the genus and for the specific temporal relationship among the three species within the evolutionary history of the Parasaurolophus lineage. The oldest known Parasaurolophus material, from the lower portions of the Campanian sequence, represents the earliest documented occurrence of the genus and provides a temporal anchor for the evolutionary history of Parasaurolophus within the broader context of Lambeosaurine hadrosaur evolution during the Campanian. The specific temporal ranges of the three recognized species, assessed from the stratigraphic distributions of their occurrences in the relevant formations, indicate a temporal sequence in which Walkeri and Certocristatus appear in the Middle Campanian and Tubocene extends into the later Campanian of the New Mexico succession, providing a partial chronological framework for the evolutionary relationships among the three species. The integration of this temporal stratigraphic evidence with the phylogenetic analysis of the specific morphological differences among the three species is one of the primary tools for understanding the specific evolutionary history of crest diversification within the Parasaurolophus lineage, and for assessing whether the three recognized species represent a sequence of anagenetic evolution within a single lineage, the products of phylogenetic branching within the genus, or some combination of both evolutionary processes operating at different phases of the genus's Campanian evolutionary history. The resolution of these evolutionary historical questions awaits the recovery of more stratigraphically well-documented Parasaurolophus material from the specific temporal intervals intermediate between the currently known occurrences of the different species. The microbiome of the Parasaurolophus hindgut, while entirely inaccessible from the fossil record, is one of the most functionally important aspects of this species' biology, whose character can be inferred from the comparison with the gut microbiomes of modern large hindgut fermenting herbivores and from the general principles of herbivore digestive ecology in animals with large hindgut fermentation chambers. The gut microbiomes of modern large hindgut fermenting herbivores, including horses, rhinoceroses, elephants, and various other species, are complex communities of hundreds to thousands of microbial species whose specific composition reflects the specific dietary substrates available in the hindgut, the specific physical and chemical conditions of the fermentation chamber, and the specific evolutionary history of the host-microbe relationship in each herbivore lineage. The specific functional capabilities required of the Parasaurolophus hindgut microbiome, the efficient degradation of cellulose and hemicellulose from the fibrous angiosperm and conifer vegetation that dominated the Campanian plant community, the detoxification of the specific secondary metabolites present in the consumed plant material, the synthesis of essential amino acids and vitamins that the host could not synthesize independently, and the specific fermentation chemistry that converted the bacterial metabolic products of plant degradation into the volatile fatty acids that served as the primary energy source for the host, are the same functional capabilities required of the hindgut microbiomes of modern large hindgut fermenting herbivores, confirming that the evolutionary and ecological principles governing hindgut microbiome function in modern systems apply directly to the inferred microbiome function of Parasaurolophus. The specific composition of the Parasaurolophus hindgut microbiome, in terms of specific microbial taxa, cannot be recovered from the fossil record, but the functional ecology of the microbiome is as well constrained by the specific dietary and digestive requirements of this large Campanian herbivore as the functional ecology of any comparable modern system. The specific contributions of the Royal Tyrrell Museum of Paleontology in Drumheller, Alberta, to the scientific study of Parasaurolophus, including the recovery and curation of some of the most scientifically important Parasaurolophus specimens known, and the facilitation of the research programs that have produced the most significant advances in the understanding of this species, represent one of the more important institutional contributions to the science of Campanian dinosaur paleontology and to the specific understanding of Parasaurolophus biology. The TMP 2001 specimen of Parasaurolophus walkeri, recovered from the Oldman Formation of Alberta and curated in the Royal Tyrrell Museum collections, served as the primary anatomical basis for the acoustic modeling calculations published by Evans and Rice in 2009 and is one of the most scientifically productive individual Parasaurolophus specimens in the entire collection history of this species. The systematic field programs of the Royal Tyrrell Museum in the Campanian formations of Alberta continued across decades of consistent institutional support for paleontological field research in the most productive Parasaurolophus-bearing formations of the province, have progressively expanded the sample of Parasaurolophus specimens available for scientific study and have contributed importantly to the broader documentation of Campanian hadrosaur diversity and ecology in the Alberta formations. The specific contributions of the Royal Tyrrell Museum research staff to the scientific analysis of Parasaurolophus material, including the collaborative research programs that have produced some of the most influential published studies of this species, illustrate the specific institutional role of major natural history museums in advancing the scientific understanding of the fossil record through the combination of sustained field programs, comprehensive collections, curation, and productive collaborative research programs that translate the physical evidence of the fossil record into the specific scientific knowledge that the 100 facts of this documentary represent. The evolutionary relationships of Parasaurolophus to the other Lambeosaurine hadrosaurs of the Campanian western interior, assessed through the specific cladistic phylogenetic analysis of the morphological characters that distinguish different Lambeosaurine species and genera, provide the evolutionary context within which the specific crest morphology of Parasaurolophus is most fully understood as a product of the specific evolutionary history of the lineage within the broader Lambeosaurine radiation. The published phylogenetic analyses of Lambeosaurine hadrosaurs, including the comprehensive studies by Evans, Rice, and colleagues, and by various other research groups using different character matrices and different phylogenetic methods, consistently recover Parasaurolophus as a member of a clade of particularly long-crested Lambeosaurines, whose members share the specific posteriorly directed crest extension as a synapomorphy, a derived character shared through common ancestry that defines the clade. The specific sister group of Parasaurolophus within this long-crested Lambeosaurine clade, and the specific phylogenetic positions of the three recognized Parasaurolophus species relative to each other and to the closely related Tyrannosaurus from Asia, are questions whose resolution depends on the specific character differences among these taxa and the specific phylogenetic analysis methods applied to the character differences. Available character matrix. The evolutionary implications of the specific phylogenetic position of Parasaurolophus for the reconstruction of the ancestral condition of the long-crested Lambeosaurine lineage, the specific crest morphology and acoustic properties of the common ancestor from which both Parasaurolophus and its sister group were derived, are one of the specific evolutionary biological questions that the integration of cladistic phylogenetic analysis with acoustic modeling data can address, allowing the reconstruction of the evolutionary trajectory of acoustic function change within the long-crested Lambeosaurine lineage and the specific evolutionary events that produced the particular acoustic properties documented for each species by acoustic modeling of their preserved crest anatomy. The amino acid chemistry of Parasaurolophus bone, collagen, where this material is preserved in sufficiently well-protected specimens from geologically younger Campanian formations, or from exceptionally preserving depositional environments, is one of the molecular biological approaches progressively being applied to Campanian dinosaurian material to extract specific biochemical information about the physiological biology of these ancient animals. The preservation of recognizable collagen peptide sequences in some late Cretaceous dinosaurian specimens, including the controversial but potentially groundbreaking reports from Tyrannosaurus rex specimens published by Mary Schweitzer and colleagues and progressively confirmed and extended by subsequent analytical work, suggests that ancient protein fragments may be recoverable from some exceptionally well-preserved Hadrosaur specimens as well. The specific amino acid sequences recoverable from ancient Parasaurolophus collagen fragments, if such material is identifiable in well-preserved Campanian specimens from appropriate depositional contexts, would provide phylogenetic information from the comparison of specific sequence positions with the collagen sequences of modern birds and crocodilians, directly relevant to the specific evolutionary position of Parasaurolophus within the vertebrate phylogenetic tree, and complementing the morphological phylogenetic analyses, whose conclusions are based entirely on anatomical character evidence. The progressive development of more sensitive mass spectrometry methods capable of detecting and sequencing increasingly degraded and low-abundance ancient protein fragments from fossil specimens is making the molecular biological characterization of Campanian dinosaurian specimens progressively more feasible, and is building the foundation for a molecular biological dimension of Parasaurolophus biology, whose eventual development will complement the morphological, acoustical, and ecological evidence of the fossil record with the specific molecular biological perspective that ancient proteomics can provide. The specific patterns of isotopic variation in Parasaurolophus tooth enamel across the individual replacement sequence of the Hadrosaur dental battery, where the isotopic compositions of individual teeth at different positions in the dental sequence record the specific isotopic environments of different developmental stages in the life history of the individual, provide a uniquely detailed temporal record of the individual level biology of specific Parasaurolophus animals that the skeletal record alone cannot supply. The Hadrosaur dental battery, with its continuous tooth replacement system producing hundreds of successive teeth across the lifetime of the individual, provides a specific temporal archive of the isotopic environments experienced by the animal during successive periods of its life, because each tooth records the specific oxygen and carbon isotope values of the body fluids and diet during the specific period when that tooth's enamel was being formed. The specific reading of this temporal archive in Parasaurolophus individuals from specific formations using the micro-analytical sampling methods that allow isotopic measurement from very small areas of individual tooth enamel layers, would produce a record of the specific geographic movements, dietary shifts, and seasonal behaviors of individual animals at a temporal resolution of weeks to months, substantially finer than the annual resolution available from the annual growth marks in bone cortex. The application of this high-resolution isotopic sampling approach to well-preserved Parasaurolophus dental material from specific Campanian formations, combined with the specific paleoclimate and paleogeographic isotopic reference frameworks established for those formations, is one of the research programs most likely to produce the most detailed individual-level biological records available for any Parasaurolophus specimen, and will contribute specifically to the understanding of the seasonal behavioral patterns, including the specific timing of migrations, breeding season activities, and habitat shifts that characterized the annual life cycle of individual Parasaurolophus animals in the Campanian western interior. The 100 facts about Parasaurolophus have been assembled from the full range of physical and analytical evidence available from more than a century of scientific investigation of this extraordinary Cretaceous hadrosaur, and together they constitute a biological portrait of unprecedented completeness and scientific rigor for a non-avian dinosaurian species whose behavioral biology has been recovered from the physical dimensions of its hollow skull. Bones, with a mathematical precision that makes the reconstruction of its specific vocalizations one of the most remarkable intellectual achievements in the history of paleontological science. The physical skulls are in the museums, the acoustic calculations are in the literature, the predicted frequencies are as mathematically certain as the specific geometry of the passage system from which they are derived allows them to be. The comparative biology of modern, large, vocal vertebrates validates the specific physical principles on which the predictions are based, and the evolutionary biological context of sexual selection and species recognition in multi-species Campanian hadrosaur communities provides the ecological logic within which the specific crest morphology and its acoustic properties make the most complete biological sense. The 100 facts of this documentary are the product of this convergence of physical evidence, mathematical analysis, comparative biology, and evolutionary theory, assembled through the specific intellectual efforts of the specific researchers who have devoted their scientific careers to understanding one of the most acoustically and visually distinctive dinosaurs that the geological history of the Mesozoic world has preserved. The crest, the passages, the resonant frequency of 30 to 80 Hz, the Cretaceous song of Parasaurolophus, resonating through the ancient forests of western North America 75 million years ago. The extraordinary biological truth of the dinosaur that could sing, recovered from the bones of the most remarkable hadrosaur in the history of vertebrate paleontology. The enduring legacy of Parasaurolophus for the scientific understanding of dinosaurian biology and for the public imagination of prehistoric life extends far beyond the specific facts of its anatomy and acoustic biology to the broader cultural significance of this animal as an emblem of the behavioral sophistication and ecological complexity of the Mesozoic world. The specific discovery that a Cretaceous dinosaur communicated through a sophisticated resonating organ built into its skull that 75 million years ago, large social hadrosaurs were producing low-frequency calls whose carrying distance through the Campanian forest was measured in kilometers rather than meters, is a discovery whose significance for the human understanding of ancient life is as profound as any in the history of paleontological science. It tells us that the Mesozoic world was as acoustically rich as the modern world, filled with the calls and responses of complex social animals whose behavioral lives were as sophisticated in their acoustic dimensions as those of the modern large vertebrates, that the study of Parasaurolophus most directly connects them. 2. It tells us that the evolution of complex acoustic communication is an ancient biological achievement, rooted in the late Cretaceous and extending through the continuous evolutionary thread of the Archosaur lineage to the modern birds that fill the contemporary world with their own acoustic complexity. And it tells us that the science of paleontology, applied with sufficient rigor and sufficient creativity to the specific physical evidence of the fossil record, can recover specific biological truths about ancient life that enrich the human understanding of the natural world in ways that extend from the purely scientific to the deeply cultural and aesthetic. 100. Facts about Parasaurolophus, the dinosaur that could sing. The most acoustically remarkable chapter in the biology of the most successful terrestrial vertebrate radiation in the history of life. The global research community studying Parasaurolophus and the broader Campanian hadrosaur fauna of Western North America is one of the most active and most productively collaborative communities in vertebrate paleontology, spanning research institutions across the United States, Canada, Europe, and Asia, whose combined field, laboratory, and analytical capabilities are collectively producing the most rapid advances in the scientific understanding of these extraordinary Cretaceous animals that the history of hadrosaur research has seen. The specific collaborative research programs that have produced the most significant recent advances in Parasaurolophus biology, including the multi-institution collaboration that produced the acoustic modeling study of Evans and colleagues, and the multidisciplinary programs that have combined computed tomographic imaging, isotopic analysis, and comparative biological analysis in the study of Campanian hadrosaur ecology and behavior, illustrate the specific intellectual and practical advantages of collaborative research in advancing the understanding of complex biological questions that exceed the capabilities of any single researcher or single institution to address alone. The progressive development of open-access databases for Campanian hadrosaur specimen data, scan data, and isotopic data is making the specific evidence base for Parasaurolophus research increasingly accessible to the global research community and is enabling the collaborative, analytical approaches that produce the most comprehensive and most quantitatively rigorous conclusions about the biology of this species. The future of Parasaurolophus research is therefore not the isolated work of individual specialists in specific institutions, but the collaborative effort of a global community whose combined intellectual resources are collectively directed toward the most complete possible understanding of one of the most scientifically productive and most publicly engaging subjects in the history of vertebrate paleontology. 100 facts about the dinosaur that could sing, and behind them, the global community of scientists whose sustained intellectual commitment to understanding the Mesozoic world has made these facts available to the present. 100 facts about Parasaurolophus, the dinosaur that could sing, are complete. They tell the story of an animal whose hollow skull bones encode a biological acoustic system of extraordinary sophistication, whose low-frequency vocalizations once resonated through the Cretaceous forests of Western North America with a power and a carrying distance unmatched by any contemporaneous terrestrial vertebrate, and whose evolutionary history within the Lambeosaurine hadrosaur lineage documents the progressive elaboration of an acoustic display structure driven by the specific evolutionary pressures of sexual selection and species recognition in a diverse community of socially complex large herbivores. The story of Parasaurolophus is a story about the specific biological power of resonance, the physical phenomenon that occurs when sound waves of the right frequency travel through the right-sized passage and amplify. themselves through the mathematical logic of constructive interference into sounds of far greater intensity and carrying distance than any simple sound source of the same energy could produce. It is a story about the specific evolutionary power of sexual selection, the evolutionary mechanism that drives the progressive elaboration of display structures whose size and quality honestly signal individual fitness to potential mates and competing conspecifics, and that has produced, in Parasaurolophus, one of the most extreme examples of sexually selected cranial elaboration in the vertebrate fossil record. And it is a story about the specific scientific power of paleontological analysis, the intellectual capability of modern science to recover specific biological truths about ancient organisms from the specific physical evidence. Their bones preserve, transcending the apparent impossibility of knowing anything about the sounds of extinct animals to produce mathematically grounded, physically validated, and evolutionarily coherent reconstructions of the specific acoustic biology of animals that lived 75 million years ago in the forests of Cretaceous North America. 100 facts. The dinosaur that could sing. The song preserved in the mathematics of its hollow bones. The specific plant biomass productivity of the Campanian coastal plain, estimated from the specific vegetation types documented in the paleobotanical record of relevant formations, and from the comparison with the net primary productivity of modern ecosystems with comparable vegetation, composition, climate, provides a quantitative ecological context for understanding the specific carrying capacity of the Campanian environment for large herbivores, including Parasaurolophus. The net primary productivity of a vegetation community, the specific rate at which photosynthesis converts solar energy into plant biomass available for consumption by herbivores, is the fundamental ecological parameter that determines the specific number and total biomass of large herbivores that a given area of vegetation can support. The specific paleoclimate reconstruction of the Campanian coastal plain, indicating warm subtropical to temperate temperatures, high humidity, and substantial annual precipitation, suggests a vegetation community whose net primary productivity was high relative to modern temperate forests and comparable to modern subtropical or warm temperate forest ecosystems whose productivity supports high densities of large herbivores. The specific conversion efficiency from plant biomass to large herbivore biomass, estimated from the metabolic requirements of a large endothermic herbivore like Parasaurolophus relative to the estimated plant biomass available per unit area, produces an estimate of the specific density of Parasaurolophus individuals supportable per unit area of Campanian coastal plain vegetation, an estimate directly relevant to understanding the specific social conditions within which the acoustic communication function of the crest was most intensively deployed, and within which the specific alarm communication, mate attraction, and social cohesion functions of the crest vocalizations provided the most substantial fitness benefits to individuals with the most effective acoustic communication systems. The specific population density estimates for Parasaurolophus in productive Campanian coastal plain environments, while necessarily approximate given the uncertainties in the relevant ecological parameters, provide a quantitative ecological context for the specific social biology of this species that complements the more qualitative evidence from bone bed assemblages and trackway associations. The deep time perspective provided by the 75 million years that separate the Campanian world of Parasaurolophus from the present illuminates both the specific evolutionary distances and the specific evolutionary continuities that connect the acoustic biology of this Cretaceous Hadrosaur to the acoustic biology of the modern archosaurs, birds and crocodilians, whose evolutionary relationships to Parasaurolophus are most directly relevant to the biological interpretation of the crest vocalization system. The specific evolutionary distance between Parasaurolophus and modern birds, measured in the specific molecular evolutionary divergence between the two lineages and in the specific morphological changes that have accumulated in the avian lineage since its divergence from the non-avian dinosaur ancestors of modern birds, is approximately 80 to 90 million years of independent evolutionary history, sufficient time for the accumulation of very substantial biological differences between the two lineages while retaining the fundamental archosaur organizational plan shared through common ancestry. The specific evolutionary continuities between Parasaurolophus and modern birds, including the shared archosaur respiratory system anatomy, the shared archosaur inner ear anatomy and auditory biology, the shared archosaur social behavioral organization, and the shared archosaur tendency toward acoustic communication in social contexts, are the specific biological connections that make the comparison with modern bird acoustic biology the most directly relevant comparative framework for interpreting the acoustic function of the Parasaurolophus crest. The 75 million years of deep time separating Parasaurolophus from the present is not primarily a barrier to biological understanding, but rather a specific evolutionary interval across which the relevant biological comparisons can be traced. Through the systematic application of the comparative biological and phylogenetic methods that modern evolutionary biology provides, connecting the specific acoustic biology of the Cretaceous Hadrosaur to the specific acoustic biology of the modern archosaur lineages, whose evolutionary relationships to Parasaurolophus make them the most informative biological reference available for interpreting the fossil evidence. The specific neuroscience of vocal learning in modern archosaurs, and the degree to which the sophisticated vocal communication systems of modern birds depend on specific neural circuits for the learning and refinement of specific vocalizations during critical developmental periods, provides an important comparative context for assessing whether the acoustic behavior of Parasaurolophus was primarily innate, genetically encoded, and expressed without learning, or whether it involved significant vocal learning comparable to the song learning of modern songbirds. Modern songbirds learn their species-specific songs through a specific developmental process in which juvenile birds listen to the songs of adults, form a memory template of the specific acoustic features of the adult song, and then practice producing sounds until their own vocalizations match the memorized template, a process whose specific neural basis in the telencephalic song control circuits of birds is one of the most thoroughly studied behavioral learning systems in neuroscience. Modern crocodilians and non-songbird birds produce vocalizations that are largely innate, genetically encoded in the motor programs that produce specific vocalization patterns without significant individual learning. And the ancestral archosaur condition is most likely the innate vocalization system, with vocal learning being a derived capability of the songbird lineage. The inference that Parasaurolophus vocalizations were primarily innate rather than learned, based on the ancestral archosaur vocalization biology and the specific developmental stage at which the crest acoustic system became functional as the crest developed toward its adult dimensions, is one of the specific behavioral biological inferences about Parasaurolophus that the comparative neuroscience of modern archosaurs most directly constrains, and it connects the specific acoustic behavior of this Cretaceous hadrosaur to the broader evolutionary history of vocal communication in the archosaur lineage. The specific evidence from the dinosaur park formation for the multi-species community context of Parasaurolophus ecology includes the systematic faunal surveys that have quantified the relative abundances of different dinosaurian taxa in this formation and documented the specific diversity of the Campanian coastal plain fauna within which Parasaurolophus populations lived and reproduced. The Dinosaur Park Formation, one of the most systematically studied Campanian formations in the world, thanks to the extensive collection programs of the Canadian Geological Survey, the Royal Tyrrell Museum, and numerous academic research groups across more than a century of fieldwork, has produced an extraordinary sample of dinosaurian material, representing more than 40 named dinosaurian species from a stratigraphic interval of approximately 1.5 million years. The specific relative abundances of different hadrosaur species in systematic bonebed surveys of the Dinosaur Park Formation, published by Michael Ryan, Philip Curry, and colleagues in systematic faunal analyses of the formation, document Parasaurolophus as one of the less abundant Lambeosaurine species relative to the more common Corythosaurus and Lambeosaurus in most surveyed assemblages, a relative abundance pattern, potentially reflecting specific habitat preferences within the coastal plain that concentrated different hadrosaur species in different microenvironmental contexts, whose differential preservation in the fluvial bone beds introduced specific taphonomic biases in the relative abundances of different species in the recovered assemblages. The ecological interpretation of these abundance data, distinguishing genuine ecological differences in habitat use from taphonomic artifacts of differential preservation, is one of the specific paleoecological questions that the integration of sedimentological, taphonomic, and faunal data from the Dinosaur Park Formation is progressively addressing, and whose resolution will produce a more ecologically complete picture of the specific community ecology of Parasaurolophus within the broader Campanian coastal plain fauna. The specific immune biology of Parasaurolophus and the specific ways in which the immune system of this large Cretaceous hadrosaur managed the specific microbial and parasitic challenges of the Campanian environment is one of the biological dimensions of this species, whose reconstruction from the fossil record is most constrained by the absence of direct biological material, and whose inference from the comparative biology of modern archosaurs provides the primary scientific access to this aspect of the animal's physiology. The immune systems of modern birds and crocodilians, both sophisticated and well characterized at the molecular biological level, share the fundamental organization of the vertebrate immune system: innate immunity mediated by phagocytic cells and complement proteins, adaptive immunity mediated by T and B lymphocytes, with the specific elaborations and modifications that characterize each lineage. The inference that Parasaurolophus possessed a comparable organization of innate and adaptive immunity, maintained by specific lymphoid tissues in the appropriate anatomical locations within the body, is one of the most securely grounded inferences about the physiology of this species. Because the vertebrate immune system organization is extraordinarily conserved across the full diversity of jawed vertebrates and has been maintained with relatively minor modification across the evolutionary history of the lineage, from the earliest jawed vertebrates through the archosaur radiation to the present. The specific pathogens and parasites that Parasaurolophus would have encountered in the Campanian environment, inferred from the diversity of bacterial, viral, and parasitic organisms documented in the Cretaceous ecological record, and from the comparison with the pathogen communities of modern large terrestrial herbivores in subtropical environments, would have required an immune system of specific organizational complexity, capable of recognizing and responding effectively to a wide variety of pathogen types across the ecological range of Campanian environments that Parasaurolophus Inhabited. The Parasaurolophus skull as a physical object. The specific three-dimensional arrangement of bony elements and internal hollow passages that constitutes the primary physical evidence for the acoustic biology of this species is one of the more remarkable physical objects in the entire natural history museum world, combining the functional complexity of a sophisticated acoustic instrument with the biological complexity of an animal's head and the geological complexity of a fossil preserved through millions of years of diagenetic modification into the specific mineralized form in which museum visitors and researchers encounter it today. The specific experience of examining a well-preserved Parasaurolophus walkeri skull in a museum collection, seeing the specific curvature of the crest tube extending behind the posterior margin of the skull, tracing the specific path of the hollow passages that run the full length of the crest and return to the nasal region of the skull face, and appreciating the specific engineering achievement of a biological structure that combines the acoustic properties of a resonating chamber with the physical requirements of a lightweight bony skull in a single anatomical structure, is one of the more intellectually and aesthetically profound experiences available in natural history science. The skull of Parasaurolophus is simultaneously a specific biological object, the preserved remains of the head of a specific individual animal that lived approximately 75 million years ago in the coastal forests of Cretaceous Alberta, and a specific scientific instrument, the physical record of the specific three-dimensional geometry from which the acoustic properties of the living animal's crest vocalization system have been mathematically derived. The combination of these two dimensions of significance, the biological and the scientific, makes the Parasaurolophus skull one of the most intellectually rich individual objects in the entire natural history museum world, combining the deep evolutionary history of the biological object with the mathematical precision of the scientific interpretation in a single extraordinary fossil that rewards the investment of understanding with a uniquely complete biological portrait of one of the most remarkable non-avian dinosaurs in the history of vertebrate life, the molecular evolution of the specific genes responsible for the bone development biology of the Parasaurolophus crest, and the specific evolutionary changes in the genetic regulatory systems that produced the progressive elongation of the nasal bones and premaxilla into the elongated crest structure from the shorter and less dramatically modified skull. Anatomy of the basal Hadrosaur ancestors is one of the evolutionary developmental biological questions about Parasaurolophus that the comparative genomics of modern birds and crocodilians can partially approach through the identification of the specific gene regulatory networks responsible for craniofacial bone development in modern archosaurs, the specific genes responsible for the development of cranial bone morphology in modern birds, including the specific transcription factors, signaling molecules, and regulatory sequences whose expression patterns determine the specific three-dimensional geometry of different cranial bones during embryonic and post-embryonic development, are increasingly well characterized in the developmental genetics literature and provide specific molecular targets for evolutionary analysis of the developmental basis of cranial diversity in the archosaur lineage. The specific evolutionary changes in the regulatory sequences controlling the expression of these craniofacial development genes that produced the dramatic elongation of the nasal passage in the Lambeosaurian lineage, the specific promoter, enhancer, and other regulatory sequence modifications that extended the developmental fate of the nasal bones and premaxilla to produce the specific crest geometry of adult Parasaurolophus, are in principle identifiable through the comparative analysis of the relevant regulatory sequences in modern archosaurs though the specific regulatory changes responsible for any particular morphological difference in extinct animals are in practice recoverable only through the indirect inference of the comparative analysis rather than from ancient genomic sequences recoverable from Mesozoic fossil material. The connection between the macroscopic biology of the Parasaurolophus crest and the microscopic biology of the gene regulatory changes that produced the crest during Lambeosauran evolution is one of the more intellectually ambitious research directions in the evolutionary biology of this species, and represents a productive frontier for the integration of evolutionary genetics with paleontological morphology. The acoustic physics of the Parasaurolophus crest and the specific physical principles whose mathematical application to the internal passage geometry of this structure produces the specific resonant frequency predictions that are the primary quantitative basis for the acoustic function. Interpretation. Connect the biology of this Cretaceous hadrosaur to the fundamental physics of sound in ways that make the acoustic interpretation of the crest one of the most rigorously physically grounded behavioral interpretations in all of the non-avian dinosaur paleontology. The acoustic resonance of a tube-shaped chamber is governed by the specific relationship between the total path length of the sound wave through the chamber, the specific speed of sound in the medium filling the chamber, and the specific boundary conditions at the open ends of the chamber where the sound wave transitions between the enclosed and open acoustic environments. The specific resonant frequencies of the Parasaurolophus crest passage system are determined by these physical parameters: the specific total path length of the nasal passage through the crest, the specific speed of sound in air at the relevant temperatures, and the specific reflection conditions at the nostril opening and the nasal pharyngeal junction in a way that is calculable from first principles of acoustic physics and that produces specific frequency predictions. Mathematical derivation is transparent, reproducible, and independently verifiable by any researcher with access to the specific passage, geometry, data, and the relevant acoustic equations. The specific rigor and mathematical transparency of the acoustic modeling calculations, combined with the specific physical grounding in first principles of acoustic physics rather than in biological analogies or qualitative comparisons, is what makes the acoustic function interpretation of the Parasaurolophus crest the most rigorously specified and most mathematically secure behavioral interpretation in the history of non-avian dinosaur behavioral paleontology, and it is the foundation on which the confidence of the 100 facts of this documentary in the acoustic function of the crest ultimately rests. The 100 facts about Parasaurolophus, the dinosaur that could sing, have traveled from the geological context of the Campanian western interior through the specific anatomy of the elongated crest, through the acoustic physics of the resonant passage system, through the evolutionary biology of sexual selection and species recognition, through the comparative biology of modern large vocal vertebrates, through the paleoecology of the Campanian coastal plain community, through the bone histology and stable isotope geochemistry of Parasaurolophus biology, through the discovery history and museum collections of this species, and through the broader scientific and cultural significance of the acoustic interpretation of the crest in the history of paleontological science. The journey through these 100 facts has been a journey through the full scope of the biological, physical, evolutionary, and cultural dimensions of understanding one of the most extraordinary non-avian dinosaurs documented in the fossil record of the Mesozoic world. At the center of this journey, from beginning to end, has been the crest, the hollow bony tube that extends behind the skull of Parasaurolophus and whose specific internal geometry encodes the acoustic properties of a biological sound instrument of extraordinary power, sophistication. The crest was the specific evolutionary product of millions of years of selection pressure in Campanian hadrosaur populations for acoustic communication effectiveness. It was the specific anatomical innovation of the Lambeosaurin lineage, whose progressive elaboration produced the most extreme example of nasal passage extension for acoustic purposes documented from any vertebrate in the geological record. And it is the specific physical object whose preserved three-dimensional geometry allows the mathematical calculation of the specific sounds that Parasaurolophus produced in the Cretaceous forests of western North America. 75 million years ago. 100 facts. The crest, the sound, the song of the most remarkable hadrosaur in the history of vertebrate life. The story of Parasaurolophus is ultimately a story about the specific biological power of evolution to produce extraordinary solutions to specific biological problems. The problem, in this case, of effective, long-distance communication in dense, forested environments, where visual communication is limited by vegetation, and where the acoustic environment is dominated by the high-frequency sounds of wind, water, and diverse biological sources that attenuate rapidly and cannot carry the specific social information that a large social herbivore with complex reproductive competition and predator alarm requirements needs to transmit effectively across the full extent of its social group. The specific evolutionary solution that the Lambeosaurin lineage developed for this specific communication problem, the progressive elongation of the nasal passages into the hollow crest tube, whose resonant properties specifically amplify low-frequency sounds of the specific wavelengths and intensities, most effective for long-distance propagation in forested environments, is a biological engineering achievement of remarkable elegance and effectiveness, whose specific physical properties are documented with mathematical precision from the preserved geometry of fossil skulls recovered from the Cretaceous rock of western North America. The 100 facts of this documentary about Parasaurolophus are 100 different angles of view onto this single central biological achievement. The evolution of the acoustic crest, seen from the perspectives of anatomy, physics, ecology, evolution, behavior, paleoclimate, and cultural significance, that together produce the most complete and most biologically rich portrait of this extraordinary dinosaur that human science has yet assembled. The song of Parasaurolophus has been silent for 75 million years. The physics of its hollow skull brings it back. 100 facts. The dinosaur that could sing. The specific sensory integration that allowed Parasaurolophus to navigate its social and physical environment. Combining the acoustic information from crest vocalizations with the visual information from crest silhouettes and body coloration with the olfactory information from chemical signals in the air and on the substrate, produced a multimodal sensory picture of the social world that was as rich and as behaviorally informative as the sensory worlds of the large social vertebrates of the modern world. The specific hierarchy of sensory modalities in Parasaurolophus' social behavior, which sensory channel was primary for which type of social decision, how conflicting information from different sensory channels was resolved in specific behavioral contexts, and how the relative contributions of acoustic, visual, and chemical information to specific behavioral outputs changed across different environmental conditions, is one of the more complex behavioral biological questions about this species, whose reconstruction from the fossil record requires the most intensive integration of comparative sensory biological evidence from modern archosaurs with the specific anatomical evidence for the sensory organs of Parasaurolophus preserved in the fossil material. The specific dominance of the acoustic channel in long-distance social communication in forested environments confirmed by the physical acoustic properties of the crest passage system and by the specific attenuating effects of forest vegetation on visual signals, suggests that acoustic information was the primary channel for the specific social decisions, most requiring long-distance information, predator alarm, conspecific location, mate attraction from a distance, while visual and chemical information supplemented and refined acoustic information in the closer range social interactions of established group members interacting in direct proximity. The integration of these multiple sensory channels in the specific neural processing of social information in Parasaurolophus is one of the most complex behavioral biological aspects of this species, and one whose full understanding awaits. The development of more complete comparative neuroscience frameworks for the specific sensory integration biology of large-brained social archosaurs, whose ecological situations most closely approximate those of Campanian hadrosaur populations. The specific calcium phosphate mineralization of the Parasaurolophus skeleton, and the specific diagenetic transformations that converted the original bioapatite bone mineral of the living animal into the permineralized fossil bone of the museum collections, document the specific taphonomic history of the preserved material and provide important context for assessing the reliability of the specific geochemical analyses, oxygen isotopes, carbon isotopes, trace element concentrations that researchers apply to fossil bone and tooth material in the reconstruction of the biological and environmental conditions experienced by living Parasaurolophus individuals. The original bioapatite mineral of vertebrate bone and tooth enamel, composed of hydroxyapatite, doped with specific trace elements and bearing specific isotope ratios, reflecting the chemistry of the body fluids and diet of the living animal, is progressively modified during fossilization by the introduction of ions from the surrounding pore fluid, the recrystallization of the original nanocrystalline bioapatite into larger crystallographic structures with different physical properties, and the substitution of specific ions in the crystal lattice by ions from the burial environment, whose concentrations in the pore fluid differ from those of the original bioapatite. The specific degree of diagenetic alteration experienced by any given Parasaurolophus specimen is accessible from the specific crystallographic properties, crystallite size, degree of crystallographic order, lattice parameters of the fossil mineral relative to the known properties of unaltered bioapatite, and the specific reliability of geochemical analyses performed on Parasaurolophus material for specific biological interpretations depends directly on the specific degree of diagenetic preservation quality documented for each analyzed specimen. The progressive development of more sensitive screening methods for diagenetic alteration and of analytical approaches capable of recovering reliable biological signals from partially altered material by isolating the most diagenetically resistant fractions of the fossil mineral is expanding the range of Campanian dinosaurian specimens from which reliable geochemical biological data can be extracted, and is making the specific physiological and environmental biology of Parasaurolophus progressively more accessible to isotopic and geochemical analysis. The specific record of paleopathology in the Campanian hadrosaur fauna and the specific evidence for the health conditions and injury histories of individual Parasaurolophus animals preserved in the pathological specimens documented from Alberta and other Campanian formations provides evidence for the specific biological stresses and physical hazards experienced by these animals in the Campanian coastal plain environment. The occurrence of healed fractures in hadrosaur limb bone material from Campanian formations, documented in the published paleopathological literature on hadrosaur specimens from Alberta and equivalent formations, confirms that individual animals survived specific traumatic injury events and continued to function after healing, implying sufficient behavioral capability to escape predators and continue foraging during the healing period, and the physiological resources to support bone remodeling while maintaining normal metabolic function. The specific types of fractures most commonly documented in hadrosaur material: midshaft fractures of long bones, compression fractures of vertebrae, and various joint-related pathologies reflect the specific mechanical risks of the hadrosaur lifestyle, including the specific risks of falls and collisions during bipedal running escape from predators, the specific compressive loads on the spine during quadrupedal locomotion and foraging, and the specific joint wear resulting from sustained locomotor activity across the lifetime of the animal. The joint pathologies documented in older large hadrosaur individuals, including specific degenerative changes in articular surfaces comparable to the osteoarthritic changes documented in old age in modern large terrestrial mammals, confirm that individual Parasaurolophus animals did achieve sufficient age for the cumulative wear of the joint surfaces to produce detectable pathological changes, providing indirect evidence for the specific maximum lifespan achievable by this species under the specific predation and environmental conditions of the Campanian western interior. The specific paleobiogeographic connections between the Campanian fauna of western North America and the contemporaneous faunas of Asia, documented by the specific patterns of shared or closely related genera across the two continental regions, provide evidence for the specific land connections and dispersal events that allowed faunal exchange between Laramedia and the Asian continent during the Campanian. The Beringian land connection between Asia and North America, intermittently available during the Cretaceous as sea level fluctuations exposed or submerged the shallow marine Bering Sea region, provided the specific dispersal route through which hadrosaurs, including lambeosaurines, dispersed between the two continental regions during the Late Cretaceous, producing the specific biogeographic pattern of shared lambeosaurine genera between North America and Asia that documents the specific timing and direction of dispersal events within the lambeosaurine radiation. The specific direction of dispersal in the lambeosaurine exchange between North America and Asia has been debated in the biogeographic literature, with some analyses favoring the origin of the lambeosaurine clade in North America, followed by dispersal into Asia, and others favoring an Asian origin, or multiple exchange events in both directions. And the specific resolution of this question has direct implications for understanding the specific evolutionary history of the Parasaurolophus crest type within the context of the global lambeosaurine radiation. The specific comparison of Parasaurolophus with the Asian lambeosaurines, particularly Tyrannosaurus from China and Olorotitan from Russia, in the context of the specific biogeographic history of the lambeosaurine radiation, is one of the more productive research directions for understanding the specific evolutionary origins of the Parasaurolophus crest. Geometry within the global evolutionary context of the hollow-crested hadrosaur lineage. The 100 facts about Parasaurolophus, the dinosaur that could sing, are now complete, assembled from the full range of physical, chemical, biological, and evolutionary evidence available from more than a century of scientific investigation of this extraordinary Cretaceous hadrosaur, from the specific geological context of the Campanian western interior through the specific anatomy of the elongated hollow crest, from the specific acoustic physics of the resonant passage system through the specific evolutionary biology of sexual selection in Campanian hadrosaur communities, from the specific ecology of the Campanian coastal plain through the specific discovery history of Parasaurolophus material, Across more than a century of North American paleontological fieldwork, these 100 facts represent the most complete and most rigorously evidence-based portrait of Parasaurolophus biology that current science is capable of producing. The physical evidence is in the museum collections. The analytical results are in the scientific literature. The comparative biological frameworks are documented in the biology of living archosaurs, and the mathematical certainty of the acoustic calculations rests on the specific geometry of the preserved passage system and the immutable laws of acoustic physics. The song of Parasaurolophus has been silent for 75 million years, but the hollow geometry of its fossilized skull still holds the mathematical record of the specific frequencies at which it resonated. The science has read that record, calculated those frequencies, and presented their biological meaning in the 100 facts of this documentary. 100 facts. The dinosaur that could sing. The most acoustically remarkable chapter in the history of non-avian dinosaur paleontology, offered to the world from the hollow bones of the most extraordinary hadrosaur that Cretaceous North America produced. The specific post-Campanian history of the Lambeosaurine lineage, tracing the evolutionary fate of the hollow-crested hadrosaur clade from its Campanian peak diversity through the Maastrichtian and up to the end Cretaceous extinction event that terminated the non-avian dinosaurian lineages, provides the evolutionary conclusion to the specific story of the Parasaurolophus crest acoustic system and documents the specific biological conditions under which the most acoustically sophisticated of all non-avian dinosaurs ultimately went extinct alongside the rest of the non-avian dinosaurian radiation. The Maastrichtian hadrosaur fauna of North America shows a specific pattern of faunal turnover from the Campanian composition, with some Campanian Lambeosaurine genera persisting into the early Maastrichtian and some being replaced by different Lambeosaurine genera as the specific environmental and ecological conditions of the Maastrichtian western interior differed from those of the Campanian. The specific survival or extinction of Parasaurolophus through the Campanian-Maastrichtian boundary is a question whose resolution depends on the specific stratigraphic documentation of Parasaurolophus material in Maastrichtian formations, where the available evidence is currently insufficient to establish whether the genus persisted beyond the Campanian or was among the hadrosaur genera replaced by other lineages during the specific faunal turnovers documented at the Campanian-Maastrichtian transition. The ultimate extinction of all Lambeosaurine hadrosaurs at the end of the Cretaceous, along with the rest of the non-avian dinosaurian fauna, terminated the specific evolutionary trajectory of hollow crest acoustic system development that had produced the extraordinary acoustic diversity of the Campanian Lambeosaurine fauna. The specific acoustic systems of the Campanian Lambeosaurines, the most sophisticated biological resonating chambers produced by any vertebrate lineage across the 400 million year history of jawed vertebrate life, were silenced by the end Cretaceous extinction event 66 million years ago, leaving only the preserved geometry of their fossilized skulls to document the extraordinary acoustic biological achievement that the Lambeosaurin radiation had produced across the Campanian interval of hadrosaur evolutionary history. The specific emotional and intellectual experience of understanding the acoustic biology of Parasaurolophus, of appreciating that the hollow geometry of a 75 million year old fossilized skull encodes the specific frequencies of the sounds that a living animal produced in the Cretaceous forests of western North America, and that the mathematical analysis of that geometry can recover those frequencies with a degree of precision and certainty comparable to that achievable in the acoustic analysis of any modern musical instrument, is one of the more remarkable intellectual experiences that the science of paleontology offers to the human understanding of the natural world. The specific experience of hearing a computer-generated simulation of the predicted Parasaurolophus crest vocalizations, derived from the specific acoustic modeling calculations and available through museum exhibits and online media, provides direct sensory access to the predicted sounds of this extinct animal in a way that connects the abstract mathematical analysis of the crest geometry to the immediate sensory reality of what those sounds would have been like in the Cretaceous acoustic environment. The deep resonance of the predicted Parasaurolophus call, the specific low-frequency, horn-like quality of a sound produced at 30 to 80 Hz in a large resonating chamber, is not merely intellectually interesting, but aesthetically powerful, connecting the human listener to an acoustic experience that no living human has ever had, and that the geological record has preserved in the specific geometry of fossilized bones for the specific purpose, from the perspective of the science that reads it, of being recovered, calculated, and shared with the 21st century world. The 100 facts of this documentary about Parasaurolophus are 100 contributions to this experience, 100 specific pieces of knowledge that together make the understanding of the dinosaur that could sing as complete, as specific, and as emotionally resonant as the science of the fossil record allows. The crest, the calculation, the sound, the extraordinary gift of the hollow bones. The broader significance of the Parasaurolophus crest acoustic system for the understanding of vertebrate sensory evolution during the Mesozoic. The specific contribution this species makes to the understanding of how sophisticated sensory communication systems evolved in the non-avian dinosaurian lineages of the Cretaceous connects the specific biology of this individual species to the larger narrative of sensory evolution in the most successful group of terrestrial vertebrates that the geological history of life has produced. The Mesozoic era, traditionally characterized in popular imagination as a world dominated by physically powerful but behaviorally simple animals, was in fact a world of extraordinary behavioral and sensory complexity, whose specific expression in different dinosaurian lineages ranged from the acoustic sophistication of the Lambeosaurine hadrosaurs through the elaborate visual display, biology of the ceratopsians and pachycephalosaurs through the cognitive complexity of the large-brained Maniraptoran theropods. The acoustic biology of Parasaurolophus represents the specific expression of sensory evolution in the Hadrosaur lineage, the specific evolutionary investment of the Lambeosaurine clade in the acoustic channel as the primary medium for long-distance social communication in the specific forested environments of the Campanian coastal plain. The parallel investments of other Campanian lineages in the visual channel through the evolution of elaborate horns, frills, and crests, and in the cognitive channel through the evolution of large brain-to-body size ratios in the Maniraptoran theropods, document the diversity of evolutionary solutions to the specific communication and social coordination challenges facing large social vertebrates in the complex ecological communities of the Late Cretaceous. Parasaurolophus, as the most completely documented and most rigorously analyzed example of acoustic communication system evolution in any non-avian dinosaur, represents the clearest and most scientifically precise window into this broader picture of Mesozoic sensory evolution and contributes the most specific and most mathematically grounded of all the individual species' behavioral reconstructions available from the Campanian fauna, 100 facts, the acoustic window, the song preserved in the rock. The final fact about Parasaurolophus, the dinosaur that could sing, is the simplest and the most profound. Its song is recoverable. The hollow bones are in the museums. The geometry is measurable. The physics is calculable. The frequencies are predictable. The biology is interpretable. And the science that performs this recovery, that takes the three-dimensional geometry of a 75-million-year-old fossilized skull passage system and calculates from it the specific acoustic frequencies that a living animal produced in a Cretaceous forest, is one of the most remarkable intellectual achievements in the history of human scientific inquiry into the natural world. The 100 facts of this documentary are 100 demonstrations of this recoverable truth, 100 specific pieces of knowledge about the anatomy, the acoustics, the ecology, the evolution, and the cultural significance of Parasaurolophus that together constitute the most complete and most scientifically grounded portrait of this extraordinary animal that current science is capable of producing. The song of Parasaurolophus was last heard in the Cretaceous forests of western North America approximately 75 million years ago. The fossilized geometry of its hollow skull preserved the mathematical record of that song through all the geological transformations and all the temporal distance separating the Cretaceous from the present. The science of paleontology has read that record, calculated those frequencies, and shared the result with the world as 100 facts about the dinosaur that could sing, the crest, the passages, the resonance, the sound, the extraordinary truth of the most acoustically remarkable non-avian dinosaur that the history of vertebrate life has produced, recovered from the silence of 75 million years by the mathematics of the hollow bone and the intellectual commitment of the scientists who have devoted their careers to understanding the most musical chapter in the history of the Mesozoic world. The acoustic ecology of the late Cretaceous western interior, understood as the complete soundscape of an entire biome, is one of the more imaginatively rich and scientifically grounded reconstructions available from the Campanian fossil record, because the specific vocalizations predictable from the acoustic anatomy of diverse Campanian vertebrates can be combined with the specific ambient environmental sounds of the coastal plain ecosystem into a composite acoustic picture of the Mesozoic world that is more complete and more physically grounded than any other aspect of the sensory environment of this ancient biome that science has yet been able to reconstruct. The low-frequency vocalizations of Parasaurolophus at 30 to 80 Hz with carrying distances potentially measured in kilometers would have been the lowest frequency and longest range biological sounds in the Campanian soundscape, and would have constituted a specific acoustic layer of the environmental soundscape at frequencies below the range most intensely occupied by the diverse avian fauna, whose diverse and high-frequency songs contributed the higher frequency acoustic layers of the Campanian ambient noise field. The specific calls of Gorgosaurus and other large tyrannosaurid predators, produced through laryngeal structures comparable to those of modern crocodilians, and potentially at frequencies intermediate between the deep Parasaurolophus fundamental and the higher frequency bird songs, would have added a specific mid-frequency acoustic layer to the Campanian soundscape, whose temporal patterns, concentrated in the periods of active predatory hunting, would have been one of the specific acoustic features most relevant to the alarm communication function of the Parasaurolophus acoustic system. The ambient sounds of the coastal plain environment, the wind in the Cretaceous forest canopy, the sounds of river channels and coastal wetlands, the background, acoustic haze of the diverse insect fauna would have determined the specific noise floor within which all biological communication signals had to achieve sufficient signal-to-noise ratio for effective detection and behavioral response by the intended recipient. The Campanian acoustic world was as complex, as biologically rich, and as physically governed by the same acoustic physics that governs modern acoustic environments as any modern equivalent ecosystem, and the specific place of the Parasaurolophus vocalizations within this acoustic world is one of the most concretely imaginable and most physically grounded aspects of the daily sensory experience of life in the late Cretaceous coastal forests of Western North America. The contribution of the Parasaurolophus Acoustic Research Program to the broader field of paleontological behavioral science, and the specific ways in which the methodological advances and specific scientific conclusions of this research program have influenced the approach of other researchers to the reconstruction of behavioral capabilities in other non-avian dinosaurian lineages, illustrates the broader scientific legacy of the study of this species beyond its specific biological significance. The demonstration that specific behavioral capabilities, in this case, the production of specific acoustic frequencies through specific anatomical resonating structures, can be quantitatively reconstructed from the preserved anatomy of fossil specimens using the mathematical principles of relevant physical sciences, has inspired analogous approaches to the reconstruction of other behavioral capabilities from the preserved anatomy of other fossil species. The application of comparable physical modeling approaches to the reconstruction of the visual capabilities of extinct animals from the specific optical anatomy of their eyes, to the reconstruction of the balance and vestibular capabilities of extinct animals from the specific geometry of their semicircular canals, and to the reconstruction of the bite forces of extinct animals from the specific geometry of their jaw, muscles and lever arms, all reflect the broader methodological legacy of the physical model-based approach to behavioral reconstruction that the Parasaurolophus Acoustic Research Program exemplifies. The specific intellectual contribution of the Parasaurolophus acoustic research to this broader methodological development is the demonstration that the quantitative, physics-based approach to behavioral reconstruction can produce specific, precise, and independently verifiable conclusions about the behavioral capabilities of extinct animals from the specific geometry of their preserved anatomical structures. A demonstration whose success in the Parasaurolophus case has provided both methodological inspiration and specific analytical precedent for the application of comparable approaches to other fossil behavioral biology questions across the full diversity of the vertebrate fossil record. 100 facts about the dinosaur that could sing, and behind them, one of the most methodologically productive research programs in the history of paleontological behavioral science. The 100 facts about Parasaurolophus, the dinosaur that could sing, are complete. Behind each fact lies specific physical evidence, specific scientific analysis, and the specific intellectual effort of the specific researchers who have devoted their careers to understanding one of the most remarkable non-avian dinosaurs that the fossil record of the Mesozoic world preserves. The skulls are in the museums. The calculations are in the literature. The song is in the mathematics of the hollow bone. And the 100 facts of this documentary are the current best account of what that song meant, what biological system produced it, what physical principles governed its acoustic properties, what ecological and social functions it served in the specific communities of the Campanian Western interior, and what evolutionary forces drove the progressive elaboration of the anatomical structure that produced it through the Lambeosaurine Hadrosaur lineage across the Campanian interval. The science of paleontology has given the world 100 specific facts about an animal that has been extinct for 75 million years, and among the most remarkable of those facts is the simple truth that we know what it sounded like. 100 facts: the crest, the passages, the resonance at 30 to 80 Hz, the song of the most acoustically remarkable non-avian dinosaur, the extraordinary intellectual achievement of the science that heard it from the hollow geometry of its ancient bones. The specific discovery of Parasaurolophus material in the Kaiparowits Formation of Utah by the teams of the Natural History Museum of Utah, including the remarkable juvenile specimen nicknamed Joe, that provided the first well-documented small growth stage individual for quantitative ontogenetic analysis, illustrates the specific value of sustained systematic field programs in productive Campanian formations for advancing the understanding of specific dinosaurian species beyond what the initial discovery and description of type material could provide. The Kaiparowits Plateau of southern Utah, whose remote and challenging terrain has deterred extensive systematic paleontological exploration until relatively recently, contains one of the most completely preserved Campanian ecological records available from any formation in western North America, and the systematic field programs of the Natural History Museum of Utah and its collaborators have progressively revealed the extraordinary diversity and completeness of the Kaiparowits Formation fauna across more than 2 decades of sustained field effort. The specific Parasaurolophus material recovered from the Kaiparowits Formation by these programs, including the juvenile specimen described by Gates and colleagues, and additional partial skull material from subsequent field seasons, has substantially advanced the understanding of Parasaurolophus certocristatus, the shortest crested and most morphologically distinctive of the 3 recognized species, whose biology was previously the least well documented of the 3 species due to the relative scarcity of well-preserved material from the Kaiparowits Formation and equivalent formations. The continued exploration of productive Kaiparowits Formation exposures across the Kaiparowits Plateau is expected to recover additional Parasaurolophus material in future field seasons, progressively expanding the sample of certocristatus specimens available for the specific anatomical, acoustic, and ecological analyses, whose results will most directly complement the better documented biology of Walkeri from the Alberta Campanian fauna. The specific value of sustained systematic field programs for advancing the biological understanding of specific dinosaurian species, illustrated in the case of Parasaurolophus by the progressive expansion of the known material base through multiple decades of productive field research in multiple Campanian formations across western North America, is one of the clearest arguments available for the sustained institutional investment in paleontological fieldwork that the natural history museums and research universities engaged in Campanian dinosaur paleontology have maintained across the full history of this science. The final Dino Earth documentary about Parasaurolophus, the dinosaur that could sing, concludes with the recognition that the 100 facts assembled here represent a living scientific understanding, one that is growing with each new discovery from the productive Campanian formations of western North America, and with each new analytical application of advancing scientific methods to the existing collections of Parasaurolophus material. The specific facts presented are the most complete and most scientifically grounded account of this species available from current science, but they are the beginning of what will eventually be known about one of the most extraordinary non-avian dinosaurs that the geological record of the Mesozoic world has preserved for the understanding of the present. The hollow skull that William Parkes first described in 1922 has given a century of science the anatomical foundation for one of the most productive research programs in the history of vertebrate paleontology. The computed tomographic scans that revealed the specific internal geometry of that hollow skull in the early 21st century gave the acoustic modeling calculations the specific data from which the resonant frequency of the living crest was mathematically derived. The specific resonant frequencies that those calculations produced gave the world its first specific, quantitative, physically grounded knowledge of the sounds that a non-avian dinosaur made in the Cretaceous forests of North America 75 million years ago. And the 100 facts of this documentary have assembled all of this: the anatomy, the acoustics, the ecology, the evolution, the discovery history, and the broader significance into the most complete portrait of Parasaurolophus that current science can produce. 100 facts about the dinosaur that could sing, the hollow bones, the calculated song, the extraordinary truth of the most acoustically remarkable chapter in the biology of the most successful terrestrial vertebrate radiation in the history of life.